In this lesson, we're going to go over what you should expect from this series of videos. So in terms of topics covered, we're going to cover a pretty broad range of material. We're going to go over footprinting and reconnaissance, where you get an idea of what's involved in the engagement that you're working on and information about the target that you are engaged with. We're going to talk about networking fundamentals, and here we're going to get our hands dirty with packets and understanding TCP/IP at a deeper level, and also understanding how the different protocols work and why they work that way. We're going to talk about cryptography, where we talk about different cryptographic ciphers. We're going to deal with web encryption, so SSL and TLS. We're going to talk about certificates and creation of certificates and how they actually operate. We're going to talk about public key cryptography. We're also going to deal with scanning and enumeration, so Nmap, and dealing with Windows servers and using SNMP and LDAP and all of that sort of stuff. We're going to be talking about penetration, where we deal with different ways of getting into systems, and also go over using Metasploit, which is an exploit framework. And we're going to talk about how to use Metasploit to actually get into systems and make use of the exploits that they have available. We're going to talk about malware, so viruses and worms and rootkits and all of that sort of stuff. We're going to look at different pieces of malware and how you would pull that apart in order to understand what it's doing and potentially make use of that malware during a ethical hacking engagement. We're going to talk about different types of denial of service attacks and the difference between a denial of service attack and a distributed denial of service attack, and there is a difference there. So we're going to go over DOS attacks. We're going to talk about web application hacking and the types of tools that you would use during web application hacking, the different vulnerabilities that web applications have, and how to make use of and exploit those vulnerabilities. We're going to talk about wireless networking, how to probe wireless networks, what wireless networks are doing, and how to secure wireless networks. We are going to talk a little bit about detection evasion. And to be honest with you, detection evasion kind of comes up in a lot of different areas through many of the topics. We're also going to talk about programming attacks and how to protect against and prevent programming attacks. Now, the approach that I'm going to be taking in this series of videos is, wherever possible, we're going to be using a hands-on approach. So I'm going to show you the actual tools. I'm going to make use of the tools and do some demonstrations on how they actually work. I am a big believer in getting your hands dirty as the best way to learn anything. So as we go through this series of videos, I strongly encourage you to get access to the tools that I'm going to be demonstrating wherever possible, and dig in and get your hands dirty along with me. There are places where we're going to be going over theoretical material, and I'm not a big fan of PowerPoint slides, but sometimes they are necessary in order to convey certain types of information. So wherever possible, I'm going to minimize their use, but you will run across places where they're just a necessary evil, and we're going to have to go through some slideware in order to get some particular points across that are primarily of a theoretical nature. So that's the approach that we'll be taking through this series of videos, and I hope that you have fun as we go along the way. What is hacking? The Internet Engineering Task Force is responsible for maintaining documentation about protocols and various specifications and processes and procedures regarding anything on the Internet. They have a series of documents called Request for Comments, or RFCs. RFC 1389 says, "A hacker is a person who delights in having an intimate understanding of the internal workings of a system, computers, and computer networks in particular." While the expression hackers may go back a long time and have many different connotations or definitions, as far as computers go, some of the earliest hackers were members of the Tech Model Railroad Club at MIT, and those people and the various things that they did and were involved in are detailed in Stephen Levy's book, Hackers. For our purposes, we'll be talking about other types of hackers, although the spirit of what we do goes back to those early days. The definition of hacking or hackers changed, particularly in the 1980s, and in part as a result of a couple of people. Robert T. Morris was a Cornell graduate student who unleashed a piece of software that was called a worm on what was an early version of the internet. That worm went on to cause a lot of damage and create a lot of downtime on systems across the country and across the world. The Morris worm did end up resulting in something good, however. The Computer Emergency Response Team at Carnegie Mellon was created primarily in response to the Morris worm. Kevin Mitnick is another well-known hacker who was responsible for various acts of computer crime over a couple of decades. He was first convicted in 1988. So the definition of hacker or hacking moved from something benign to something far more sinister. In popular culture, we see hacking or hackers in the movies War Games, the movie Hackers, of course, the Matrix movies, where you can see if you look really closely, they use a tool called Nmap, which we will go into the use of in great detail later on. Also the movie Sneakers, the movie Swordfish, and on television, in addition to other places, you can see the agents at NCIS regularly doing things like cracking complex cryptography in just a matter of seconds or minutes. So what is hacking really? Hacking is about a deep understanding of something, particularly with relation to computers and computing. It's also about exploring and the joy of learning new things and understanding them very clearly and being able to manipulate those things in ways that maybe other people haven't before. It's also about digging into problems to find solutions in creative and interesting ways, and sometimes finding problems where there weren't problems previously. That's a little bit about what is hacking. In this lesson, we'll be talking about why you may want to learn to hack. Sometimes you may want to hack just for fun. As discussed previously, hacking is a tradition that goes back several decades at MIT, even preceding the computer-related definition of hacking. MIT has a long and storied history of hacking, sometimes of a computer-related nature, which in this case happens to be true, sometimes of a non-computer-related instance. Here, MIT's homepage has been hacked, or you might say defaced, to indicate that Disney is buying MIT. This was an April Fool's Day prank in 1998. And again, this is just kind of for the fun of it. Sometimes you want to make a social or political point. In this case, again, MIT. Bill Gates donated some money that allowed MIT to have a new building. He was coming to MIT to visit and to speak, and the Microsoft Windows systems that were installed in the entryway at the building were hacked to be running Linux instead. And you can see here Tux the Penguin is saying, "Welcome to the William H. Gates building." And again, that's some students who decided they wanted to make a point about Linux and Microsoft and Windows to Bill Gates. Sometimes you hack just for the challenge. Here's an example, again at MIT, where some students turned the facade of a building into a Tetris game board. This was a reasonably difficult hack, and the students went after it just for the challenge of completing it, just so they could have some pride of ownership and to be able to say that they were able to pull this off in spite of its difficulties and its challenges and all of the obstacles and planning that had to go into it. And they were able to pull it off, and they have those bragging rights now. So that was one that was just for the challenge of doing it. Sometimes you want to hack to prevent theft. And this is where we get more specifically into computer-related hacking. You'll see a lot of articles and stories in the news over the last few years about cybercrime. And here's an example. Data theft compromised fewer than 1.5 million cards for global payments. So there are some attackers who got into this company, Global Payments, and they were able to pull about 1.5 million credit card numbers during an intrusion there. So what you may want to do is you may want to learn how to hack in order to find holes in your own systems or applications, or your employer's systems or applications, so that you can fix those holes and prevent these compromises from happening because of the reputational hit that your company would have to take, or because of the loss of customers, or because that loss of customers may eventually lead to the company going out of business, which means you lose your job. So here's a good reason to hack. You may want to find all of the problems that exist in your systems before putting them out and deploying them, so that you can keep these attackers from getting in and stealing critical or sensitive information. Sometimes you may want to hack to get there before the bad guys. Same sort of idea as the last one we were just talking about. Here's some attack code that was published for critical Internet Explorer flaw. There are a number of people in the world who go out looking for these flaws. They call themselves security researchers. They get in touch with vendors after they've found a flaw or a bug and work with the vendor to get it fixed. What they end up with is a bit of a reputation. They get a name for themselves. That name recognition may end up getting them a job or some speaking engagements or a book deal, any number of ways that you could cash in on name recognition from finding these sorts of bugs and getting them fixed. So you want to get there before the bad guys. You may think you're helping out a vendor. You may want to just make a name for yourself. And you want to find these sorts of bugs before the bad guys do. Because the thing about the bad guys finding them is they don't announce them. They don't get them fixed. And that makes everybody a little less secure. Finally, you may want to protect yourself. Hacked companies fight cyber criminals. This is a news headline from June 18th, 2012. We're starting to see these sorts of news headlines show up as companies are starting to retaliate against attackers. In order to retaliate against attackers, you need to be able to have the same sorts of skills and techniques and knowledge and experience that those attackers have. Or your company may want you to learn to hack, or the company may want to bring in people who are skilled at these sorts of activities so that they can attack the attackers, and hopefully you end up with a more steely exterior and you get a reputation for not being a company that people want to go after. And those are several reasons why you may want to hack. In this lesson, we're going to be talking about different types of hacking. The first type of hacking that I want to discuss is ethical hacking, which is really what we're going to be talking about through the rest of these lessons. Now, an ethical hacker is somebody who thinks like a black hat hacker, or thinks like somebody who's intent on breaking into your system, but follows a moral compass that's more in line with probably the majority of the population. So their intent isn't to do bad things. Their intent is to look for bad things and get them fixed so that bad things don't happen. Ethical hackers aren't out to destroy anything, and they're not out to break anything unless it's deemed to be acceptable as part of the engagement and also necessary in order to demonstrate a particular vulnerability to the organization that they are working with. So that's an ethical hacker. And there is a certification that's available from the EC Council. It's a certified ethical hacker. And, if you find certifications valuable and this sort of thing is what you want to do, pursuing a certified ethical hacker may be something that you want to look into. Now let's talk about black hat hackers. There's certainly plenty of cases of black hat hackers through the years. This guy right here is a particularly good example, probably because he was a black hat for a lot of years. His goal was to cause mischief and to steal where necessary and to just be engaged in the lifestyle of being a hacker and doing whatever was necessary to continue doing that, whether it crossed moral or ethical boundaries or not. So Kevin Mitnick here was involved for well over a decade in computer crime and was finally picked up by the FBI, and he was charged and prosecuted, and he was eventually convicted of some of the activities that he was involved with. Now, you may be able to argue that Kevin is a gray hat hacker as well. And a gray hat hacker is somebody who kind of skirts the line between black and white hat hacking. And white hat hacking is really what an ethical hacker is. So instead of saying ethical hacker, you could say white hat hacker. It's the same idea. A white hat hacker is somebody who hacks for good, if you want to think of it like that, if you want to think about it as good versus evil. And what they really are doing is they're in it for the technical challenge. They're looking to make things better, make things more efficient, improve them in some way. A black hat hacker is out for the money, for the thrill. It's really a criminal activity. A gray hat hacker is somebody who may employ the tactics and techniques of a black hat hacker, but have sort of a white hat focus. In other words, they're going to do things that may be malicious and destructive in nature, but the reason they are doing it is to improve the security posture of an organization that they are working with. So you can see there's actually a book called Gray Hat Hacking. It's a pretty good book, and it details a lot of the tactics and strategies and techniques that we'll be going over in subsequent lessons. Now, one other type of hacking that I want to talk about is this thing called hacktivism. And you'll find hacktivism all over the place. And one example in the last year or so, and certainly in recent memory, is Lulz Security. And you could argue that Lulz is actually a response to another type of hacktivism. An organization called Anonymous started hacking companies like Sony to protest their involvement in a lawsuit regarding a PS3 hacker. Lulz Security was supposedly protesting the treatment of Anonymous, or was hacking in support of this group Anonymous. So they hacked a number of companies and did things like pulled information, usernames, and passwords from databases at these companies. And they said the reason was to shine a light on the security of these companies, and also theoretically to embarrass the companies with their weak or poor security postures. The problem with what they were doing, though, was they were posting information that they found online, and that information often included details about the customers for these particular corporations. And for an ethical hacker or a white hat hacker, that would cross the boundary of causing harm. So there's no reason for me as an ethical hacker to post information in a public forum about somebody because I could be doing damage to them. In this case, Lulz Security and Anonymous, but specifically Lulz Security, were engaged in a form of hacktivism. And what they were doing was not only damaging to the corporations, that certainly was detrimental to those people. So different types of hackers, different types of hacking. We've got ethical or white hat hacking. We've got black hat, gray hat, and then finally we've got hacktivism. It's really the goals and the means that vary from one to the next. This lesson is about the importance of being ethical and ethical behavior. One really important reason for exhibiting ethical behavior and being ethical is that it inspires trust, and trust is a really important thing when you're looking for people to engage you in the activity of ethical hacking. They want to make sure that you are not going to exceed the bounds of your authority, and also that you're not going to do something that's going to damage their infrastructure or their reputation or any of their systems or critical data. As with any testing, hacking comes with risks. and it's important to always get permission before you do anything with a client or any sort of engagement. Here's an example here of an instance where someone didn't get permission and things got a little out of hand. Robert Morris Jr., also called RTM, was a graduate student at Cornell, and he wrote what was probably the first internet worm, and certainly the first that had a lot of notoriety. Morris said that the worm got out of his control, and he had originally expected that it was only going to stay in the lab where he was doing some work. Instead, it got through what was then the entire internet and took down a large number of systems. Now, one of the good things that came out of this was Carnegie Mellon decided that they would create the first computer emergency response team. But in the meantime, lots of users were without any ability to get to systems or get to the internet at large. So again, it's really important to get permission before you do anything. It's also really important to know what you've agreed to do. So when you get permission, you need to make sure that it's very clear what it is you've agreed to. You need to understand what the scope of your authority is and what systems you're allowed to touch and systems that you are not allowed to touch. As I mentioned earlier, hacking, as with any testing, comes with risks. And here's an example of the risk that you take with any sort of computer testing. A worker at United Airlines was doing some systems testing, and there was an error that occurred, and as a result, about 300 flights were impacted, either delayed or canceled. So lots of people were impacted due to this one error that occurred. No matter how careful you are, there's always a risk that you're going to have some negative impact on a system. Because of that, you also want to make sure that you are communicating closely and carefully with the client or the company that you are working with. You want to make sure they know what it is you're doing and when you're doing it so that they can communicate to any customers that there's testing going on and there's a possibility for outage. So again, it's certainly in the title, ethical hacking, but I can't stress enough how important being ethical is to this whole process and the work that you're undergoing. In this lesson, we'll be talking about legal issues associated with ethical hacking. I don't want you to get the impression that ethical hacking is all sweetness and light and just endless fun with no repercussions. There are significant repercussions with these types of activities, and it's important to become aware of them. One of the repercussions is that there are laws around the world that prohibit this type of behavior, specifically because it can be used to damage infrastructure or companies or take systems down and cause financial impacts to businesses and companies. So we're going to go over some of the laws that you should be familiar with. This is by no means all of them, but just to give you a taste of what's out there. The Computer Fraud and Abuse Act was originally passed in 1984 and has been amended a couple of times. One of the important things here is in the very beginning of it, whoever having knowingly accessed a computer without authorization or exceeding authorized access. So they're making illegal unauthorized use of computer systems. And that's exactly what you're doing with ethical hacking if you don't have an agreement in place with your employer so that they know what you're doing and how you're going about doing it. We've talked about scope. Scope has to do with exceeding authorized access. So again, we go back to you want to make sure that you know what you're authorized to do and how far you are authorized to go. Going beyond that can not only get you in trouble with your employer, but it can get you in trouble with the law as well. Now, this law goes on to talk about all sorts of other activities that you can't do, like knowingly and with intent to defraud a protected computer without authorization. intentionally without authorization to access any non-public computer of a department or agency of the United States. So there's a lot of detail in this particular law, and it's worthwhile being aware and familiar with what it covers. It's not the only federal law that protects against these types of activities, however. We have the National Information Infrastructure Protection Act that talks about whoever having knowingly accessed a computer without authorization or exceeding authorized access, and that has to do with fraud and related activities. Sounds very familiar if you're familiar with the Computer Fraud and Abuse Act. What they did was they basically took the Computer Fraud and Abuse Act and did some targeted work in order to make sure that national infrastructure was protected. So that's the United States, and we have several laws, not only federal laws, but state laws as well, that you need to be aware of if you are practicing these types of activities. There are laws around the rest of the world as well. One that made news in 2007 was in Germany. They passed a computer crime law that made it illegal to possess the tools that we'll be talking about in this series of lessons. There are a number of other activities that it has made illegal as well, but that's a really big one. So if you're doing work in Germany, just having these tools, and that includes creating tools that are like this, just having these tools in some fashion is illegal. You can see here on the Slashdot article, a similar law was proposed for the United Kingdom, but it was modified after outcry from the industry. So, as I said, there are laws in the United States, there are laws around the world that you need to be aware of if you are engaged in ethical hacking activities. A couple of big examples of cases where people thought they were doing research or claimed that they thought they were doing research and ran afoul of the law. You may have heard of Mafia Boy. In 2000, he took down several prominent websites with what at the time was the first known distributed denial of service attack. And he attacked CNN, Yahoo, E-Trade, Dell, Amazon, and eBay. He claimed to have been doing research for a security tool that he was working on. I can tell you from having been through that on the internet service provider side and dealing with trying to mitigate those activities and mitigate the damage being done to the websites, that it didn't feel like research. And he was convicted of this activity and served time. Somebody else who was convicted of activity similar to that was Robert T. Morris, who was involved in the Morris worm back in 1988, where he took down a significant portion of what we now call the internet, which was slightly different at that time, was more based around universities and research activities, so it was considerably smaller by several orders of magnitude than it is today. But he took down a lot of infrastructure with this worm that he had created, which he said he was writing for research purposes. So don't expect that just saying that you are engaged in ethical hacking for research or because you are doing something to help somebody, whether it's a client or whether it's just from a good Samaritan aspect, don't expect that you are going to be okay. There are laws that protect against this sort of behavior, which again is where it comes back to making sure that you have the authority and the permission in the activities that you're engaged with. In this lesson, I'm going to be talking about methodologies. It's useful or important to have a methodology as you go through an ethical hacking engagement, so you're not using a shotgun approach and have no process or procedure to help you along. The thing about a methodology is that it provides you a framework for you to know what steps you need to take in what order you probably need to take them in so that you can have a clean, well-run engagement that actually gets results that you can present to your client. While it's certainly possible to come up with your own methodology, there are a couple of methodologies that are available, and you can certainly use those as a starting point. And you probably will want to, over time, do some refining as you continue to work more and know what works best for you and the types of engagements you have. These open source methodologies have an advantage of being available and put together by people who've put a lot of thought and have a lot of experience, but they're also very generic and not targeted to maybe the types of engagements that you expect to be working on. So while they're great starting points and you may very well use them on an ongoing basis and never make any changes, don't assume that you can't make changes to these or that they're something that's set in stone and you should never ever change them. The Institute for Security and Open Methodologies has this thing called the OSSTMM, which is the Open Source Security Testing Methodology Manual. You can find it online. You can see here I've got a PDF open of it. It's a pretty big document. It's got all sorts of extraneous information, which is important to the people who are involved in it. You've got the contributors here. And it takes several pages before we get down into the actual meat of the document. But let's take a quick skim through the table of contents. Section A is information security, and they talk about doing a competitive intelligence review and a privacy review and just document grinding. And document grinding is getting architecture documents and policies and procedures and any sort of documentation that you can get from your client or your target and just digging through it to see what you can find and what you can learn. Section B is about process security. It talks about risk assessment values, and they talk about request testing and guided suggestion testing and trusted persons testing, and those are 3 different types of testing that they have guidance around. Section C is all about internet technology security. Again, they talk about risk assessment values, and the modules for this particular section include logistics and controls, network surveying, competitive intelligence review, privacy review, the document grinding, vulnerability research and verification, internet application testing, which would be probably web applications, although it may include just network-facing applications, routing, trusted systems testing, access control testing, intrusion detection system testing, containment measures testing, password cracking, denial of service, security policy review. Then we get into communication security, where we're dealing with PBX testing and voicemail testing, and possibly a fax review, as well as looking at modems. There's a section for wireless security, and we talk about the different types of wireless networks, including Bluetooth and wireless input devices and handheld security, cordless communications, and there's also sections for RFID and infrared systems testing. So as you can see, there's a pretty detailed and comprehensive amount of information in this particular methodology document. They take a lot of things into consideration. There's also physical security, which is something that is definitely worthwhile to look at, although it may or may not be something that you would get into as an ethical hacker. Physical security is really important. It involves not only the perimeter with respect to things like fencing and guardhouses and those sorts of physical security measures, but there's monitoring, and there's also inside. This would fall under the environment review. There's things like a clean desk policy, and whether people have left information up on whiteboards that could be gathered by visitors coming through the building, or whether there's sensitive documents that have been left out on people's desks. There's also some templates here for reporting. There's some social engineering templates here, which are useful if you start getting into social engineering aspects. I wouldn't necessarily expect that you would be following this entire methodology on every engagement that you were involved with, but this is definitely a good set of information, certainly as a starting point for you to follow as you are starting to work into doing ethical hacking. Another methodology here is from the OISSG, and this is a penetration testing methodology. You can see here they've got a wiki set up and some similar sorts of things, although this is more targeted at an actual penetration test, where the other one is more geared towards something that's closer to a security assessment, where you're assessing the entire risk posture of the organization and you're doing a full round of security testing. This methodology is more targeted at, I just want to see if I can break in, and what you would do to do the penetration and how you would handle that, as well as getting out and covering your tracks, and also cleaning up and destroying any artifacts from your test. So there's not a cookbook here of these are the steps you take. It's a methodology document where at a somewhat high level, you want to talk about the different steps you would take to achieve the different goals that you have for your penetration test or your security assessment or your ethical hacking engagement. And that's the purpose of a methodology. In this lesson, we're going to be talking about types of attacks. One type of attack that you'll find common, particularly in cases of hacktivism, for example, or cases where people are trying to make a particular point or just be a general pain, is this idea of defacing. Defacing goes back for quite a while. It's the idea of sort of digital graffiti, where you've left your mark or your imprint behind so that everybody knows you were there. Primarily a website thing, and it's really just making alterations to something. It used to be pretty common a long time ago to have particular businesses or people or just organizations in general to have their home pages be replaced by this other thing that was along the lines of, hey, I was here and I took over your page. We also have a pretty common one, or certainly has been common over the years, and it's a pretty good path towards quality exploits and high-profile vulnerabilities, and that's buffer overflows. A buffer overflow is a result of the way programs are stored in memory. When programs are running, they make use of a chunk of memory called a stack, and it's just like a stack of plates. When you put a bunch of plates down, when you pull a plate off, you're going to pull the top plate. You're not going to pull the oldest plate. You're going to pull the one that was on top. So the same thing with a stack here when we're accessing memory, and this has to do with the way functions are called in memory. When you call a function, a chunk of memory gets thrown on the top of the stack. That's the chunk of memory that gets accessed. And you've got a piece of data in memory within that stack, and that's called a buffer. And when too much data is sent and tried to put into that buffer, it can overflow the bounds of the configured area for that particular buffer. Now, the way stacks are put together, we end up with a part of the stack where the return address from the function is stored. So when you overflow the buffer, you have the ability to potentially overwrite that return address, at which point you can control the flow of execution of the program. And if you can control the flow of execution of the program, you can insert code into memory that could be executed. And that's where we get buffer overflows that turn into exploits that create the ability to get like a command shell or some other useful thing from the system where the buffer overflow is running. So that's a buffer overflow in short. We also have format string attacks. And sometimes these can be precursors to buffer overflows. Format strings come about because the C programming languages makes use of these format strings that determine how data is going to be input or output. So you have a string of characters that define whether the subsequent input or output is going to be an integer, or whether it's going to be a character, or whether it's going to be a string or a floating point, that sort of thing. So you have a format string that defines the input or the output. If a programmer leaves off the format string and just gets lazy and provides only the variable that's going to be output, for example, you have the ability to provide that format string. If you provide the format string, what then happens is the program starts picking the next pieces of data off the stack and displaying them. Because of that, we can start looking at data that's on the stack of the running program just by providing a format string. And if I can look at the data, I may be able to find information like a return address or some other useful piece of information. There's also a possibility of being able to inject data into the stack using this particular type of attack. Denial of service, this is a pretty common one. You'll hear about this a lot. This is not to be confused, though, with the one that I'll be talking about after this. A denial of service is any attack or action that prevents a service from being available to its legitimate or authorized users. So you'll hear about a ping flood, a SYN flood, a Smurf attack, and a Smurf attack has to do with ICMP echo requests and responses using broadcast addresses. That one's been pretty well shut down over the last several years. You can also get a denial of service simply from a malformed packet or piece of data, where a piece of data is malformed and sent into a program. If the program doesn't handle it correctly, it could crash. If it crashes, suddenly you're not able to use that program anymore. Therefore, you are denied the service of the program, thus a denial of service. As I said, a denial of service is not to be confused with a distributed denial of service. And I know it's pretty trendy, particularly in the media, to call any denial of service a DDoS. Any denial of service is not a DDoS. A DDoS, or distributed denial of service, is a very specific thing. A distributed denial of service is a coordinated denial of service making use of several hosts in several locations. So if you think about a botnet as an example, a botnet could be used to trigger a distributed denial of service, where I've got a lot of bots that I am controlling from a remote location, and I'm using all of those bots to do something like sending a lot of data to a particular server. When I've got a lot of systems sending even small amounts of data, all of that data can overwhelm the server that I'm sending it to. So the idea behind a distributed denial of service attack is to overwhelm resources on a particular server in order to cause that server not to be able to respond in a normal way. The first known DDoS attack used a tool called Stacheldraht, which is German for barbed wire. Stacheldraht came out of some work that a guy by the name of Mixter was doing in 1999. He wrote a proof of concept piece of code called TFN, which was the Tribe Flood Network. The Tribe Flood Network was then turned into something called Trinu, and Trinu was used as more or less the basis for this program called Stacheldraht, which was then used to attack servers like eBay and Yahoo back in February of 2000. So that attack in February of 2000 was really the first known distributed denial of service attack, which is not to say that there weren't denial of service attacks previous to that. There certainly were plenty of them, but they were not distributed in nature, meaning there weren't a lot of systems used to coordinate and create a denial of service condition, and therefore we get the distributed denial of service attack. So that's a handful of types of attacks and some pretty common attacks that you're going to see. In this lesson, we're going to be talking about different skills that are required or will be learned as part of this series of videos. So initially, just for basic computing, you need a basic understanding of operating systems and how they work and how to work them. There are going to be several fundamental types of tasks that I won't be going into any detail at all on. You'll need to know how to run programs and do things like open up a command prompt without me walking you through how to do that. I'm going to assume that you have some basic understanding of how to do those sorts of tasks. You need an understanding of basic system software, and you'll need a basic understanding of how to use command line utilities. There are a number of tools and programs that we're going to be going over through this series of videos. Many of them use the command line, whether it's on Windows or Linux. You need to be familiar with typing and being able to run programs from the command line and the various command line switches and parameters that those types of programs use. From a networking perspective, you need a basic understanding of some simple networking concepts. Know what cables are and switches and hubs and how systems are networked together. You don't need a deep level of networking understanding. I'll be going through some protocols at a reasonably deep level because I think it's important as an ethical hacker to understand what's going on at the protocol level so that you can know better what you are doing and how to achieve the goals and tasks that you have before you. So we're going to be going over some protocols, so just understanding what protocols are and how they go together, those sorts of things are necessary from a networking perspective. Life skills. Yes, there are some life skills that it's important to have. I think the most important one is the ability to accept failure and persevere. By that, I mean that you're going to be running across several things that just don't work the first time around, and it's going to take a little bit of stick-to-itiveness to plug away and keep going until you get something to work. And the way that you get things to work is having an ability to problem solve. And sometimes solving problems requires being a little creative. Sometimes you need to think out of the box and come at a problem from a different perspective in order to find the solution and the way forward. You're going to run across a lot of sticky problems through the course of learning about being an ethical hacker and just doing the work, because it's not as simple as, here's a little recipe for how to do this, now go follow this recipe every time and you're going to be successful. Every situation is different, every system is different. You're going to run across some pretty sticky problems that you're going to have to just wade into and get your hands dirty with and keep failing and failing and failing until you find a way to succeed. So I think those skills are very necessary to learning how to be an ethical hacker and digging through some of the material that we'll be going over in these videos. As far as what you're going to be learning, you're going to learn how to use a lot of tools. You're going to learn networking. And by that I mean we're going to be talking about different protocols that are involved in networking systems together. You're going to learn about security. Security is the heart and soul of ethical hacking. It's why we do ethical hacking, in order to make systems and networks more secure than they were previously. That's the goal. From a networking perspective, we're going to be talking about how to read packets from network captures. We're going to go into TCP/IP and related protocols in a fairly significant amount of detail. You're going to understand how protocols interact with one another. So we're going to do all of that, and the reading packets is going to be really important. We're going to do a fair amount of that, in addition to just a fundamental approach to learning how to read packets. In several lessons, we're going to read packets as a way of understanding the different tools that we're using and how they work. You're going to learn tactics and methodologies. You're going to learn ways to use the information you've gathered in order to get more information. And information is really what this is all about. You can't do much of anything without information, and sometimes it takes a fair bit of digging in order to find that information. And what you're going to learn is the entry points and the stepping stones to get the information that you need. And then once you have that information, you're going to be learning about ways to exploit it in order to get deeper into the target. You're going to learn security awareness. We're going to be talking about risk and understanding risk and vulnerabilities, primarily recognizing the difference between a vulnerability and an exploit, and there's a significant difference there. So security awareness and understanding what a risk is and how that impacts your target is going to be pretty key to a lot of things that we talk about. So it sounds like a lot. We're going to cover a fair bit of ground, not all of it at a deep level. Sometimes we're going to skim the surface, but there's an awful lot of material to cover. So let's get started. In this lesson, we're going to be talking about penetration testing and some of the details around how it works and logistics, and specifically things like scope. So what is penetration testing? Well, not surprisingly, it's testing to see if you can penetrate something, which means you're going to check to see whether you can break into a particular thing, whether it's a server or an application. Depending on the type of engagement you've got, you may have the ability to try to break in physically to a location. But primarily, what you're going to be doing with penetration testing is you're going to be trying to break into systems and networks and applications. That's kind of what it's all about. This may actually involve social engineering attacks, so it may require you to make a phone call to somebody and get them to give you their username and password, or some other type of social engineering attack where maybe you send a URL via a crafted email. Sometimes it's just strictly a technical approach where you're running scans and you're running Metasploit and you're gaining access that way, or maybe some other type of technical application sort of connection. Sometimes it's physical access that you need. So in order to get access to a particular system, if you can get physical access, then maybe you can get in. So what are the goals of penetration testing? Well, the goals would be to assess weaknesses in an organization's security posture. You want to figure out where they're vulnerable so they can go fix these problems. You want to help them understand their risk position better and what they can or may be able to do to mitigate those risks. And ultimately, you want to be able to access systems in a particular way to find weaknesses. So those are really sort of the goals of penetration testing. From a results standpoint, when you're done your testing, what are you going to do? Well, you're probably going to generate a report. And by that, I don't mean you're going to run some automated tool and you're going to get it to generate a report for you and you're going to give that to the client and then they're going to write you a really large check. That's not really how it works. You're going to write a report detailing the findings in a detailed way. So what did you find? How did you find it? How can you go mitigate that particular risk? So you should really include remediation activities in order to fix the vulnerabilities that you find. It's pretty easy to walk around going, hey, that's a problem, and that's a problem, and that's a problem. There's really not a lot of value in that. Where there's value is, hey, that's a problem, and here is how you can go about fixing it. So let's talk about scope. How big is the breadbox? And specifically, what is it that the two of you have agreed to? So you as the penetration tester and them as the target organization or the client, what have you agreed to? Are there any exclusions? Are there any areas where you're not allowed to touch anything? So if they've got a database server, maybe there's a lot of really sensitive data on it and they're a little hesitant and they may put a don't touch this clause into the scope. So there's a lot of different reasons why they may exclude areas from the scope. And if they exclude them, trust their reasons and listen to what they have to say in terms of this is what we want you to accomplish. So along those lines, you really need to get sign-off from the target organization We've talked about this before. This is certainly all about ethics and trust, and it's also about legality, because if you do something that you don't have permission to do, you could be prosecuted for that. So definitely get the scope very clear and in writing, and with signatures attached to it as to what you can and can't do. Always get approval from the right people. Make sure you get somebody who has the right level of permissions and is the right level of management so that they can sign off on it, understanding and accepting the risk that is associated with a penetration test. So let me talk a little bit about security assessments and how they differ from penetration tests. A security assessment is a hand-in-hand approach with the client. So you would walk in doing a collaborative thing where you're a trusted partner and ally with them, and your goal isn't to penetrate them and point out all of the things that are really bad, but it's to get a full assessment of the risk that the organization is exposed to. You would probably provide more detail about fixes than maybe you would in a penetration test. What we're going to do is we're going to walk in and make sure that the policies and procedures they have in place are really what they need for the organization and the risk appetite that they've got. And we're going to make sure that the policies and procedures have controls that can tell us whether they are being actually adhered to or not. So the procedures and policies are being followed. A security assessment is probably a little bit more comprehensive than a penetration test. You would look at more factors to assess the security posture of the organization and their overall risk, and you would tailor the output based on their risk appetite and what they're most interested in. And that's not to say that I'm going to tell them what they want to hear, but if there's something that they know and I know that they're just not going to do, I'm not going to make a big deal out of it because they're already aware of it, and I'll make note of it in the report just for completeness sake, but I'm not going to go into a lot of detail. So it's really kind of a hand-in-hand collaborative approach where, again, we're not just saying what they want us to say, we're providing some real security and risk guidance toward their activities. The other thing about a penetration test is it may provide an unrealistic view. So you've got a week, let's say, to do this penetration test against your target. Now you're going to have to go in, you're going to have to get set up, and you're also going to have to start doing a bunch of scans and make sure that you're gathering information and screenshots and data for your reports. You're going to have to do all sorts of activities. Also, during the course of that week, you're going to be engaged in probably beginning to write your report and getting a sense of what it's going to say and what's going to be in it. If you don't actually get any major penetration during the course of that week, the organization may feel like they are quote-unquote secure. That's one of the reasons why penetration testing, while really sexy and showy, is nice and all, but if an organization walks out of it believing that in a week you didn't manage to, get the keys to the kingdom, then they must be secure. That's a really misguided view, because a dedicated, skilled, and motivated attacker isn't going to just take that week or some portion of that week. If they're after something, they're going to dedicate themselves to it and really go after it. So just because you didn't find a penetration in some subset of a week doesn't mean that they are secure and invulnerable to attack. It just means that during the course of that particular week and other circumstances that were in place, you didn't get a penetration that was really significant or major. That's all it means. It doesn't mean anything beyond that. And if an organization walks away feeling like they're secure, then they're going to end up not fixing the real vulnerabilities that may be in place that could expose them to significant risk. So that's penetration testing and scope and security assessments. In this lesson, we're going to be going over footprinting. What is footprinting? Well, footprinting is getting an idea of the entire scope of your target. That means not just the scope that you were given, which may be an address block, or it may be a domain name, or it may be a set of address blocks. What you want to do is you want to figure out all of the information that's associated with that in as great detail as you can possibly get. So you want a list of domain names. And as you're going through this, you probably want some sort of database or Excel spreadsheet or something to keep track of all of the information, because you're going to have a lot of it at the end of the day. So you want to be able to find the information quickly. And so having some sort of either notepad going with your notes, or, as I said, a spreadsheet or a database if you can get organized in that way. But you want to keep all of those sorts of things down. So in this case, I want to do infiniteskills.com. I need network blocks. So far we've found one, and that's just a made-up IP address because I'm just putting information down. But I need network blocks. You may only have one IP address that you can find externally. You're going to want a whole range of internal blocks, and you can do a little bit of digging if you aren't provided those. You want specific IP addresses for critical systems, web server, email server, database if you can find it, those sorts of things. You want system architectures. Are they running Intel? Are they running Windows? Are they running Unix? What are they running? Access control lists. These are going to be hard to get, but you may be able to guess them, and you can guess those by doing port scans to see what sorts of responses you get and whether you get filters back or not. You want to know whether there's an IDS around somewhere. You want to do system enumeration. If you can get access to a system somehow, you want to know usernames, group names, and so on. You want system banners, routing tables, and SNMP information if you can get it. DNS host names, if you can get those. This is for both internal and external. On the inside, if you're doing an internal penetration test or ethical hacking engagement, you want to know networking protocols. Are they only using TCP/IP, or are they using IPX, SPX? Are they using DECnet, AppleTalk? Are they using some sort of split DNS? In other words, do they have an internal DNS server that's different from their external, and will it give different information? You want to check for remote access possibilities, VPN or dial-up. And yes, people still use dial-up. How about extranet? Do they have connections to other partner facilities? What are the connection points? What sorts of access control are they using? Is it public or private? In other words, are they doing some sort of VPN tunnel between the endpoints, or are they using just a private line to connect the two different endpoints? This is the type of information that you want to be gathering, and you don't have to gather it all up front. Some of it you need to gather up front so you can figure out what you're doing and where you're going to start. Some of it you're just going to gather as you go in order to have information so that you can continue, and also provide you some launching points for additional attacks or tests that you may be able to do. But this is definitely a starting point of the types of information that you need to have as you go about footprinting your target. This lesson will be going over the use of a couple of websites to do a little bit of historical digging about companies and the types of infrastructure that they may be using. This information, of course, is useful so that we can narrow down our focus in terms of what we want to target against them for attacks. Now, over time, we've improved our awareness about what sorts of information we may want to divulge. So several years ago, you may have gone to a company's website and discovered that you could get email addresses and names of people in positions that you may find relevant. There were all sorts of bits of information that could be used against the company, and over time we've discovered that Those sorts of pieces of information probably don't belong on a website where they can be used against a company, and so they have been pulled off. Now, it used to be also that Google had the ability to pull up information that it had cached. So, for example, if a website was no longer available or if it was temporarily offline, there was a little cached button that you could click when you did a Google search, and you could pull up that cached information. So even though the website wasn't available, you could still get the information from Google. Google's removed that, so we don't have that ability any longer. However, there is an Internet Archive that we can go to that will provide information about what websites looked like in years gone by. So I'm going to go to the Wayback Machine, which you can see is at archive.org, and I am going to infiniteskills.com, and we're going to take a historical look at the Infinite Skills website. You can see we've got some years where they've got information going back to 2008. They've done some archived captures. So let's go back to the very beginning. Looks like the first snapshot that they were able to take was in February of 2008. And we can see there it's just a username and password. So we go back, and let's try later in the year and see if things got any more interesting. So in December, it looks like they've posted some content, and the content looks much different than it does today. I can jump ahead a little bit to 2010, and you can see a number of snapshots that they gathered. Here's one in June that looks different than the one from 2 years previously, of course. So you can see that you could go back a couple of years and see what a website used to look like, and of course get the information that used to be there that isn't there any longer. So let's take a look at Microsoft.com here. Now you can see their website goes back to 1996, and we can pull that up. Their first snapshot was in October of 1996, and you can see what Microsoft's website looked like way back then. There's 2003. We can go back to 2000, and there's a number of snapshots here that we can take a look at. We happen to grab one on August 31st, 2000. So the Wayback Machine is really useful for getting some historical context on what websites used to look like, as well as the information that they used to have. Another really useful website is one that's called Netcraft. Now, Netcraft does internet research, including the types of web servers that companies run, and they have a web server survey. You can see here as we scroll down, Apache's web server has 64.3% of the internet market. Of course, that's followed by Microsoft with 13%. Interesting information, maybe useful information, but even more useful than that is looking at what different companies run for their websites. You can see here, Infinite Skills, date first seen was in November 2002, and we have a little bit of hosting history here. The IP address doesn't look like it's changed over the last couple of years, and they've been on a Linux platform running Apache 2.2.3. Looks like they're on Red Hat, and they've got some modules that have been installed on Apache as well. You can use this information to get more specific about the version of the web server that you're running, so you can maybe go look for vulnerabilities that are specific to that version and target your attack more closely against the company that you're doing your ethical hack on. So Netcraft and Wayback Machine, both really useful websites for gathering some historical data on companies, and in particular, the targets of your ethical hacking. In this lesson, we're going to be going over using resources. There's a variety of resources available on the web where you can do some reconnaissance on the target that you are engaged with. One good resource is Monster. Now, Monster, if you're not aware, is a job searching website. You may be wondering why we're going to go to job searching websites to research information about an engagement or a company that we are working with. Well, the reason for that is very often companies post information about the types of infrastructure that they have. So let me show you an example. We're just going to look for systems administrator. So I've got a lot of jobs back here. And if I look down through the listings, I can see some information about the types of systems that different companies are working with. So here's an example here. I happen to know that Cybercoders is a headhunter, so it's unlikely we'll find the company name here, but we can pop this open. You can see that they are looking for somebody who has experience with Windows, Cisco, Citrix, and healthcare. So it's a healthcare company. It's using Windows, and they're also using Cisco probably for their network hardware, and they are using Citrix for probably some sort of virtualization solution. So that's a lot of information that we now know about this company. And if you were to plug in a particular company as well as a job like systems administrator, you could turn up all sorts of information about the types of infrastructure that they are using. This is a company called Akibia, and they're looking for somebody who does Unix, Apache, and Tomcat. So there's another company that's provided information about the types of systems that they use. So again, you can see Monster is a very good resource for finding information about the types of systems and software that companies are using. And the reason for that is if you're looking to hire somebody, you're going to use a site like Monster, and you need to post the types of job requirements and the skills required. And so if you start looking around for a particular company and you look for the right jobs, you're going to be able to find out the types of systems and software that they are using in-house. Often, in addition to the Apply Here button, you may see an email address at the bottom, and sometimes it's something like HR or jobs or careers, but occasionally you'll see an actual recruiter's email address, and that can provide you some information about not only that user or that person, and you may be able to use that down the road in some sort of social engineering attack where you can pretend to be that person, where you have their name and also the position that they hold. You can also make some determinations probably about email addresses for other people in the company, and you may be able to use those as well. If you go to LinkedIn, you're going to find the same sort of thing where people who have previously worked at that company are going to list the types of experience that they have, and you may be able to figure out, again, the types of systems and infrastructure that that company is using. Facebook or other social networking mechanisms like Twitter, for example, you could do some searching for companies or users that you have found in other ways and see if you can find some information about things that they have posted about the things that they do at their job, the types of systems that they work with, or sometimes people will slip and post things like, we had a major outage because we were off on Apache. It's really not a good idea to do that sort of thing, but sometimes people make mistakes and they don't get caught. So there's all sorts of resources available on the web to find out the types of systems and software, as well as information about users and people within different companies, and you can use that to your advantage when you start looking to exploit vulnerabilities down the road. In this lesson, we're going to be going over the use of Whois, a utility that is used to query the various regional internet registries to store information about domain names and IP addresses, and there are 5 regional internet registries. First, there's ARIN, which is responsible for North America, so that would be the US and Canada. And then we have LACNIC, which is responsible for Latin America and portions of the Caribbean. RIPE, that's responsible for Europe, the Middle East, and Central Asia. AFRINIC, which is responsible for Africa. And finally, we have APNIC, which is responsible for the Asia-Pacific Rim. So that's the regional internet registries, and as I said, WHOIS is responsible for querying information from the various regional internet registries, and you can use WHOIS to get information about who owns a particular IP address. So, for example, I could do WHOIS, and I'm just going to make up an address here. And WHOIS tells me that actually belongs to IBM. You can find out pretty quickly who owns particular IP addresses and who's responsible for them. And from that information, you can get email addresses that belong to a particular company. This one has an email address for the tech contact of ipreg@us.ibm.com. So that's just doing a WHOIS query. I can specify which WHOIS registry I want to query. So different IP addresses and different information belong in the different regional internet registries, of course. So if I wanted to go to a particular database, I would use the -h flag. So I could do whois.aaron.net and remember the IP address. And I'm going to query that again. And of course, I get the same information back because I went to where it's actually stored. So I can query the regional internet registries directly using the -h flag, and the different registries, of course, would use whois.whatever for their WHOIS server. So in this case, it would be whois.aaron.net. So I can get information about domains as well. So I can query infiniteskills.com, and I can find out that this is Infinite Skills. There's an administrative contact and a technical contact, and you can see the different domain servers. So the servers that would have authoritative information about the DNS entries for that particular domain. You can also see other information like when the record was created for that particular domain. This goes back to 2007. Now, I could also find information where I may not know specifically what I'm looking for. So if I just did WHOIS foo, I would get a whole lot of systems and domain names that existed with that particular string in it. So you can see it actually aborted after 50 records were found because there's a lot of different systems out there that have foo as part of the name of the system. So the regional registries, in addition to storing information about IP addresses and domain names, sometimes will store information about particular host names. And there may be other reasons why you would store a host name or particular information about a host name or a system name within one of the RIRs. Now, if I wanted to look up something specifically once I had found that, I could now do a lookup on whoisfoo.bar. And it says we don't actually know what that is. Not surprising. I could also do something like this where I'd get more detailed information about all of the things that it turned up. So if I did a WHOIS equals foo, I've got all of these bits of information. So here, for example, is foo.net. The registrar is Network Solutions. And I've got a couple of name servers here and the creation date and the expiration date. Same thing here with foo.com. So I could scroll up and find more detailed information about the 50 specific things, just in case you wanted to get more information to figure out which entity you were actually looking for. You could use the equals and help you narrow down what you were really looking for. So I'm using WHOIS as a command line utility here. There are other ways of accessing WHOIS, and this command line utility is available on Unix-like operating systems. Right now, though, I'm going to show you a web interface at geektools.com, and GeekTools has a handful of tools that are useful for system administrator kind of uses, and in this case, for our ethical hacking uses. So I'm going to go to the Whois site. They've got a little CAPTCHA thing there. And now I'm going to say I want to look up infiniteskills.com. And it's the same thing as I had before. It's just I've got a web interface. So you could do this from like your phone or a tablet or some other device where you may not have command line access. As long as you've got a web browser, you can look up all of this information. Now, if you're running on Windows and you like the command line access for maybe programmatic reasons, you want to script a bunch of things or something like that, or you just like typing, there is a Whois utility for Windows. So if you go to Windows sysinternals, you can download it. So it provides the same functionality as the one that you can get on Unix-like systems. So that's information about how you would look up details about maybe your target and get more information about them using Whois. In this lesson, we're going to be talking about using DNS to extract information. DNS is the domain name service, and the domain name service exists because it's easier to remember things that look more like words than it is to remember a series of numbers. So nobody's going to walk around remembering IP addresses, so we have to have mnemonics, which means we have to have ways of referring to systems and hosts and servers on the internet without referring to them by their IP address. So we need to use something called the domain name system, or DNS, in order to do that translation from hostname to IP address and from IP address to hostname. So I'm going to show you a few different ways to extract information from DNS. The first little utility I'm going to show you runs on just about all systems that run TCP/IP. It certainly runs on Windows and Unix. It's called NSLookup. So I'm in Windows here. I'm going to run NSLookup, and you can see I've started up, and it's telling me what my DNS server is. As a default, I can actually change that, and I'm going to change that to 4.2.2.1. And now I can just type in a host name here, and it's telling me that this host name, www.infiniteskills.com, is actually an alias for infiniteskills.com, and that has the address 76.12.59.46. Something else I can do with NSLookup is look up different types of records in DNS. In DNS, there are several different types of records. One of them happens to be the A record, which is what I just looked up here. So the A record translates a host name to an IP address. A pointer record, or PTR record, does the reverse, which is IP address to host name. I can also do MX, which is the mail exchanger record. That's another type that I can look up. So I can look up the mail exchanger records for the domain infiniteskills.com, and you can see here I've got several MX records with different preferences, and the preference indicates the hierarchical order in which these different mail exchangers should be used. I can also do set type equals SOA, and if I type infinite skills again, I get the start of authority record. So I've got the primary name server, the responsible mail address, the serial number, the refresh rate, retry, expire, and the default time to live. So that's all information about the domain Infinite Skills, and that's all stored in a record called the SOA record, or the start of authority record. Now, another tool that you can use is more of a Unix thing, and that's something called host, where I can just do infiniteskills.com. And host will just do a very quick and simple lookup without a lot of frills and without a lot of extraneous information or a lot of other stuff that you've got to read through. It says here that www.infiniteskills.com is an alias for infiniteskills.com, shows me the IP address, and because it's a reference to the domain name as host name, it also gives me the mail exchanger records. So that's the host command, and as I said, that runs on Unix. I could do host 4.2.2.1, and that will do a reverse lookup as well. So I can look up things very quickly with host. Now, there's another tool that I can use if I want to get into a lot of detail. I can use dig, and I can dig infiniteskills.com. And that tells me that infiniteskills.com has an IP address, and it actually tells you the record type that it's got. You see in A there, tells me it's an A record, and that's 76.12.59.46. It also gives me information about how long the query took in the server that it used to do that. So I could change the server that I'm going to and do the same query. And you can see I did a dig at 4.2.2.1. That tells dig that I want to use that IP address as my server. When it goes and does the query, it should query that server rather than the default server. So it went out to 4.2.2.1 and queried for that particular piece of information. And you can see at the bottom again, I've got the server and how long it took. In this case, it took 50 milliseconds, and the message size was 52 bytes. Same thing here as with NSLOOKUP. I could do dig MX, and that's going to give me the MX record. I can do dig SOA. I could do dig SRV. So I can look up any of the record types using dig. Dig has a lot of information about the question, the authority, which server it's using, how long it took, and the message size that it came back with. I could do a dig PTR 174.118.14.72. It tells me that particular address doesn't actually have a host name attached to it. It does tell me the root server that it went to in order to look up that particular information. It's got some information about the start of authority record for that particular server. Now, something else I can do with dig, and this doesn't work as often as it used to in the past. Used to be you could list servers from the domain. So if I were to use NSLOOKUP, like I could do ls, and that would list the servers for a particular domain. I could dump the entire DNS table. Most people don't allow things called domain transfers, but it's often worthwhile just to give it a try. What I would do would be dig AXFR, which means I want to do a transfer of A records, and it's basically going to list the host names if it works. In this case, it's not going to work because they don't allow transfers. You can see transfer failed, but since it's such a quick little test, it's worthwhile doing the dig AXFR just to see if you can get the list of domain names and see whether you can get that list and provide some jumping off points for places that you can go looking. So that's information about how to use DNS and the various DNS related tools to extract information about your target. In this lesson, we're going to be going over how to find network ranges. So you've got an engagement that you're working on, and you only know the domain name, and you don't know much beyond that, and you're expected to figure out where everything is and what everything is. So how do you go about doing that? Well, you use some of the tools that we either have been talking about or will soon be talking about in more detail. And the first thing I'm going to do is I'm going to use the domain name infiniteskills.com, and I'm going to look up Infinite Skills, and I've got an IP address back here. So that's just an IP address. I don't know who that IP address belongs to, and I also don't know how big the network range or network block is that's associated with that. So I'm going to do a whois, and I'm going to look up with Aaron, who owns that IP address. And I can see it's owned by Host My Site, and the network block or network range is 76.12.0.0 all the way through 76.12.255.255. Host My Site, I am going to guess, is a hosting provider. It would be out of scope to look at any of those other addresses unless I can find some evidence that Infinite Skills has a presence on a different address than the one I have located by looking up that particular host name. So I've got one address here that I can look at. Let's take a look at the website, because that may be a different address. www.infiniteskills.com is an alias for infiniteskills.com, which I've already looked up. What I'm seeing here is all the mail that's being handled. If I didn't have that, I could do digmx infiniteskills.com, and I could get back all of the mail handlers. In this case, their mail is being handled by Google. If it weren't being handled by Google, let's say this was a different address, I could do a host here and get the IP address back. Now I've got an IP address, and now I'm going to do a whois again, and it's going to tell me that that's Google. Not particularly surprising. The other thing you can do is to check for different host names. Since I'm assuming DNS probably doesn't allow zone transfers, since most DNS servers don't anymore, although they used to, you may have to start guessing. So I could do something like host webmail.infiniteskills.com. And this is completely guessing, and it may not actually return something. In this case, it doesn't. I could also guess something like vpn.infiniteskills.com. And I've got nothing there. But you could keep going, remote, mail, any other different type of host name that you can think of that may be serving up some additional content. Any host name that you may be able to run across using a Google search. You find the IP address, you figure out who it belongs to, and you just keep going, and you start narrowing down the field of what IP addresses belong to what entities and what IP addresses are relevant to the one that you are working on. The other thing that you can do sometimes is, if I did a whois infiniteskills.com, sometimes what you will get in contact information, you may find that their email address refers to a different domain name, and you can use the same techniques that I've just demonstrated here against that domain name in order to figure out whether it's related to the target that you've been given. And if it is, you start chugging away with finding all of the information that you can about that. So you're going to want to use a lot of DNS information to look for these network ranges. You also are going to need to use the whois databases and the internet registries. A lot of it takes a lot of guesswork and just making inferences. So if you see something that looks like it may be related, start looking it up and chasing down the lead and see where it goes. This can be a time-consuming task, but you want to make sure that you get all of the targets that you can if you haven't been provided them. And again, you always want to make sure that you have the scope clearly in mind and clearly agreed to. Even if they don't give you a set of information that they want you to track down, IP addresses or domain names, they should always give you exclusions if they've got any. So that's how you would go about looking for network ranges for particular engagements. This lesson will be talking about Google hacking. And no, I'm not talking about breaking into Google to steal information. I'm talking about making use of specific keywords that Google uses to get the most out of the queries that you submit. So, for example, a pretty basic one is the use of quotations. You quote things in order to use specific phrases, otherwise Google will find pages that have instances of all of those words rather than the words specifically together in a particular order. So I'm going to pull this query up, and this should show a list of sites that have pages where there's a directory listing allowed on the website. And here you see index of /, which is what I use. That's a directory listing for Ubuntu. We can also use another simple one. The plus sign says you have to find this word in your query. It's critical. And here's a list of different sites that have this particular set of words in it. So index of /, and we want to make sure we get the PASSWD or password file. Google has defined a number of keywords, for example, this one, And that gives us a set of answers that has a file type config in it. So you can see the second one down, web.config, and the third one down, web.config. So the file type is config there. We can also use a query that looks for a set of words just in the title. So I'm going to look for sensitive in the title. And you can see a number of responses here. Another thing I can use is file type. As we did above, I can add that into this one. And I want to look for Word documents where the title says sensitive. And here's a set of responses for that. You can see the doc indicator on the Google response that we found some Word documents. I can look for cite. And you can see here, the first one, other than the definition, is a PDF that's a questionnaire for non-sensitive positions, and that's in the Navy, so ncis.navy.mil, because we looked for mil as the site. And you can get more specific than that. We can also look for keywords in the URL. I want to look for www.root, which is a pretty common directory, and we've found a handful of responses here. So that's all in the URL, which would be the address that's in the address bar up above. I can look for in title, which is slightly different from all in title. And I can look for ext, which is similar to the file type. We're looking for file extensions. We could use ext.js, which would be a JavaScript file. And you can see a number of JavaScript files here that come up in response. And another one we can use, this one is maybe a little bit more obvious. What this says is we're looking for the words in this query in the text of the page. So that's a number of keywords that you can use to look for information in Google and find some very specific responses. In this lesson, we'll be going into some more detail about the various things you can find using Google hacking techniques. While Google hacking techniques are really useful for just general searching in Google, they're also really useful for penetration testers or ethical hackers. You can narrow down information that you get from Google so you get a specific list of systems that may be vulnerable. So we can do things like look for error pages. If I do in title error, I'm going to get a whole bunch of information here, various documentation pages about different vendors and the errors that they support. So here's one, for example, at docs.oracle.com about a Java error. But if you know something more specific, we may be able to get errors here about MySQL. And again, you're going to get a lot of forums and documentation pages unless you do something like -forum or -manual. And the minus says, leave these things out of my responses that you show me. So we can get into a lot of detail here about the types of things that we're looking for, and it can take a lot of work to actually get the specific pages that you're looking for after you've narrowed down all of the extraneous information from things like documentation and forums and discussions and that sort of thing. We can look for things like version numbers. For example, you may be able to get Apache servers that are running some version of 2. And again, we're getting a lot of documentation pages, and we can narrow down that focus a little bit more with various other queries. Sometimes you can get information about people's systems. We're going to look for directory listings, which is why I look for index of. And I'm going to look for a bash history file. And bash history will show a list of commands that somebody has been running. So here's a page right here, and here's the bash history. So we can look at another page here, and you can see there's a number of them where people have given their file listings to their web server and made them available for whatever reason. Sometimes they don't realize they're doing it. Sometimes it's for specific purposes. but you can get all sorts of information about things that people may not actually want you to see. We can also look for things like specific servers. So we can look for powered by shout stats. And then we're going to look for the words hourly and daily, and that will give us pages where statistics from Shoutcast servers are available. And we may want to do something like drop off Google so that we avoid places where it references Google hacking. So here's a page right here for a Shoutcast server. And we've got a particular server that's available. You can see it's at this address here. We can also look for things like outdated web servers. So I'm looking for Microsoft IIS 5.0, and you see the server at. I want to find this particular phrase because it's going to indicate something that the server generated with its version number, and there will be an IP address or a host name after the server at piece. And again, we get the Google things, so we can drop those off. And here's an example. It's actually an index page, and there's the server that it's available at. So there's a system running a very old version of Microsoft IIS. You can also look for things like specific web applications and vulnerable data in those web applications. In this case, I'm going to look for information about Joomla, which is a web application, and I'm going to look for an index page with a file listing that says joomla1.txt, index of / right off the bat. Here's a couple of them actually. And you can see this particular file has a lot of information in it, variables, and probably there's a lot of details about maybe passwords and host names on the system. So as you can see, using Google hacking, we can turn up all sorts of information in a very targeted way. This lesson will be talking about the Google hacking database. Several years ago, a guy by the name of Johnny Long put this Google hacking database together to begin to compile a list of searches that would bring up interesting information. Johnny has also written a couple of books on Google hacking. So we're at the Google hacking database website here, and you can see them talk about Google Dorks, and there is a list here of the latest Google hacking entries. And they also have a number of categories that you can look through to find some specific things that you may be interested in. Of course, you can also search specific information that you may be looking for with regards to a specific product, for example, like here's one on Joomla. There's also information about files containing usernames. This is always interesting. You don't necessarily get the passwords here, but a username can sometimes get you a foothold into some password cracking attempts. You can do some brute force checking, and you can see here it talks about the type of search it is and what it reveals, and you can just click here on the Google search and it will actually bring up Google with the list of responses that Google generates. So let's look at this one here. The file type is log, and the username is putty, and this is information about an SSH client, and let's see what we can bring up here. So here's a putty log. You can see they're using username ec2-user, so they're logging into an Amazon Linux system, which it says right here in the middle, although EC2 is the product that Amazon uses for some of their cloud computing. And if we continue to scroll down, there's a lot of interesting information in here. So somehow somebody's got a putty log that has logged a lot of information, and they've just got it up on a website. So looking through a little bit more, we can see a number of other things. There's vulnerable servers, which can bring up interesting information about specific server types. Here's one here, find servers vulnerable to the CVE 2007-5423 exploit. So you can find servers that are vulnerable to specific exploits. If you were looking to see if your client, for example, may have a server that's vulnerable, you may want to do that type of search. Error messages are really interesting. They often provide, as this says here, way too much information. And let's just bring up one of these searches just for fun. We're going to look for some PHP data. And as we've mentioned before, sometimes you're not going to always get everything that's a hit. Sometimes it requires a little bit more. And we have some information on this website. There's a warning about this particular PHP page. And we've also got information here about a directory and a path on the system that may provide us some information. There are a number of other categories here. Files containing passwords, files containing juicy information, network or vulnerability data. Various online devices are interesting because you may end up being able to find things like cameras, or in this case, here's a Beyond TV. You can get surveillance video, more or less what this one here is, Spectra IV IP. And here's a website that's got a camera. And in this case, it's taking some time for the video to load, or there may be a problem with the QuickTime stream. I can, however, take a snapshot and then open it up. And there's the snapshot, so you can see that the video is actually working. So a number of categories that they've classified things into: advisories and vulnerabilities, pages containing login portals. But what this really has is a list of queries that you may be able to use as you're going through a penetration test. So the Google Hacking Database, definitely a website to put into your bookmarks and check in with on a regular basis as you're working with your clients and doing ethical hacking and penetration testing. In this lesson, we're going to be talking about the history of TCP/IP, the network that eventually morphed into the thing that we now call the Internet. Began in 1969, and it spun out of this government organization called ARPA, which was the Advanced Research Projects Agency. They had an idea to create a computer network that was resilient to certain types of military attacks. And the idea was to have this network that would survive certain types of war and warlike conditions. So ARPA sent out this request for proposals, and BBN, which is Bolt, Beranek, and Newman, and they were previously an acoustical consulting company. They won the contract to build what was called the ARPANET. The first connection was in 1969. So that's where we get the idea that the Internet began in 1969. The Internet, as we call it now, didn't really begin in 1969, but the ARPANET did, and the ARPANET has a long history that goes through the NSF net in the 1980s after the ARPANET was sort of decommissioned, and a lot of other networks were folded into this thing called the NSF net that then turned into what we now call the Internet once a lot of other networks were connected into it. First protocols on the ARPANET. Initially, there was the 1822 protocol, which was the very first protocol defining communications on the ARPANET, and it was called the 1822 protocol because of BBN Report 1822, which described how it worked. Shortly after that, there was this thing called the Network Control Program. And the Network Control Program consisted of ARPANET host-to-host protocol and an initial connection protocol. Now, there's certainly not a direct correlation or analogy here, but if you want to think about it in a particular way, you could say that the ARPANET host-to-host protocol is kind of like UDP, and the initial connection protocol is kind of like TCP. So the host-to-host protocol provided a unidirectional flow-controlled stream between hosts, which sounds a little bit like UDP. and the ICP provided a bidirectional pair of streams between two hosts. Again, these aren't perfect analogies, but the host-to-host protocol is a little bit like UDP, and the ICP is a little bit like TCP. Now, the first router was called an interface message processor, and that was developed by BBN. It was actually a ruggedized Honeywell computer that had special interfaces and software. So the first router wasn't a ground-up built piece of hardware. It was actually an existing piece of hardware that was specially purposed for this particular application. So Honeywell had this computer that they made, and BBN took that and made some special hardware interfaces and wrote some special software that allowed it to turn into this interface message processor, which passed messages over the ARPANET from one location to another. So where did IP come in here? Well, in 1973, a guy by the name of Vint Cerf and another guy by the name of Robert Kahn took the ideas of the NCP and what the ARPANET was doing, and they tried to come up with some concepts that would work for the needs that the ARPANET had. So by 1974, they had published a paper that was published by the IEEE, and they proposed some new protocols. They originally proposed a central protocol called TCP. Later on, TCP was broken into TCP and IP to get away from the monolithic concept that TCP was originally. So they broke it into more modular protocols, and thus we get TCP and IP. So how do we get to version 4? Since that's kind of where we are right now. Version 6 is coming and has been coming for many, many years now, but we're still kind of at version 4. So how did we get there? Between 1977 and 79, we went through version 0 to 3. And by 1979, 1980, we started using version 4. That eventually became the de facto protocol on the internet in 1983. When NCP was finally shut down because all of the hosts on the ARPANET were using TCP/IP by that point. In 1992, work began on IP Next Generation, and for a long time, all of the specifications in the RFCs talked about IPNG. Eventually, IPNG became known as IPv6. You may be wondering where IPv5 went. Well, it was a specially purposed protocol that had to do with streaming, and certainly not a widespread thing. What are the differences between IPv6 and IPv4? Well, IPv6 has 128-bit addresses, which gives us the ability to have some ridiculously large number of devices that have their own unique IP address. IPv4, by comparison, has only 32-bit addresses, and as you've probably heard, we're well on our way to exhausting the number of IP addresses that are available, and we've done a lot of things over the years to conserve address space and reuse address space, and so we continue extending the point at which we just truly run out of IPv4 addresses. Another thing about IPv6 is it attempted to fix some of the inherent issues in IP. And some of those has to do with security concerns, and there are certainly a number of flaws in IPv4. And when they started working on the IP Next Generation or IPv6, they tried to address some of those concerns and some of those issues. And they may not have done it perfectly, but it was certainly an attempt, and IPv6 attempted to fix some of the issues that were inherent in IP. So that's a history of TCP/IP. In this lesson, we'll be talking about a utility called Wireshark. Now, Wireshark is a packet capture utility, meaning that it grabs data that's either going out or coming in off a specific network interface, and there are a number of reasons why this may be useful or important. One of the reasons why it's really important is what's going on in the network is always accurate. In other words, you can't mess around with things once they're on the network, or you can't lie about something that's actually on the network as compared with applications in their logs, which can be misleading or inaccurate, or if an attacker gets into an application, they may be able to alter the logging behavior or several other behaviors that make it difficult to see what's really going on. In the network, you can really see what's going on. Once it hits the wire, it's on the wire, and you can't change the fact that it's on the wire once it hits it. So what we're going to do here is a quick packet capture and show some of the important features of Wireshark so that we can use it later on when we're starting to do some more significant work. I selected the interface that I'm using primarily. I'm going to go over here and we'll bring up a Google page just so we can see what's happening on the network. I'm going to go back here and it's grabbing a whole bunch of stuff off the network. I'm just going to stop that and we're going to go back and take a look at some of the messages here and some of the features of Wireshark. Now you can see in the top part of the screen here, there's a window that says number, time, source, destination, protocol length, and info. Those are all of the packets that have been captured, and they're numbered starting from 1, and the time has to do with being relative to the point that we started capturing. You'll see the source and destination addresses here, the protocol, the length of the packet in bytes, and some information about the packet. The bottom of the screen you'll see has detailed information about the packet that has been selected. So I'm going to select one here. And we're going to see at the bottom of the screen here, or in the middle frame, it says frame 290. That means that's the 290th packet that was captured. It's 66 bytes, and we grabbed 66 bytes of it, 528 bits. Tells you what the source and destination MAC address is, or the layer 2 address. And then you can see the IP addresses, both source and destination. And it says it's a TCP packet, and it gives us the source port and the destination port. We can start drilling down into different bits of the packet, and you can see when I select a particular section of the packet down at the very bottom, you can see what's actually a hex dump of the packet, and on the right-hand side is the ASCII equivalent of that hex dump, and it tells you the actual byte level details of what's in the packet there. The nice thing about Wireshark is it really pulls the packet into its different layers, and we'll talk about the different layers a little bit later on in another movie. But packets are put into different layers, and there's a couple of different models that we can talk about with that. But what Wireshark does really nicely is it demonstrates those layers for us. As we can see here, there's actually 4 layers in this particular packet here. We can also do some filtering. So I've got a Google web request. So what I want to do here is I want to filter based on HTTP. So I filter HTTP, and now I've got just the HTTP and HTTP related protocols here. I can select one here where I see here it says get text input assistant, and it's going to get an image that's a PNG image. This is a request to get the icon that's going to be displayed in the address bar in the web browser. It's favicon.ico. What I can do here is I can select Analyze and follow TCP stream, and you can see all of the requests related to this particular request, and it breaks them down very nicely into what they would look like, just a text form here. That's all of the messages related to getting that one image. So that follow TCP stream or follow conversation is a really useful way of pulling related packets together so that you can follow them clearly and easily without having to look through all of the packets here and try to figure out which ones you think may be related, which ones may not be related. And you can see here that Wireshark has created a filter for us. It says tcp.stream equals 12. So Wireshark has flagged that stream with the number 12, and it's done a filter for us. And now all of the packets that show up in this window are only packets related to this particular stream. And that's some details about Wireshark. We'll get into more specifics and more digging deeper into Wireshark in subsequent movies. In this lesson, we'll be talking about the OSI and TCP IP models for network protocols and network stacks. OSI stands for Open Systems Interconnect, and in the late 1970s, they started working on a model for how a network stack and network protocols would look. Originally, the intent was to develop the model and then develop the protocols that went with it. What ended up happening was, after they developed the model, TCP/IP started really taking off, and the TCP/IP model that went along with it matched better what was going on with TCP/IP, which became the predominant protocol, and as a result, the OSI protocols never actually got developed. However, we still use the OSI model for a teaching tool as well as a way of describing what's going on within a network stack and in networked applications. You'll often hear people talking about the different layers, like that's a layer 2 problem, or we're in layer 3 space now. Continuing through these lessons, I'll refer occasionally to the different layers, and when I do that, I'm referring to the OSI model. So let's take a look at the OSI model. Starting from the bottom, we have the physical layer, which is where all of the physical stuff lives, the wires and cables and network interfaces and hubs and repeaters and switches and that sort of thing. Sitting above that is the data link layer, and that's where the Ethernet protocol, ATM protocol, frame relay, those sorts of things live. Now, I mentioned the switch below. Physically, the switch lives at layer 1, but it operates at layer 2. And the reason it operates at layer 2 is because it looks at the data link addresses, the layer 2 or physical address. And that's not to be confused with the physical layer. It does get a little mixed up sometimes. We refer to the MAC address on a system as the physical address because it lives on the physical interface and is bound physically to that interface. However, that MAC address or media access control address lives at layer 2 at the data link layer. The network layer, which is right above that at layer 3, that's where IP lives, as well as ICMP and IPX from the IPX-SPX suite of protocols from Novell. Routers operate at layer 3. Layer 4 above that is the transport layer. That's TCP, UDP, and SPX, again from the IPX-SPX suite of protocols. Above that is the session layer, that's layer 5, and that's AppleTalk and SSH as well as several other protocols. At the presentation layer, which is layer 6, you'll often see people refer to something like JPEG or MPEG as examples of protocols that live at that layer. Those are presentation layer protocols. And finally, we have layer 7, which is the application layer, and that's HTTP, FTP, SMTP, similar application protocols whose responsibility is to deliver end-user functionality. So that's the OSI model, and that's the 7 layers of the OSI model. There's some important things to note here. You'll see on the left-hand side there's some arrows, and what those suggest is when we are putting packets out onto the wire, the packet gets built from the top of the stack down, which is why it's called a stack. Each layer sits on top of the other. The application layer is responsible for beginning the process, and then that follows through the presentation session and transport layers and down through the network data link until we finally drop it on the wire at the physical layer. When it's received from the network, it goes from the bottom up. We receive it on the physical, it gets handled by the data link, then the network, transport, and so on. When going down or up, what we're dealing with is an encapsulation process. So at every layer on the way down, the different layers add bits of information to the datagram or the packet so that when it gets to the other side, each layer knows where its demarcation point is. And while it may seem obvious, each layer talks to the same layer on the other side. So when we drop a packet out onto the wire, the physical layer talks to the physical layer. In other words, the electrical bits that gets transmitted by the network interface on the first system are received on the second system. On the second system, the layer 2 headers that were put on by the first system get removed and handled as necessary. Same thing at the network layer. It's the network layer that puts on the IP headers, and it's the network layer that removes the IP headers and determines what to do from there, and so on. So again, while it may seem obvious, it's an important distinction to recognize that each layer talks to each layer. And when you're building a packet, you go down through the stack, and when you're receiving, you come up through the stack. And again, it's called a stack because we keep pushing things onto the top of the packet and they get popped off on the other side. So the OSI model. Let's move on to the TCP/IP model, which is on the right-hand side, and you'll notice that there's a really big difference here. That being that there are only 4 layers in the TCP/IP model as compared with the 7 layers of the OSI model. We have the network access layer, the internet layer, the transport layer, and the application layer. The functionality that the stack provides is the same. In other words, you're not going to get less functionality out of the TCP/IP model. It's just they've changed where different functionality resides and where the demarcation point between the different layers is. So there are only 4 layers in the TCP/IP model, which means that a couple of the layers have taken in functions from some of the OSI model. And we can get into that right here. The differences between the models at the network access layer in the TCP/IP model, that consists of the physical and the data link layer from the OSI model. So on the right here, you see the network access layer, and that takes into account the physical and data link layers from the OSI model on the left-hand side. Similarly, the application layer from the TCP/IP model encompasses the session, presentation, and application layers from the OSI model. So on the right, the very top box, the application layer, encompasses the session, presentation, and application layers on the left-hand side. And that, of course, leaves the transport layer to be the same, and in the OSI model, they call it the network layer. In the TCP/IP model, it's called the internet layer. Same sort of thing. That's where IP lives. And even though it's called the internet layer as compared to the network layer, it's the same sort of functionality. So those are the really big differences between the OSI and the TCP/IP model. Anytime I refer to layers through the course of the rest of these videos, I'm going to be referring to the OSI model, in part because it makes it easier to differentiate the different functionality. If I were to say the layer 1 function in the TCP/IP model, you wouldn't necessarily know if I was talking about a physical thing or a data link thing. Since there's more granularity in the OSI model, it's better to talk about the functionality in terms of the layers in the OSI model. And that's the 2 predominant models, the OSI model and the TCP/IP model, for network stacks and network protocols and applications. So talking about how an IP address is put together. We've got an IP address of 192.168.1.24. You can see there are 4 sections here. Each one is separated by a dot. And each section is a value that's represented by 8 bits or stored as 8 bits. And because of that, we can have values from 0 to 255 in each place there. So the 192 place, the first octet that you see, that number can be a value from 0 to 255 because that's what you can represent with 8 bits. Since 2 to the 8 is 256, and we have to go starting from 0, so the case where there are all zeros in the 8 bits, you can get values from 0 to 255 in each position, and that gives us 256 values. So each bit position out of the 8 can be a 0 or a 1. And as I said, we can get 2 to the 8 values out of each of the positions in an IP address. So each of those sections there can be from 0 to 255. So that's an IP address. Now, another important component that goes along with the IP address is the subnet mask. A pretty common subnet mask that you'll see is the one represented here, 255.255.255.0. Now, why do we need a subnet mask? Well, we need a subnet mask because the subnet mask tells us which portion of the IP address is the network portion and which part is the host portion. And again, the same thing applies here as with the IP address. Each position there is an 8-bit value, and so you can have values from 0 to 255. In this case, you'll see all of the bits are set in the first 3 octets. So there's all ones, and that gives us 255 in each of those first 3 positions. So let's look at an IP address again. 192.168.1.24. If we've got a subnet mask of 255.255.255.0, which portion of that IP address is for the network and which part is for the host? Since all of the bits are set in the first 3 octets, that means all of those positions, all 3 octets there, are for the network. That leaves the 4th octet for the host. Now, when it comes to the host portion of the IP address, for every subnet, you have a network address, which is the bottom of the subnet, the very lowest address in the host for that particular network. And the broadcast address is the very highest value in the host for that subnet. So in this case, .0 would be our network address and .255 would be our broadcast address. So in this particular subnet that we're talking about here with a subnet mask of 255.255.255.0, we've got 0 as the network, 255 as the broadcast. That leaves us .1 through .254 available for hosts. So we can have 254 host addresses in this particular subnet. In this lesson, we'll be going over UDP, which is a protocol in the TCP/IP suite of protocols. IP is the network layer, and that's the network layer in the OSI 7-layer reference model. The IP network layer carries the IP address, and that has information about how to get packets to its destination. The transport layer sits on top of the network layer, and that carries information about how to differentiate networked applications. That information about how those networked applications gets differentiated is in the form of ports. So the transport layer has ports, and the network layer has, in this case, an IP address. UDP is a transport layer protocol, and UDP stands for User Datagram Protocol. It's often called connectionless or sometimes unreliable. Now, unreliable doesn't mean that you can't trust it at all. It doesn't mean that it's not worth anything. It just means that there's nothing in the protocol that says that it's going to guarantee that the datagrams that you sent are going to get there. So datagrams are sent out on the network with nothing in the protocol at all as a form of safety net. If you wanted to use UDP and you needed that type of safety net, you would have to write it into your application. So UDP is a fast protocol. That's one of the reasons why it's good. It's also one of the reasons why it's unreliable. In order to get that speed, you don't have all of the error checking and validation that messages are getting there. So because it's fast, it's good for things like games and for real-time voice and video. Anything where speed is important, you would use UDP. So right here I've got a packet capture that I took, and I'm going to narrow down my focus here in Wireshark by applying a filter that just says UDP. And now I've got a list of all of the UDP packets that were taken during this capture. I'm going to take a look at just one of these packets here. I've got a UDP packet that originated from my system. We're going to ignore the lower level headers here, the part that says frame and Ethernet 2 and Internet Protocol version 4, and we're going to focus on the user datagram protocol portion of the packet. As I expand that UDP part of the packet, I don't see an awful lot of information here. What I see is just a source port and a destination port and a length, and there's also a checksum. So UDP doesn't come with an awful lot of headers because it doesn't need any. The only thing it needs is to tell you how to get to the application on the receiving host, and that's with the destination port. Now, once the message gets to the destination needs to know how to communicate back to the originator, and that would be through the use of the source port. A return message would convert the source port to a destination port and send back to that port in order to communicate with the originator. So we have a source port and a destination port. The length is a minimal amount of checking to make sure that if the packet that you received is different from the length that's specified in the UDP header, then there may have been something wrong and you may want to discard the message. The checksum also makes sure that nothing in the middle was tampered with, although if there's some sort of man-in-the-middle attack or something like that, a checksum is pretty easy to manufacture after you've altered the packet. So you can see here in the messages that there's a number of UDP packets. Some of them just say UDP. The one I'm looking at here happens to be from the Skype application talking to Skype servers. And we've also got DNS. Now, DNS also needs some fast response times because you don't want to spend a lot of time looking up information about the servers that you're going to before you just go to them. So DNS servers throw out their queries onto the wire using UDP, hoping to get fast responses. They don't want to spend a lot of time setting up connections and doing all of the negotiating that comes with a protocol like TCP, for example. So you see here that DNS is using UDP, and what we've got here is another UDP packet, source port. Destination port is the DNS port or domain port, which is 53. And at the bottom of Wireshark here, you see the domain name system query. If we open up the queries section down below, we're looking for a type A record, which means I need the IP address or just the address of the hostname con.skype.com. So that's some information about the user datagram protocol or UDP. In this lesson, we'll be talking about TCP. TCP is the Transmission Control Protocol. It's part of the TCP/IP suite of protocols, and it's a transport protocol. That means that it sits above IP, or the Internet Protocol, on the OSI model. IP, as you may know, is at the network layer, and the transport protocols sit on top of the network layer. Like UDP, TCP uses ports to differentiate networked applications. Unlike UDP, however, TCP is connection-oriented. TCP uses a three-way handshake in order to establish a connection between a sender and a recipient. In part, this connection establishment ensures reliability, and it does that by making sure that the two parties can hear each other and that they're talking the same language. In the real world, that might look something like two people meeting in a street, and the first person says hi, and the second person says, "Hi, how are you?" And the first person replies with, "I'm great." So what you get there is the first person saying something, the second person hearing that and acknowledging it with a response. The first person then knows that what they originally said was heard, understood, and received a reply. So the three-way handshake in TCP looks like this. And I've got a Wireshark capture up of some traffic that was on my network earlier. Right here, I've got a SYN message, which is the original hi. So that's the opening of the three-way handshake. We send a synchronized message. And if I look down here in the flags for the TCP header, I see that the SYN flag is set. In order to ensure that the SYN message was heard, the second party sends back a SYN ACK, or a synchronized acknowledgement. So if I go to that message in my Wireshark capture, I see that the flags ACK and SYN, or acknowledgement and SYN, are both set here. So that's the "Hi, how are you?" Now we just need to make sure that we get a message back from the recipient back to the original sender, and that's this message here. That's the ACK, or the acknowledgement. So no other flags, just the acknowledgement flag. So with that ACK message, we know that the first person or computer can send a message to the second computer. The second computer can receive that message and reply to it, and the first computer can receive and understand that reply. And because of that, they know that there's a reliable connection between them, and so we have a full connection up. So from a reliability standpoint, we ensure that the recipient is there and responding, and for the recipient, it ensures that the sender is still there after the original message was sent. Without that acknowledgement back from the sender, what you can end up with is half-open connections. You'll hear these mentioned sometimes. They're called SYN floods, and what happens is you can send a SYN message, and the receiving computer will open up a piece of memory called a buffer in order to hold open that half-open connection, waiting for the three-way handshake to complete, at which point it has a full connection. Now, for every computer, there is a limited number of connections that it can handle at any given point, memory not being an unlimited quantity. So if I keep sending a lot of SYN messages and never finish the three-way connection, I can start filling up the buffers on the receiving computer, and that's exactly what happens with a SYN flood, is the buffers in the kernel space memory begin to fill up, and it no longer has the ability to receive legitimate messages. So this is one of the downsides of having a reliable connection. You have to go through this three-way handshake, and because of that, you end up with the possibility of a denial of service where your memory buffers are exhausted by somebody sending a whole lot of synchronized messages or SYN messages. So let's take a look at some of the other headers that come along with TCP. And since we've got the flags section open here, let's just look at the flags. We've got an echo flag, an urgent flag, acknowledgement, push, reset, SYN, and FIN. For the most part, the ones that you're going to see used are the acknowledgement, the reset, the SYN, and the FIN. And we've looked at the acknowledgement and the SYN. The reset is used to reset a connection. So, for example, if I were to send a SYN message to port 83 and port 83 wasn't open, the receiving computer would send back a reset to me to indicate that port 83 was not open. The other flag that you'll see pretty regularly is the FIN flag, and the FIN flag is used to tear down connections, so it's kind of the opposite of the SYN flag. Now, unlike the three-way handshake that's used to set up a connection, a teardown is actually 4 messages. So what happens is both sides originate a teardown. So both sides will send out a FIN when they're tearing a connection down. And then the other side or opposite side will acknowledge that FIN. So you'll send a FIN to tear down the connection, you'll get an acknowledgement back. The other side will send a FIN and you'll send an acknowledgement back. So there's 4 messages to tear a connection down, unlike the 3 that are used to set it up. So some of the other headers that we've got with TCP, you see the source port and the destination port, obviously. Again, we use ports to differentiate networked applications. So once you've got to the computer, which is the IP address, you need another address to differentiate which application you're talking to, and that's done using ports. So in this case, we've got the destination port of 80, which means I'm talking to probably a web server. I've got a sequence number, which makes sure that the messages are put back together in the correct order. I've got an acknowledgement number, which has to do with while the communication stream is going on, the receiving computer continues to send back acknowledgements to let the sender know that it has received the messages that have been sending. And it does that to make sure that we continue to have a reliable connection. In other words, the messages that are being sent continue to be received. So we have to keep sending acknowledgement back. We have a window size value, which again goes back to that reliable transmission. The window size has to do with the number of bytes that I can send before I have to wait for an acknowledgement to be received. We have a checksum, which ensures that the message that is sent is actually the one that's received. In other words, it hasn't been altered in any way in transmission. And then we've got a set of options flags, which include a timestamp value. And the timestamp value can be used for a handful of things, which we'll get into in another lesson. But that's a quick overview of TCP and the headers and the various ways that TCP works. In this lesson, we're going to be talking about services. Services are applications that run in the background, which means they're hidden from view. They don't typically have any sort of interface component at all, and you wouldn't normally interact with them directly except through the interface that they are exposing through the services port in the case of a network application. First, I want to show you services under Windows. So you can see there are a number of services here that are running, and you'll notice in this window there's a status column, which shows whether the service is started. Now, there are a number of services here, and they do a variety of things. So you'll see a background intelligent transfer service, for example, which would transfer files without you needing to be directly involved in it. You can see the BitLocker drive encryption service, and in another video we'll talk about drive encryption. That service handles the encryption and decryption of data that's stored on the hard drive. Sometimes you'll have a service that looks for hardware to be plugged in. For example, Apple has a helper service that notices when your iPod or iPhone or iPad has been plugged in, and it will launch an application like iTunes or do something else with the fact that the hardware has been plugged in. There are other types of services, and those network services, I can show you under Linux, will have listener ports. And I can show you the different things that are running as listeners here on this Linux machine. There's a database server, MySQL. There's also an SMB server. There's an asterisk server for voice over IP. There is an Apache server. You can see partway down there under local address, it's got an asterisk :HTTP. That means it's listening on the HTTP port or port 80. And at the far end, you can see that the program that's actually running, offering that service is Apache 2. These are all different services, and they have a network component, which means they are listening on a network port and waiting for connections from other machines so that they can offer up the service to remote users. So you have local services and you have remote services, and you might have a database server or a web server or a file server, even a server that's capable of sharing up your desktop. So for example, VNC would be a service that's capable of sharing your desktop from your local system out to remote systems, which would allow you to get into your desktop from a remote system. So these are all examples of different services. I've shown you where to look at services on the Windows side, and I've shown you some different services that are listening on this Linux system, /etc/init.d. These are all startup and shutdown scripts that are here, and these are all of the different services that are available on this particular Linux system. It doesn't mean all of these services are running, but these are all capable of running. I could restart the MySQL server that's running, and you'll see here that it's saying rather than using etc init.d, you should use the service utility. So some Linux systems actually have a utility called service that will start up and shut down services. So I could do service MySQL stop as an example, and it would shut down the MySQL service. You would no longer be able to get access to the MySQL databases that are on this particular system. And you'll notice I am using sudo here. That's because these services generally require administrative privileges in order to start or stop them, because they are running as a different user than the one I am logged into, and so they require administrative privileges in order to kick them off. And that's one of the things about services. They are running as different users. So let's take a particular example here. The MySQL server service is actually running as the MySQL user. Now, the thing that's significant about that is that if I could compromise this MySQL server service in some way, then I would be the MySQL user, because that's the user that's actually running that particular program or that service. So on the Windows side, often you will see services that are running as local system. And you can see here on the right-hand side, most of the services here are logged on as local system. And the advantage to compromising a Windows service in this way is that local system has a lot of privileges. If you could compromise a Windows service that's running as local system, you would have a lot of privileges. And that's a little bit about services. In this lesson, we're going to be going over more detailed use of Wireshark, specifically how you would use it to do some deep analysis of things that were going on your network. So Wireshark has some really useful network analysis tools. Up top here, you can see a lot of different menu items, and we're going to go right to left and talk about some of the things that Wireshark has to offer. The first one we're going to talk about is telephony. In this case, we're talking about voice over IP. So we're talking about SIP and RTP and H.323, voice over IP, primarily data calls. Wireshark will show you some statistics about your voice calls. And in this particular capture, I don't have any voice calls, but I can show you what the menu item looks like, or what the dialog box looks like. So in this case, you'll see it says detected 0 VoIP calls and selected 0 calls. If there were calls, you could see the start time, the stop time, who the initial speaker was, who it's from and to, the protocol being used, the number of packets, and the current state as seen by Wireshark. If you were to have a call here and you were to select it, Wireshark could show you statistics about the call, like jitter and latency and those sorts of things. So Wireshark is good about pulling up statistics about voice calls. The other thing that Wireshark can do, it can play the voice portion of the call. So you see here player, and it says launch the RTP player to listen to the selected calls. If the voice stream is not encrypted, if it's just a clear text stream, Wireshark can decode the RTP messages and play them back for you. It can also show you a flow diagram or a ladder diagram of the selected calls, so it can show you all of the signaling messages for VoIP calls and broken down in order, which is really helpful if you're doing troubleshooting for voice calls or VoIP calls. In addition to telephony, of course, it does all of the standard data stuff that you would expect it to do. So under the statistics menu item, we've got a lot of interesting things here. We can bring up endpoints, for example, and it will show you all of the different endpoints that are involved in this particular packet capture. In this case, it's selecting them by Ethernet. I can also select them by IPv4. So these are all of the IP addresses that have been seen in this particular packet capture. There's also some IPv6 addresses, And then we've got higher level protocols like TCP and UDP. So it's broken down by these as well. Going back to the Ethernet here, you can see how it's broken down. We've got the address, and it's got the packet count and the byte count, but it also breaks those down into transmit packets and bytes and received packets and bytes. So this is really helpful in order to do some diagnosis on what's going on in your network, where you can see either by Ethernet address or MAC address or by IP address the different endpoints that are doing communications in a particular packet capture. I've also got conversations, which is a similar sort of thing. It will show you the conversations that are going on. The dialogue looks very much the same as the endpoints. We've got I/O graphs, where you can do different things. You can set bytes per tick and bits per tick, and you can add colors, and you can put together a little I/O graph of the network traffic that you've captured. We can also do a flow graph. In this case, I'm going to select all packets, and I'm going to do a general flow with standard source and destination addresses. And it's going to show me, this is very similar to the ladder diagram that I mentioned earlier with regards to VoIP calls. You can see the ladder here, where the endpoints are involved in a particular dialogue and who's actually said what and to whom they said it. And on the right-hand side, the comment, so you can see the information about the packet. It's TLS, it's TCP, it's HTTPS. So this is really helpful for getting a visual understanding of the different conversations that are going on and what they're actually saying. Easier sometimes to see it in this respect than it is to just look at a list of numbers and so on in a Wireshark capture. Under statistics, you can also pull down different things like HTTP. I can get the number of requests. If I were to set up a filter, I could get a statistic on that. I can get statistics on a TCP stream graph, round trip time graph. If there were wireless traffic, I could see that under WLAN traffic. I don't happen to have any here, so it's not going to show it. Moving along to the Analyze menu, you can see the list of enabled protocols here, and it's pretty significant. Wireshark has done a really good job over a lot of years of really beefing up what they're capable of doing. And if there's new protocols that get added, Wireshark is pretty good at picking up on those. Something else that's good here is decode as. If you were to see a stream that was taking place on oddball ports, for example, web traffic on port 8908, for example, Wireshark probably won't recognize that that's web traffic because it's on an oddball port and it may not see that that's really what's going on. It might, but if it doesn't, you can do a decode as. And you can say, instead of what you've currently decoded it as, you can decode it as this other protocol. So I want to decode it as HTTP. In this case, it's already done what it can because I happen to have an encrypted packet selected. But you can see that if you've got a particular traffic stream that Wireshark isn't doing the right decoding for it and showing you the right information, you can tell Wireshark to go decode it as a different protocol, and it will reorganize itself and show you all of the right information. So like down here, when you open it up, in this case, I've just got TCP. If I were to find an HTTP packet, you can see that Wireshark down below here, it's got TCP and it's also got HTTP. So that's partly where the decode helps you. It puts that extra section down below and properly analyzes it so all of the right pieces are filled in. While we've got this open, let's select this packet here. I can do analyze and follow TCP stream. One of the advantages of follow TCP stream is you don't have to open each individual packet up and take a look at what's going on and the ASCII that's inside it to be able to see all of this. What follow TCP stream does is it follows it and then puts an ASCII equivalent or a text equivalent up here in a box so you can just read it in plain text. This is a really helpful feature. I can also change this. In this case, it's raw. I can change what I'm doing to ASCII or EBCDIC. In this case, it's not EBCDIC. I can get a hex dump of it. And then I can also show C arrays. So you see the character array definition here. So I can break this into different pieces. I can also say I only want to see this half of it, or I only want to see this half of it. If you've got a really long conversation, maybe you only want to see one side. So as you can see here, Wireshark has a lot of really useful features for deep packet inspection and analysis. In this lesson, we'll be talking about DHCP, the Dynamic Host Configuration Protocol. DHCP is a really important protocol as well as an important program or service. The reason it's important is it makes it really easy to add systems to a network. If you have a DHCP server running on your network and it's properly configured, all somebody has to do is plug their system into your network and they will automatically obtain an IP address, subnet mask, and router information, as well as several other different types of information that you may choose to configure to get your network clients configured with. There's a downside to this, of course. Somebody can plug into your network and automatically be on your network. But particularly with large enterprises, it's much easier to use DHCP to get your systems up and running on your network, so you're not going around and configuring by hand everybody's system who's on the network. Not only is that time and resource consuming and really expensive from that perspective, but it also makes it difficult for systems like laptops, for example, to be removed from desks and brought to other locations in the building. So DHCP is really helpful, not only to get you up and running faster on a network, but also it provides the ability for your users to be more mobile, particularly if they've got systems that are capable of being mobile. So let's talk a little bit more about what DHCP is. And I've got a DHCP server running on this Linux system. I can show you the DHCP configuration file, and we'll take a look at the various things that we can configure here. So I can configure a domain name. So when you just type in one portion of the host name, you're configuring the search order, basically. So if I were to just type foo in this case, your system, since I've configured a domain name, would assume that you really meant foo.example.org. I can also configure domain name servers, so you don't have to go configuring the DNS servers yourself. I'm just going to push them to you, and I can keep traffic for DNS within my network by ensuring that you stay with my DNS servers rather than using more global ones. The default lease time here is 600, and the default lease time has to do with the amount of time you are allowed to keep an IP address before you have to go back to the server and say, hey, I need that IP address again, and it will either allow you to keep that IP address or it may give you a whole different IP address. So there are some trade-offs here. A shorter lease time means you're constantly talking to the DHCP server, while a longer lease time means that your DHCP server, if you've got a lot of systems that come and go, your DHCP server is going to hold that IP address and not let anybody else have it, or it's not going to place it back into the available pool until that lease time has expired. So if you've got a lot of systems that come and go, you run the risk of running out of your pool of IP addresses because your DHCP server is just holding them all for systems that came and may not come again for quite a period of time. Here's some information about how we're going to log what's going on with our server. And they're just basic frameworks for how you would define a subnet that gets served up using this DHCP server. So here's a very basic subnet, just 10.152.187.0 with a net mask of 255.255.255.0. We're not providing any other options than that since we gave the DNS up above. And maybe we don't want them to have a default gateway or a router so that they can't get off the network. Or you can add any number of other options yourself. This is just a basic framework to get you started. Here's another basic subnet declaration. I've given a subnet here. I'm saying that my range of IP addresses, in other words, my IP address pool, is from .10 to .20. I've given routers here, so I've got 2 routers or 2 default gateways. And of course, I gave the DNS as a global configuration up above. We can also do things like providing broadcast addresses if you want to do that sort of thing, although your system will usually assume based on the subnet mask what the broadcast address is, and it would be the correct one. We can say a particular host has special configuration, and so we can set up hosts based on their hardware address or their MAC address. And if you specify the MAC address, you can then say, here are some other configurations. And in this case, what we've set up is a TFTP boot server, and we're providing this system the boot server name as well as the file name that it's going to use to boot off from. So there's a whole lot of other configuration parameters that you can use on DHCP. Again, this is Linux. The DHCP server will have the same sort of configuration parameters on a Windows system. And of course, the way you would manage that would be through a graphical user interface that Microsoft would provide. So that's the configuration side. Let's take a look at how it's going to look on the network. So here's a Wireshark capture. I've got a DHCP request and a DHCP acknowledgement. In this case, the DHCP request, even though we call it DHCP now, DHCP came from an older protocol called the Bootstrap protocol. So when you're looking to filter in Wireshark, you would use bootp, which is what I typed up here, and it's now gone from the filter box. But you can see down here is the Bootstrap protocol. And let's zoom in a little bit. So the request type or the message type is boot request. There's a transaction ID. I've got some flags. Client address is blank. The client MAC address is my MAC address or my physical hardware address. And the option is a DHCP request. And there's a parameter request list where I'm asking for subnet mask, router, domain name server, domain name, domain search, and a number of other things. Now here you can see I have actually requested an IP address. What that means is I previously had this IP address, and for ease of use, I would like to have it again. And the DHCP server, if it knows about this and if that IP address is available, if it doesn't know about it, then it's going to give that IP address. So that's the request. Now let's look at the acknowledgement. This would be from the DHCP server back to me. And you can see that the server IP address is 192.168.1.1. My IP address is 1.26. I've got the MAC address again, which is the physical address of my system. DHCP server is going to be 192.168.1.1. It's giving me a lease time of a day and a renewal time value of 12 hours. So even though I've got the lease for a day, after 12 hours, I need to be asking for the lease again. It's got my subnet mask, my broadcast address, the router address, which is the gateway, DNS server address, a domain name, and up above it gave me my IP address back. So these are what the DHCP messages look like. Again, I pulled them right off the wire, and Wireshark has actually pulled this apart into its individual pieces and is presenting it to us in a way that we can read. This is not actually what the packet looks like. What the packet looks like is what's down at the very bottom It's all in hex, and you may see some ASCII characters there from time to time, but Wireshark does a really good job of presenting the information in a way that's easy to read and easy to understand, which again is another good reason for using Wireshark. So that's some information about DHCP and how it works and how you would configure it and what it looks like on the wire. In this lesson, we're going to be talking about ARP, or the Address Resolution Protocol, and how you would make use of it and how it actually is used. So the first thing I want to do is show you what's called an ARP table. So every computer system carries what is called an ARP table. The reason it's called an ARP table is because it matches a layer 2 or physical address or MAC address to an IP address, and that's what ARP is. ARP is the Address Resolution Protocol, and what it resolves is an IP address to a MAC address or a physical address. And the MAC or physical addresses are interchangeable because they mean the same thing. The reason it's called a physical address is because it is physically on a network interface, which is, of course, a physical device. So it's sometimes called a physical address, it's sometimes called a MAC address for media access control. So I might use MAC address, I might use physical address to make a particular point, but it means the same thing. So you can see here there are IP addresses and there are MAC addresses that are listed in this ARP table, and I've done ARP-A, meaning show me all of your ARP entries. And while I'm doing this on a Linux system, it will work on any system pretty much that has the TCP/IP suite of protocols installed, because it's an important utility to have in order to help diagnose any issues with your network problems. So this is how you would display an ARP table, and as I said, ARP is just a mapping from IP address to MAC address. So let me show you how the protocol actually works. I'm going to do a little filter here, just so that all we're seeing is ARP. And you can see on the info column here in Wireshark, it says who has 192.168.106, tell 192.168.1.1, and that's really what an ARP request looks like. What an ARP request is a message going out to the wire saying, hey, who has this IP address? I need to know the MAC address that goes along with it so that I can throw it out and get it to the right place. So ARP is really a local area network protocol, because once you get to the local area network, you're not communicating with IP addresses anymore, you're communicating with MAC addresses. So a system is only going to look at messages that have a MAC address that it has some control over. So either it's a broadcast MAC address or it's a unicast address that is directed to that particular system. So in order to get messages to the correct system on a local area network, you need to use the correct MAC address. So you send out a request. Who has a particular address? So here's an exchange here that we can take a look at. Who has 192.168.1.18? And I'm going to pop open the Address Resolution Protocol section here in Wireshark so we can take a closer look at it. And you can see it's a hardware type Ethernet, a protocol type IP. I've got an opcode of request. So the operation code is a request. I've got the sender's MAC address, which is how we know where to send it back to. And you'll notice the target MAC address is empty, and that's because we don't know it yet. So when the system who actually has that IP address or is responding on its behalf sends a message back, and we can show this one here, you'll see the target MAC address is filled in with the original requester, and the sender MAC address is filled in with the correct MAC address of that particular IP address. So you'll see sender MAC address happens to be an Apple device. Wireshark does a good job of actually decoding the MAC addresses so that it's got the vendor ID. So a MAC address is actually broken into two sections. The first three hex numbers there, 34, 15, 9E, are for the vendor. So the first half of a MAC address belongs to the vendor. That's the vendor ID. The second half is the device ID for that particular vendor. So Wireshark, as I said, will actually map the vendor ID to the vendor name. So I've got Apple and I've got Netgear here. So you can see the request in this packet here and the response in this packet here. So that's actually how ARP works. You send out a request looking for a MAC address based on an IP address, and you get a response with the correct MAC address. Sometimes you may need to go from MAC address to IP address, and you would do that using the Reverse Address Resolution Protocol, or RARP. So let me show you something here where you would make use of ARP. So let's say you're sending a message that is an ARP response, but there was no request to go with it. If you were running the system that received that request, what would you do with it? Well, you might discard it, but one of the easiest things to do is just log the information. That way you don't have to ask for it later on. You've just got a record of it. So if you happen to see a message with what's called a gratuitous ARP, or an ARP response that hasn't been requested, if you see one of those going around, you may just consider keeping track of it so that you know later on and you don't have to ask. It saves time and it saves network bandwidth. Here's a utility here that actually takes advantage of that. This is called EtterCap. EtterCap has the ability to do a lot of gratuitous ARPs and do what we call ARP poisoning, or a man-in-the-middle attack. So the first thing here I'm going to do is unified sniffing. And I'm going to get a host list. And I don't actually have any hosts that it's aware of yet, so I'm going to scan for hosts. And let me bring up the host list again. I am going to add a bunch of hosts to one target, and then I'm going to add another bunch of hosts to another target. So you create two targets, and then you set up your ARP poisoning. And I want to do that. I want to sniff remote connections. And this is my man-in-the-middle attack. It's ARP poisoning. I'm going to send out a whole lot of ARP responses here. And you can see there's a whole chunk of is-at messages that are going by. So 25, 33, 25, these are all at the same MAC address. That's what's going on here. I've got a whole bunch of gratuitous ARP messages that are being sent out onto the network saying, hey, this IP address belongs at the MAC address that actually lives on my particular system. And so messages that would normally be directed to that IP address would then come to me. Now, there's a bit of a challenge there because you need for the system that you are on to be able to forward packets, because you've got to get the messages back out onto the wire with the correct MAC address. Otherwise, nobody gets their messages. And so you start to think that something is a little bit screwy because suddenly there's no communication. And that's a big flag indicating that something is wrong on the network, and somebody's going to go start looking for what's wrong on the network, and they're going to see that, hey, guess what? Somebody's doing a whole bunch of gratuitous ARPs. They're going to track the MAC address back, and they're going to find your system there. So I'm going to shut down the man-in-the-middle attack here. And you can see that in addition to ARP poisoning, EtterCap has the ability to do other types of attacks as well, including ICMP redirect, port stealing, and DHCP spoofing. So EtterCap is a pretty good utility for sitting in the middle of conversations and seeing what goes on. And this is why I'll mention from time to time that switches are not effective tools to prevent people from hearing conversations that don't belong to them or that they're not normally a part of. Primarily because EtterCap just makes it so easy to do this ARP poisoning in which case you're entirely bypassing the switch because people are addressing packets to you. So that's the address resolution protocol and some different ways of making use of it. In this lesson, we'll be going over a brief history of cryptography. Cryptography actually goes back several thousand years, probably shortly after people began to find ways to communicate. There were some who were finding ways to make the understanding of that communication difficult so that other people couldn't understand what was going on. The Caesar cipher was developed by Julius Caesar, and it's a simple rotation cipher. And by that, I mean that you rotate a portion of the key in order to generate the algorithm. So here's an example. We've got 2 rows of letters that are in alphabetical order, means we've basically written the alphabet down. The second row is shifted by 3 letters. So A, B, and C from the first row get shifted to the back on the second row, and we start with the letter D. And below that, there's an example of an encrypted string. So I've encrypted the word hello, and in this particular shift, that translates to LHOOR. So with variable spaced fonts, it's harder to see what lines up right over another letter, but if you count the letters out, you can see that the letter H translates down to the letter L, and so on. So that's a Caesar cipher, and you'll occasionally hear things like ROT13, which means that you rotate 13 letters instead of the 3 that we've done here, and that again is just a simple rotation cipher or Caesar cipher. And that's what, of course, the ROT stands for, is rotate or rotation. Coming forward a couple thousand years, we have the Enigma cipher. Now, it's important to note that Enigma is not the word given to this particular cipher by the people who developed it. It's actually the word given to it by the people who were trying to crack it. The Enigma cipher is a German cipher. They developed this cipher and a machine that was capable of encrypting and decrypting messages so that they could get messages to and from different battlefields and war fronts, which is similar to the Caesar cipher. Caesar used it to communicate with his battlefield generals, and the same thing here with the Germans. You've got to get messages from headquarters down to where the people are actually fighting, and you don't want it intercepted in between by the enemy, so therefore you use encryption. And lots of energy was spent by the Allies, in particular the British, trying to decrypt the messages. One of the first instances that we are aware of where a machine was used to do the actual encryption. So we're going to come ahead a few decades now into the 1970s, where it was felt that there was a need for a digital encryption standard. Now, the National Institutes of Standards and Technology is responsible for that sort of thing, and so they put out a proposal for this digital encryption standard and an encryption algorithm. What ended up happening was IBM came up with this algorithm that was based on the Lucifer cipher that one of their people had been working on a couple of years previously in 73, 74. And they put this proposal together based on this Lucifer cipher, and in 1977, that proposal for an encryption algorithm was the one that was chosen to be the digital encryption standard. And so that became known as DES. Over time, it became apparent that there was a problem with DES, and that was it only had a 56-bit key size. And while in the 1970s that was considered adequate to defend against brute forcing and breaking of the codes, by the 1990s it was no longer considered adequate, and there was a need for something more. It took time to develop something that would last for some long period of time, and so in the meantime, a stopgap was developed, and that stopgap is what we call triple DES. The reason it's called triple DES is you apply the DES algorithm 3 times in different ways, and you use 3 different keys in order to do that. So here's how triple DES works. Your first 56-bit key is used to encrypt the plain text, just like you would with standard DES. Where it changes is you take that ciphertext that's returned from the first round of encryption and you apply the decryption algorithm to that ciphertext. However, you don't use the first key to decrypt it because otherwise you'll get the plain text back. So what you do is you use a second key with the decryption algorithm against the ciphertext from the first round. So now we've got some ciphertext that has been encrypted with one key, decrypted with a second key, and we take the ciphertext from that and we apply a third key using the encryption portion of the algorithm to that ciphertext to receive a whole new set of ciphertext. Obviously, to do the decryption, you do the third key and decrypt it. With the second key, you encrypt it. And then with the first key, you decrypt it. So you do reverse order and the reverse algorithm at each step to apply the triple DES. So we get an effective key size of 168 bits, but it's still only 56 bits at a time. As I said, triple DES was only a stopgap. What we were really looking for was the advanced encryption standard. Once again, NIST requested proposals so that they could replace the digital encryption standard. In 2001, after several rounds of looking for algorithms and looking them over, getting them evaluated and looked at, NIST selected an algorithm that was put together by a couple of mathematicians. The algorithm was called Reindahl, and that became the Advanced Encryption Standard, or AES. One of the advantages of AES is it supports multiple key lengths. Currently, what you'll typically see is AES with 128-bit keys. However, AES supports up to 256-bit keys. So if we get to the point where 128 bits isn't enough, we can move all the way up to 256 bits of keying material. So cryptography has a really long history. Currently, we're in a state where we have a reasonably stable encryption standard in AES, but the history of cryptography shows that with every set of encryption, eventually people find ways to crack it. In this lesson, we're going to be talking about different types of cryptography. The first type of cryptography I'm going to talk about is symmetric cryptography. And by symmetric, I mean that the key is the same for encrypting or decrypting. So I use the same key whether I'm encrypting the data or decrypting the data. One of the things about symmetric key cryptography is that they use a shorter key length than for asymmetric, which I'll get into in a couple of minutes. It's also faster than asymmetric. You can use algorithms like DES or AES. Those are both symmetric key cryptography algorithms. And you can use a utility like AES crypt. I've got a file here called text.txt. I can use AES crypt. I'm going to encrypt it with the password cookie. And now I've got text.txt.aes. And if I just take a look at that, it looks like garbage. Now to decrypt it, I just use AES crypt again, -d with a password of cookie, and text.txt.aes, and that just decrypts it. So that's how you would use symmetric key encryption to encrypt a file for this example. Symmetric key uses either stream or block ciphers, and the difference between stream or block ciphers is that block takes a block of bits at a time, and it's a fixed length block. So for example, 64 bits. If I were to use a block cipher with 64 bits, I would need to take in 64 bits before I could start encrypting. If I didn't have 64 bits to encrypt, I would have to fill it with padding in order to get up to the 64 bits. A stream cipher, on the other hand, will encrypt a bit at a time, so it doesn't matter how many bits you've got. You don't need to have some multiple of the block length in order to encrypt without padding. Another type of cryptography is asymmetric. Asymmetric, as you would expect, uses two different keys. That's where we have a public key and a private key. Asymmetric cryptography uses a longer key length. It also has more computation, and the encryption process is slower with asymmetric key encryption. One of the uses for asymmetric key is for signing documents or emails, for example, where I would have the private key sign something and the public key would be used to verify the signature. Another reason for using asymmetric key encryption is to ensure that who you got it from is who actually sent it. Since you've got two keys, you always know who the other end of the equation is, where with symmetric key, since it's just one key, if you can intercept the key, you can decrypt and also encrypt messages. And so if somebody can figure out the key, you can break into a communication stream using symmetric key encryption. So asymmetric gives you the advantage of ensuring that the other end is who the other end says they are, since they're the only ones who should have the private key in this particular instance. In practice, however, hybrid encryption models tend to be used. And that's where you would use asymmetric encryption to encrypt a symmetric session key. Since symmetric is the faster algorithm, if you're transmitting a lot of data, particularly in a real-time sort of fashion, like a web session, for example, you would want to be using symmetric key encryption, but you would want to make sure that you transmit the session key using asymmetric key encryption. Now, we can use asymmetric key encryption to encrypt a file. It's going to be a slower process. You probably want to use smaller files in order to do that. Fortunately, the file example that I have here is a small one. The thing about this, though, is I've got to generate a key in order to do that. So I'm going to generate a key here. This is going to be an RSA key, and I'm going to call it private.key, and my key length is going to be 4096 bits. And we're generating the RSA private key here. And now it's asking me for a passphrase. This simply protects the key. It has nothing to do with the keying material itself. It just protects the key so that nobody other than the person who knows the passphrase can make use of the key. Now I've got to generate a public key from that private key. I'm going to use OpenSSL again to do that, and it's asking me for my passphrase for the private key in order to access it. Now I can do the actual encryption, and I'm going to use OpenSSL again. Encrypt. I'm encrypting it with my public key so that it can be decrypted with the private key. So that's how I would do the encryption. Now to do the decryption, I see that I've got my encrypted text there, and I've got my encrypted text. So in order to decrypt it, I do the reverse process, where I'm going to decrypt. I hand it my private key, since that's the other side of the public key. And I'm going to feed it the encrypted text, and I'm asking for a file name of plaintext.txt out. It's asking me for the passphrase for my private key, since I have passphrase protected it. And now it should have the plain text back. It looks right. Let's just check. And there's no difference between the original text and the plain text that came out of the decryption. So that's just a little bit on the couple of different types of cryptography and different ways of thinking about cryptographic ciphers and how to use them. In this lesson, we're going to be talking about public key cryptography. Public key cryptography only tells half the story, frankly, when you call it public key cryptography, because public key cryptography uses key pairs. There's one secret or private key, and there's also one public key. The keys are linked mathematically. Now, they have to be linked mathematically because you use one key for encryption and one key for decryption. If I were to send a message to you, I would get your public key and I would encrypt my message to you. You would then use your private key in order to decrypt that message. So there's always two sides to this public key scenario. We've got a public key and a private key. Now I can show you the private key for a certificate. As always, we password protect them. So here's all of the keying material for the private key for this server key that I've generated. 4096 bits of a private key here, and here's all of the keying material. Now I can look at the public key as well. So that's all stored in an X.509 certificate. An X.509 certificate can also be used to digitally sign a message to somebody. And in order to do that, if I were to send you a message that I wanted to sign, I would sign it with my private key. And you could verify that it was mine by using my public key, which you have access to because it's public. So these are X.509 certificates. X.509 certificates certainly implement public key cryptography, but it's not the only mechanism. You may have heard of PGP, which is short for Pretty Good Privacy. It was developed by a guy by the name of Phil Zimmerman in 1991. PGP also implements public key cryptography, but it implements it in a different way. The way that PGP implements public key cryptography is using a decentralized approach, where X.509 certificates use a certificate authority, and that certificate authority is where information is stored and where people and users are validated and verified. PGP doesn't use any central authority. PGP relies on individual users to validate and verify user identification. This is what PGP calls a web of trust model. Rather than having one central authority that's responsible for doing all of that work, which of course incurs costs because you have to employ people and have facilities and infrastructure for all of that, which makes X.509 certificates cost money. PGP uses this web of trust model, which means I post my public key to a public key repository, and there have traditionally been a few of them around. Once I post my public key, anybody who knows me goes and signs my public key with their key. And in signing my public key with their key, you can know that I'm who I say I am if you know and trust that person. So the idea is that we use people and you get the 6 degrees of separation sort of effect where eventually you know enough people who have signed enough certificates that you can trust the new ones that you run across. So that's how the PGP model works. The web of trust is used to ensure that people are who they say they are. X.509 uses a certificate authority to verify that people are who they say they are. The end result, though, is effectively the same. You have a public key and a private key. Both are required for the whole process between encryption and decryption, as well as digital signing. And that's just an overview of public key cryptography. In this lesson, we're going to be talking about certificates. So what's a certificate? Well, a certificate is a digital piece of data, kind of like a passport or a driver's license, that tells who you really are. Not only does it tell who you really are, but it gives you the ability to do things like encrypting messages. So it's a little bit more than a passport or a driver's license in the sense that in addition to validating your identity, it also gives you the ability to do some other things. So let's actually generate a certificate here. And I'll talk a little bit about what I'm doing as I'm doing it and then why we're doing this and the various things that you can use certificates for. So one of the things that you're going to be most familiar with the use of certificates for is encrypted websites. When you use an HTTPS connection to a website, you're actually using a certificate. The server has a certificate that it offers to you, and you go through this negotiation for encryption mechanisms, and that's all done through the certificate. In this case, I'm going to generate a certificate authority certificate. So I'm doing an RSA key here to use inside the certificate. So I'm generating a private key, and the private key is used as part of the certificate, and there's a public key associated with it. With certificates, you've got public and private key, and data gets encrypted with the public key and then decrypted with the private key. So they are mathematically linked, that public and private key, because you need one for one end of the communication and the other for the other end of the communication, and they have to be linked so that the data that's encrypted with one key gets to be decrypted with the other key. So this is asking for a passphrase, and that's just to protect the key. So I'm now going to generate the certificate itself. And you can see I'm using the OpenSSL utility here. I'm doing a new certificate that's going to be a new request. It's an X509 certificate. It's going to be valid for 365 days. The key that I'm using for this certificate is called ca.key. And then the out, I'm going to call it ca.crt. And since I'm accessing the key, it wants the passphrase for that. And now it wants me to fill in a bunch of information. So I'm just plugging in information that's going to be inside the certificate. It's going to be stored in the certificate that I can verify. I'm going to call this root. So now I have a certificate. And I can take a look at it using OpenSSL, and this is going to be useful if you ever need to take a look at a certificate. You can use OpenSSL, and you're just going to say it's an X509 request to OpenSSL, and I want a text. So I want text output, and the input is going to be my certificate file. And here's actually the certificate itself, and you can see all of the data that's stored inside the certificate. So I could use this CA to generate a self-signed certificate, and while there's certainly nothing wrong with that, there's also nothing that guarantees that you are who you say you are to somebody accessing this particular certificate. The self-signed certificate gives you encryption, but what it doesn't really give you is that validation that you are who you say you are, and that's what we call non-repudiation. What non-repudiation means is you can't say that you didn't send a particular message if your key was used to generate that message, particularly if you've protected your key by password protecting it. Since you're the only one who is supposed to have your key and also have the password, it's a lot harder to say that you didn't generate a message if your key was used because you had the key and you had the password and nobody else had it. So in addition to encryption, we can do things like we can digitally sign messages like email. You could digitally sign an email, and that doesn't give you any privacy, but what it does give the person on the other end is some proof that you were the one who actually sent it and that it hasn't been tampered with in transit. Because certificates have this validation using a secure hashing algorithm. And you'll see here that the signature algorithm is SHA-1 with RSA encryption. So we're using RSA encryption, but we're also using SHA-1, which is a secure hash algorithm, which verifies that the message that's received is the one that's sent. Since we generate a hash, so that we can check both ends to make sure that the data on both ends is the same. So while we did a certificate authority here of our own, there are certificate authorities where their business is being a certificate authority. And I mentioned doing this validation thing. And the validation is where the certificate authority makes sure that you are who you say you are by using some form of identification prior to issuing you your certificate. That way you don't have any sort of confusion about whether the person is who they say they are or not. Since a certificate authority is supposed to be a trusted entity, and that trusted entity says, yes, Rick, you are who you say you are, everybody can be assured that that's true. Without that certificate authority, you're a little less certain whether somebody is who they really say they are or not. So a certificate authority has to have its own certificate, which is what we generated a little bit earlier, and that's because the certificate for a user is effectively signed with this certificate for the CA. And that CA certificate then has to be installed pretty much anywhere the certificate is going to be used. So here's an example. Let's look at Firefox. And we can view the certificates that are installed on this particular computer here in this browser. So I'm looking at the certificate manager for Firefox, and I see there's an authorities tab. And here's all of the authorities that have either been built into Firefox here or have been added in some way. And you can see here that I could do an import of a certificate that I've generated, and here's an example of one, the ca.crt. I could open that up, and it's telling me it's already installed. So there's a certificate here that I created as a CA certificate that's already been installed in this browser as a certificate authority. So lots of authorities here, and every one of these is capable of creating certificates for users or for servers, and any certificate that's issued by these CAs would automatically be trusted by this particular browser. If we ran across a certificate that had not been issued by a trusted certificate authority, we would get a message indicating that there's a certificate error, and then you'd have to go through a process of generating an exception or some other process to say, yes, I really want to go to that website. So that's some of the basics of certificates and their use. In this lesson, we'll be talking about cryptographic hashing. And while the word cryptographic is in the term cryptographic hashing, and it does lead you to the belief that there is encryption involved, there is no encryption involved in a cryptographic hash. There is a significant difference between hashing and any sort of encryption, and that is primarily that encryption is a two-way process. When I encrypt a piece of data or a file or anything else, what I'm doing is putting it into a state where I expect to be able to get it back out again. In other words, when I encrypt a file, I expect to be able to decrypt the file and get the original contents back. Hashing is a one-way function. Once I've hashed a piece of data or a file, there is no expectation and no ability to get the original piece of data back. Hashing generates a fixed length value, and different types of hashing will generate different length values. For example, MD5 will generate a different length value than SHA-1 hashing. They're both hashing algorithms, but they generate different length values. The resulting value from a hash function should bear no relation at all to the original piece of data. As a matter of fact, if two inputs generate the same hash value, it's called a collision. And if you can generate collisions, you may be able to get to a point where you can generate pieces of data that are going to generate the same hash value, and that leads you to the potential ability to break the particular hashing algorithm that you're using. So what can we use hashes for? Well, one thing we can use hashes for is file integrity. We can run a hash on a file and get a value back, and later on we can check that value to make sure that it's the same. If it's the same, I can be sure that it was the same file that was hashed in both instances. So sometimes when you're going to download like a software package from a website, you will see cases where there's a hash value. If you download the software, you run a hash algorithm against it and compare the value to that was posted on the website. If the values are the same, you know that what you got is the original software without any sort of corruption. So we can show you a simple hash process here. Run MD5 sum. This is on Linux, but you can get a version of MD5 or an MD5 summation program for Windows, and Mac OS comes with a utility called MD5, which does the same thing. So I have a file here called ca.crt. I'm going to run an MD5 sum against it, and I get a value back. Since it's the same file, I'm going to get the same value back every time. Another use for hashing that you will often see is we hash passwords. The reason for hashing passwords is so you're not storing the clear text password, which would be easily seen, even if you've got it protected with permissions. If I hash the password, every time I hash that password, I'm going to get the same value back from the same algorithm. So what I do is I store the hash in some sort of password database. Since it's a one-way function, you can't get the password back directly from the hash. Now, what you can do, most password cracking programs do some variation of this, is you generate hashes against a list of words until you get a hash value that matches the one in the password file. Once you've got the hash that matches the one in the password file, you know what the password is. And here's where we come back to the idea of collisions. If I can take two different strings of characters and get the same value back, then it's easier to crack passwords, because I may not necessarily get the password, but if the hash that I get back from a particular string of data is the same as that I get from the original password, then it doesn't matter whether I know the password or not, because the string of data that I put in is going to generate the same hash value, and what you're comparing when you log in is the hash value. So let's say the strings dog and cat got the same hash value. Your password was dog. I plug cat into a hash that generates this hash value that compares to the same as the one for the word dog. While I'm using cat, since the hash value from that is the same as the one for dog, I would be able to log in even though I don't know your password. So it's not necessarily critical to know the password. All you're looking for is some string that generates the same hash value, since that's what's being compared anyway. And that's a little bit on hashing. In this lesson, we're going to be talking about different types of cryptographic ciphers, and primarily we're going to be talking about DES, triple DES, and AES. DES is the digital encryption standard. It was developed by IBM in the 1970s. Originally, it was a cryptographic cipher named Lucifer, and after some modifications, IBM proposed it as the digital encryption standard, and it was selected to be the digital encryption standard, and ever since then it's been known as DES or DES. One thing that caused a little bit of controversy was during the process of selection, NSA requested some changes, and it hasn't been particularly clear what changes were requested by the NSA. There has been some speculation that wondered if the NSA was requesting a backdoor into this digital encryption standard, which would allow them to look at encrypted messages in the clear. So basically, it would always give the NSA the ability to decrypt DES encrypted messages. It remained the encryption standard for the next couple of decades or so. So what is DES and how does it work? It uses 56-bit keys rather than a stream cipher. It's a block cipher, and it uses 64-bit blocks. In 1998, DES was effectively broken when a DES encrypted message was cracked in 3 days. A year later, a network of 10,000 systems around the world cracked a DES encrypted message in less than a day. And it's just gotten worse since then, with modern computing power being what it is. Since DES was encrypted and the writing was on the wall for a little while, we knew we needed something else. So along comes triple DES. Triple DES isn't 3 times the strength of DES necessarily. It's really DES applied 3 times. And what I mean by that, what we do is we take a plain text message, and let's call that P, and we're going to use a key that we'll call K1, and we're going to use that key to encrypt the message, and that's going to result in ciphertext, and we'll call that C1. So with C1, the output of the first round of encryption, we're going to apply a second key, and we'll call that K2. With that second key, we are going to go through a decryption process on C1. Since it's the wrong key, we're not going to get plain text out the other end. What we are going to get is another round of ciphertext, and we'll call that C2. With C2, we're going to apply a third key. We'll call that third key K3, and we're going to encrypt the ciphertext C2, and that's going to result in another round of ciphertext that we'll call C3. So we have 3 different keys applied in 2 different ways. So with key 1 and key 3, we do a round of encryption, and with K2, we do a round of decryption. So it's an encrypt, decrypt, encrypt process with 3 separate keys. While that doesn't really yield a full 168-bit key size, the 3 rounds of encryption yield an effective key size of 168 bits because you have to find 3 56-bit keys. So speaking of that, technical details for triple DES. We're still using the DES block cipher with 56-bit keys, but since we've got 3 different keys, we get an effective key length of 168 bits. Triple DES was really just a stopgap measure, however. We knew that it was broken, and if you could decrypt a DES message, it probably wouldn't be all that long before you could decrypt triple DES messages as well. As a result, NIST requested proposals for an advanced encryption standard. That was in 1999. And in 2001, NIST published an algorithm called Raindoll as AES. So this algorithm that was originally called Raindoll was published by NIST as the Advanced Encryption Standard. Some technical specifications about AES. The original Raindoll algorithm specified variable block sizes and key lengths, and as long as those block sizes and key lengths were multiples of 32 bits, so 32, 64, 96, and so on, you could use those block sizes and key lengths. When AES was published, AES specified a fixed 128-bit block size and key lengths of 128, 192, and 256 bits. So we've got, with AES, 3 different key lengths, but 1 block size. And that's a little bit of detail about DES, triple DES, and AES, and we'll use some of these in doing some hands-on work in subsequent lessons. In this lesson, we're going to be going over SSL and TLS. SSL and TLS are ways of doing encryption, and they were developed in order to do encryption between websites, web servers, and clients or browsers. SSL was originally developed by a company called Netscape, And if you don't remember Netscape, eventually Netscape spun off their source code and it became the Mozilla project where we get Firefox from. So back in 1995, Netscape released version 2 of SSL. There was a version 1, nothing was ever done with it. So we've got version 2 of SSL, and that was used for encryption of web transmissions between the server and the browser. 2.0 had a whole number of flaws, and SSL 2.0 has the types of flaws that can lead to decryption of the messages without actually having the correct keys or not being the right two endpoints. And so Netscape released 3.0 in 1996. So we've got SSL 3.0 in 1996. SSL 3.0 is better than 2.0, but it still had some issues. And so in 1999, we end up with TLS. SSL is Secure Sockets Layer and TLS is Transport Layer Security. They both accomplish the same sort of thing. They are designed for primarily doing encryption between web server and web browser because we want to be able to encrypt that type of traffic. So let me show you what that kind of traffic looks like. And we are at the Infinite Skills website here, so I can go to my Wireshark capture and I can look for the start of my encrypted communication. I'm going to apply as filter here so that I get all of those messages, and I'm going to go up to the top and I'm going to look for the TLS connection here. So how this works is I get a client hello going out to my server, and you can see here's my source 1.32 and the destination is 76.12.59.46. Doing a client key exchange and a change cipher spec, an encrypted handshake message, and then we start getting application data. So there's some other steps involved here, and you're not seeing all of it with this particular Wireshark capture because, again, we get fragmented packets, and at some point it starts getting encrypted and you can't see it anyway because Wireshark, without having the key, can't decrypt those messages. But what ends up happening is the client sends a hello, the server responds with a hello, they end up exchanging information as part of that, including version numbers supported, and you get a random number, and the client's going to send out a number of cipher suites that it may want to support or that it can support, and the server is going to pick from those suite of ciphers. Then we start doing the key exchange, and they do the change cipher spec from the client and the server, and eventually the server just sends a finished message, and at that point we've got this encrypted communication going on. But there's this handshake that goes on between the two systems, and there's a number of different types of handshakes depending on the type of endpoints that you've got. But that's the types of communication that goes on between the server and the client. One of the important things about using SSL and TLS is, as I mentioned, some of the earlier versions had vulnerabilities in them, and you want to make sure that servers aren't actually running those. So we want to run some scans to figure out the types of protocols and ciphers that different systems use. So we can use something called SSL scan. And this is available for Unix-like systems. It'll run under Mac OS and Linux, as well as BSD platforms. There is not a version available for Windows for this particular program, although there may be other programs that accomplish similar goals. So I'm going to do an SSL scan here against the website, and you can see it's going out and probing all of the different types of ciphers that we know about on this system. Started with SSL v3, and now we're going into TLS version 1. We could force SSL scan to try to do an SSL v2. If I scroll back up here, I get the preferred server ciphers, which is SSL version 3. It's using RSA for the asymmetric in order to do the key exchange, and once we get the session key up, We're going to use AES 256, and then we're going to use the secure hash algorithm to do the message authentication code, or the MAC. It's sometimes called the HMAC for the hashed message authentication code. And what that does is it's simply a hash that you would check one side against the other to make sure that the message hasn't been fiddled with in transmission. You can see here all of the different types of cipher suites that are available. Here's TLS running RC4 at 40 bits using MD5. So that would be a pretty vulnerable type of communication to use between the server and the client. A 40-bit cipher using RC4 is a low-strength cipher, and we would definitely recommend that clients remove those from the supported ciphers that they have on their server. All of that configuration would be done at the web server, as well as when you generated your key and your certificate. Normally, certificates would be handled by a certificate authority. You can also self-sign certificates and have those installed in your web server in order to do communications with your clients. The challenge with that is browsers today warn when they see a certificate against a certificate authority that isn't trusted, or if it doesn't have any certificate authority at all, you'll get a warning in your browser indicating that there may be a problem with the certificate. If your clients are savvy enough, if the users are savvy enough, you may be able to make use of these self-signed certificates and save yourself some money. But generally, it's not recommended, simply because clients start getting used to these bad certificates, and when they run across one that's really a problem, a real rogue certificate, they're going to ignore the certificate messages in their browsers and just go to these sites that could have malicious purposes in mind and may end up compromising the clients or your customers or users. So that's SSL and TLS and how they work and negotiate between the server and the endpoint. In this lesson, we're going to be talking about SSH. SSH is short for Secure Shell. It was developed in 1995 as a replacement for Telnet and the various R protocols like RShell and RExec. There are several things we can do with SSH since it's an encrypted version of a Telnet-like protocol. We have keys that we need to deal with. One of the ways you can actually authenticate, let me show you a simple authentication first. This is just a very straightforward username and password authentication. Exit out of it. Since it's a public-private key means of encryption, what I can do is generate a key. I can use that key to do my authentication. So I have my keys right there, the ID_RSA and ID_RSA.pub. What I need to do now is copy the ID_RSA.pub into the .ssh directory. You can see here I'm using SCP, which is a way of doing an encrypted copy. It uses the SSH protocol set and all of the keys, and it does a copy from one system to another. SCP is secure copy. Asking me for my password because I don't have the key set up yet, and it's copied it over. Now I need to get into that system. And I should have the ID_RSA.pub, so I can cat that into my authorized keys file, and that's going to append it. And I can show you the authorized keys file. You can see I've got 2 keys in there. So I'm going to exit out of here. And now I should be able to SSH into that other system without any authentication. And I didn't use a password to get in, so you can see that. In addition to the authorized keys file, you'll see a known hosts file. So I'm going to go back into the SSH directory here, and you can see the known hosts file. These are all of the keys for the different systems that I have connected to from this system. So this is the key storage for all of the other SSH servers or systems that I have connected to from here. You can see there's a configuration file, and this looks like it was probably from the original OS install, and this was probably part of the skeleton that just gets copied over. In the configuration file, you can set up a number of entries for hosts where you can specify the host, you can specify your login name so you don't have to type it every time, you can specify an alias for it. So instead of the 192.168.1.39 that I'm typing every time, I could set up something like Bill, for example. And then I could just SSH Bill, and in my config file, I could set up the username I use on this system, and it would authenticate me using that username, and in this case, it would just use the public-private keys to do the authentication for me, since I've already set those up. Something about SSH, though, is the early versions were vulnerable to some problems. The problems in version 1, you could essentially decrypt the communication stream. In other words, SSH version 1 has been broken, and any communication using SSH version 1 is vulnerable to being read into clear text as a result of the protocol and the keys being able to be used to decrypt the transmission. So anytime you find a system that's running version 1, there's a possibility that you could decrypt transmissions between that system and whatever system is connected to it. In subsequent versions, though, that's been worked out, and although there have been vulnerabilities in SSH, it's a pretty solid protocol and can be used for doing this command line console access to remote systems in a secure fashion using an encrypted mechanism. And as I noted earlier, there are some related programs, primarily SCP, that are part of this SSH package and provide, again, some of the same functions that the R protocols like RExec and RShell, those types of protocols, provides the same functionality that they do. So secure copy you can use to copy from one system to another in the same way that you would use just CP on any Unix-like system. So you can use SCP to copy from one system to another, and the copy will be encrypted, and you can ensure that nobody is going to intercept those files and be able to read them in plain text or clear text. SSH has a lot of other capabilities as well. Of course, if you ever want to read more about SSH, you can just do man SSH. This particular implementation of SSH was created by the OpenBSD folks, and it's OpenSSH, although the original version of SSH was created by a guy in Finland, and he eventually went on to found a company all around that and his implementation of SSH, but other folks have implemented SSH as well. This happens to be a version on Mac OS. OpenSSH runs on most of the major operating systems. There are also implementations for Windows. For example, PuTTY is a very good free SSH client. It's got a graphical configuration control panel thing that starts up and allows you to configure all your connection settings. There's a lot of other different things we can do with SSH, and some of those we'll get into in subsequent lessons. But that's just a little bit of a primer on SSH and a couple of different ways you can authenticate to remote systems with it. In this lesson, we're going to be talking about disk encryption. Disk encryption is actually something that was not really difficult to do, but sort of out of the reach of normal desktop computers for a really long time, although there have long been ways to do encryption of files and to a lesser degree maybe of entire disks. As we get faster processors, Certainly encrypting entire disks and being able to encrypt and decrypt on the fly without affecting performance is something that's certainly come within reach, and it's a feature that shows up in most modern operating systems to one degree or another these days. We're going to look at a couple of ways here of doing disk encryption, and I'm going to tell you about one of them first, and it's not one I can show you. With Microsoft, their Windows systems have this program called BitLocker. BitLocker requires either Windows Ultimate or Windows Enterprise. I don't happen to have either version, so I can't show it to you, but I can tell you that BitLocker has the ability to do entire disk encryption, and they use AES for their encryption cipher. And the thing about BitLocker is that they use a feature that comes with most modern systems, particularly laptops. They'll have this chip in them that's called the Trusted Platform Module, or TPM. The TPM chip, in part, what it does is it stores the keys that allow the operating system to be able to access the disk through this encryption and decryption process. And they use a pretty strong encryption cipher, which is AES, but you have to have one of a couple of different versions of Windows in order to be able to use BitLocker, and it's one of those things you would normally run in an enterprise, and so that's why they included it in the enterprise edition of Windows. Now, on the Mac OS side, they have this thing called File Vault, and you'll see I'm here in System Preferences, and I'm going to go to Security and Privacy, and I go to File Vault. Now, in this case, I happen to have File Vault turned on. If I wanted, I could turn it off. I'm not going to do that, but if it weren't turned on, I would have the little button there that says Turn on File Vault, and when I turned on File Vault, it would ask me about setting up keys, and I would have to set up keys and passwords. So the operating system handles this process by starting the encryption of all of the files on your hard drive, and it does this in the background. Now, you can get third-party extensions for some of these operating systems like Windows and Mac OS. PGP happens to have the ability to do disk encryption. And you can see that in the case of this Ubuntu system, they've got a package called GDEcrypt, which is a GUI that allows you to map and mount and create encrypted volumes. So I could run GDEcrypt and it would help me set up the process of encrypting the volumes that I've got on my system and doing the mapping and mounting. And if you're doing any sort of work with sensitive information like ethical hacking or penetration testing, you may be getting your hands on a lot of sensitive information that is owned by your clients. If your system were to be stolen or lost, then your client's data is now at risk. So certainly setting up disk encryption for yourself as you're working with clients and their data is a really good idea. But disk encryption, as I mentioned before, is now not only possible, it's very much a reality with current operating systems. In this lesson, we're going to be talking about cryptographic analysis. Cryptographic analysis is a technique that goes back a really long way. One of the techniques that I'm going to discuss here is frequency analysis, the distribution of letters. What you would do is take a large amount of text and you would figure out what letters were used the most. And as it turns out, that's been done. And you can see here, this is actually a frequency analysis of English letters just in common usage. So you can see that E has the most, followed by T, and then after that comes A, O, I, N, and so on. And J and X have the absolute least amount of use along with Q. So those are letters that you're not going to see very often. Letters that you're going to see a lot, E-T-A-O-I-N. So E-T-A-O-I-N, And then after that comes these letters. So what I've got here is a backwards cipher up above. I can do a little encryption here. Now I've just typed a little phrase there that's encrypted using the cipher that's up above. You can, of course, do the reverse since you've got the key, but you can see there that I've got the letter V that shows up 3 times. And using this frequency analysis, you may come to the conclusion that that's possibly an E. So if I suggest that that's an E, what I could do is this. And then I've got some other letters that show up a lot. I've got a couple of O's, and so I may be able to take some guesses as to what those letters are, and you start doing substitutions as you go through based on just this frequency analysis. Now that would be really easy for a substitution cipher if you had enough text. It would be even easier because you could actually do a frequency analysis on a large block of text and try to map it back to this chart here. And then you could start doing the substitutions until some patterns started to appear, and you may start to be able to fill in different things with good guesses about what different words are, at which point now you've got some others of the letters figured out, and so you can start replacing the letters that you've just figured out back into the text. It's a fairly time-consuming process, and for some ciphers, this sort of technique works. For other ciphers, like modern ciphers, this is not something that you're probably going to use just like this, although frequency analysis is definitely a part of the cryptographic process because we understand that these letters get used a lot, and so at some point some patterns may start to appear as you start digging through cryptographic analysis in ciphertext. So frequency analysis is definitely one method for doing cryptographic analysis, and it's a pretty important one. In this lesson, we're going to be going over different types of scans. So you'll hear people talk about scanning when we talk about ethical hacking. Scanning is often one of the first steps that you use in order to figure out what it is you're looking at and what the size of the breadbox is and what sort of tools you may need to be using in order to continue your ethical hacking activities. The first type of scan I'm going to cover here is a ping scan. Now, what a ping scan is just simply where you've got a utility that sends out echo requests to every system on a particular network or subset of a network so that you can determine which hosts are up. And I'm going to do just a simple ping scan here. And we're using Nmap for that. Nmap is a really handy utility for all sorts of things. And what Nmap is doing here, or has done, it sends out pings to every host on the network, and it's now showing the systems that it got responses from. There's a problem with ping scans. Sometimes systems are configured to block ICMP echo requests for the simple reason that they don't want to show up on the network. They figure that if they're blocking ICMP echo requests and they don't respond, it will just look like a black hole and that there's actually nothing sitting there, when in fact there is a system. Because of that, sometimes you don't want to do a ping scan, although sometimes it's useful just to do a quick ping scan and kind of figure out what's sitting out there. But don't assume that if you don't get a response from a system, that system is actually down. That's not necessarily the case. It could be blocking ICMP echo requests. You could also find instances where entire networks may be blocking ICMP echo requests inbound just simply for the reason of appearing to be black holes. And so if you can't be seen, you can't be attacked. Unfortunately, there are other ways of figuring out whether systems are up. If you've got a service or an application that is listening on the network because you need to provide a particular service, you can't hide that. So you may be able to block ICMP echo requests or pings, but you can't block requests to the open port. As a result, a different type of scan is something called a port scan. And a port scan is where we do connection requests to all of the ports on a particular system. And in the case of Nmap, you may do some subset of the 65,000 and some odd ports that are available on any particular system. Scanning 64K ports on every system can be very time consuming, and so Nmap has boiled it down to about 1,000 ports that it checks. The idea behind that 1,000 ports is you're going to hit the majority of applications that may be listening with those 1,000 ports. Sure, people can protect themselves by putting all of their services on completely oddball ports outside of that 1,000 port range that Nmap scans, but if you do that, then you're not going to be able to get people to easily come and make use of your services, which sort of defeats the purpose of having them to begin with. So a port scan, we're going to use Nmap again. And the type of scan that I'm going to be doing here requires administrative privileges. So again, you can see me using sudo here to run Nmap. And I'm just going to do a simple TCP connect scan. And I'm going to run it again on my entire network here. And what it's going to be doing is issuing a TCP SYN packet to all of the ports on every system on the network. Now, by default, Nmap will do a ping initially, and it won't follow up if the system doesn't respond with a ping. We can do something about that by saying, don't do the ping. But this is simply a TCP scan using Nmap. Every host on the network is going to get checked for the 1,000 or so ports that Nmap checks, and it's going to start returning responses with open ports on the network. A TCP connect scan is different from a simple SYN scan with Nmap because with a TCP connect scan, what Nmap is going to do is follow up a SYN ACK with an ACK and complete the three-way handshake. One reason you may want to do this is because if you start throwing out a whole bunch of SYNs and leaving a whole bunch of half-open connections sitting around on a network, you may get noticed. Now, it's possible you may get noticed with a TCP connect scan because it generates a lot of traffic, but what you're not doing is just throwing a whole bunch of SYN packets out and not following up, which is definitely something that's worth flagging. Just a lot of traffic may or may not be worth flagging for somebody, and so you may want to do a TCP connect scan in order to avoid detection, or simply just to be polite on the network and not leave those half-open connections around. And you can see that we're starting to get responses back here on some of the systems that have open ports. Another type of scan is a vulnerability scan. Now, there's a big difference between a vulnerability scan and the type of scans that we've been looking at so far. A vulnerability scan is looking for specific vulnerabilities on a system. Now, that doesn't mean that they go checking all sorts of exploits to see whether the vulnerability responds. What it means is we check things like open ports, and we check for applications and versions, and we check that against a database to see whether that particular version is vulnerable or not. If an application doesn't respond with a version, then we can't say for sure whether it's vulnerable. You can end up with a lot of systems that may potentially be vulnerable to a particular vulnerability, but may not show up in a vulnerability scan simply because the vulnerability scanner couldn't figure out the application or the version in order to check the database to see whether it may be vulnerable or not. So there's a downside to vulnerability scanning, although it's definitely a worthwhile activity and can certainly point you in directions that you want to be looking for as you continue through this process. Another thing that port scanners are useful for is to check for application banners to see whether there's a particular application running, and vulnerability scanners certainly use port scanners and do that banner grabbing activity. And port scanners can also check for operating systems and versions because of the way they get responses back from the targets that are being scanned. Vulnerability scanners also make use of that sort of information in order to determine whether they're vulnerable. So that's just a few different types of scans that you would be using as you begin ethical hacking. In this lesson, we're going to start taking a look at Nmap. Nmap is a program, and the name is short for Network Mapper. It's a port scanner. And what that means is it goes off looking for open ports on a system that you've pointed it at. And once we know what the open ports are, we can figure out what the applications listening behind those ports are. So although there is a graphical version, I'm going to be using the command line version in this lesson, in part because I want to start with the manual page, and on Unix-like systems like Linux, or in this case Mac OS, you can use a utility called man, which gives you the documentation or the manual pages for the application. In this case, we're going to look at Nmap. I have the Nmap reference guide here, and if I scroll down, I can see the different types of scans, and of course all of the various other options that I can specify on the command line. But right here we have scan techniques, and there's a number of scans that we can use with Nmap. And subsequent lessons will get into more detail about what each scan does. But just for basics, we have a TCP SYN scan. There's also a connect scan, an ACK scan. There are null scans, fin scans, and XMS scans. And the last three take advantage of different flag settings in a TCP packet. So Nmap by default scans about 1,000 ports or so, although we can scan all 65,000 with a particular flag setting. So if I were to do minus lowercase p 0 to 65535, that gives me the 65,536 ports that are available to both UDP and TCP. But as I said, by default, Nmap scans about 1,000 ports, and for our purposes here today, that's going to be adequate. I need administrative privileges in order to be able to do the scan that I'm going to be doing. So we're just going to do a quick little SYN scan, and Nmap can also make guesses about the operating system based on some information that it gets, including the sequence number handling and responses to certain packets like resets. So I'm going to have Nmap try to guess an operating system. And I'm just going to take a look at the default gateway. Although I could do the whole network if I wanted to, that would scan all hosts on my network. And there are multiple other ways of specifying host names, and again, we'll get into some more of those in subsequent lessons. But just for a basic scan right now to give you a sense of what it looks like and how it works, we're going to do this. I'm actually going to add a flag here, -v for verbose, so it can show you some more details about what it's doing. So Nmap has gone off, and you can see that it's indicating when it's found open ports, the activity that it's undertaking. There's an ARP ping scan, and there's a SYN stealth scan, which is what I had actually specified that it was going to do. The -SS was a SYN stealth scan. And we get a list of the open ports here. We have port 53, port 80, and port 443. It's taken a guess about the operating system that's running. It looks like it's running Linux 2.6. It actually can give you the amount of days that the system has been up. So that's some basics about Nmap. In this lesson, we're going to be talking about other types of Nmap scans other than the basic SYN scan, the connect scan, and the UDP scan that we've talked about a little bit previously. These are some different types of scans that you want to have in your back pocket in order to do some double checking in the case where you run across firewalls that may be giving you trouble in determining whether ports are actually open on your target systems or not. So the first scan we're going to talk about is an idle scan. It's called an idle scan because we use a system that's not actually doing anything in the way of network activity, and we appear to bounce messages off that idle system. What's really going on is we're checking the IP identification header of this zombie system or idle system in order to determine whether ports on a target system are open. So we send messages that appear to be from this idle system to the target system, meaning the target system is going to reply to the idle system, and then we can check the IP ID header to see whether it is incremented or whether it is not incremented. And based on that response or lack of response, we can determine whether ports are open. So the first thing I'm going to do is I'm going to start up a Wireshark capture. That way we can see what's actually going on here. You can see we're doing an idle scan using zombie 192.168.1.1. Not all systems can be used as zombie systems, so it may take a little bit of playing to find one that can actually be used here. So what we're doing is we're sending messages to my target, which is 192.168.1.22, and I'm spoofing my source address to be 192.168.1.1. So the 1.22 target host is going to be replying to the 1.1 zombie host, and then we're sending messages to the zombie host. That means we can't be tracked at the target. In order to be tracked, you would have to have somebody at the target get in touch with somebody at the zombie and do some sort of comparison in order to figure out that you were the one that was actually launching the scans. But the target can't actually see your IP address if you don't do any other sort of communication with them. All they're going to see is communications from the zombie host. So we've got our port scan back, and it looks like it's been pretty accurate. So I'm going to go back to Wireshark now. I'm going to stop the capture, do a filter here, so I can only see communications between my zombie and my target. So you can see I send a message to the zombie, trying to figure out what the IP ID is. And then I'm sending messages to the target here with a source IP of this spoofed IP. And you can see that Wireshark doesn't quite like this because it's flagged it as black, suggesting that that's not quite right. So we're sending a bunch of messages out, and then we check the IP ID here by going to the zombie host, and we check the reply over here. In this case, I see that my IP ID is 938. And again, it should have either incremented or not incremented based on whether the target system has sent resets back or not sent resets back or send syntax back, depending on the message that we're sending. You can see we're sending a lot of SYN messages to the target, in which case for an open port, we should get a SYNAC back, and for a closed port, we should get a reset, and if it's filtered, we should get nothing at all. So what Nmap is doing is it's doing all of this calculation of what the IP ID should be based on whether it's going to get a packet back at the zombie host or not. So it's doing all of these calculations on the IP identification header and trying to figure out whether ports are open. That's an idle scan. Let's take a look at an Xmas scan. Before I do that, I'm going to close this. I'm going to clear my filter there, and let's start up a new capture. Again, I need administrative privileges here. I'm going to do an Xmas scan, and an Xmas scan just lights up a number of the header fields in the TCP header. So a bunch of flags are going to be lit up. I'm going to do 192.168.1.22 again. And I'm going to send a bunch of messages to this target with a bunch of TCP flags that have been turned on that wouldn't normally be turned on in order to figure out what's actually going on at the target system and whether the port is open, whether it's filtered or not. So here's the messages that I'm sending. You can see I've got urge, push, and fin all turned on, and that would be an unusual packet to send. So I'm sending those out to see what response I get. And you can see some of the responses here. I'm getting a reset and an ACK back. And the reset would suggest that those ports are closed. So that's another type of scan that you can run. I'm going to close this one down. We're going to start another capture up. What I'm going to run here is a fin scan, and what a fin scan does is it sends a fin packet to my target, and again, makes determinations as to whether the port is open based on the response that we get. So I've done a fin scan on my target host. I've got a capture here. I'm going to filter out all of the other stuff. And I'm going to check my TCP headers, and you can see out of my TCP headers, just the fin flag is set. So that's a fin scan. I'm just sending the fin message. Again, you would use this type of scan if you want to check targets that may be behind firewalls or may have something else strange going on, and you want to just double check your SYN scan or your TCP open scan. You could run one of these other types of scans and see whether you get different results and maybe get some different ports that are open. So that's some other types of Nmap scans that you can run. In this lesson, we're going to be going over packet crafting utilities, one of which is a program called HPing. HPing is about a dozen years or so old. It's currently on version 3, and there have been several changes that have taken place in the course of those dozen years or so that it's been around. HPing is used for crafting packets, and that's sometimes a useful thing to be able to use evasive tactics to get around intrusion detection systems or firewalls, or sometimes it's good for just network troubleshooting. So we're going to run HPing and just bring up the help here. Here are the sorts of things that you can do with HPing. Now, up front here, we just have sort of high-level things where you get numeric output, quiet, packet count. You can show the version and, of course, the help. Down below is where it gets to be more interesting. The default mode for HPing is TCP, but I can also do raw IP mode, meaning I can craft any sort of IP packet or any protocol that sits above IP. I can do ICMP mode, I can do UDP mode. I can also do things like spoof the source address. I can set the time to live value, set an identification or an ID, and I can do things like splitting packets into fragments, set different things like the source port and the destination port and the window size. I can set all of these TCP flags like SYN, reset, push, ACK, urgent, etc. So let's do a little bit of packet crafting here. I'm going to set off a Wireshark capture just so we can see what we're doing. And since this type of activity requires administrative privileges, as usual, I'm going to use sudo here. So I'm going to run HPing, and there's my destination. Now I'm going to set the urgent flag, and I'm going to set the SYN flag. I'm going to set a source port of 55355 and a destination port of 8080. And you can see that I'm getting responses back with round trip times of around 1.8 milliseconds or so, somewhere less than 2 milliseconds for the most part. Now let's go back into Wireshark and see what we actually created. I'm going to do a stop. So I've got a fragmented IP. It's a TCP protocol. Wireshark doesn't really quite know what to do with this because it looks completely garbled. And you can see all of the messages that we've sent here. Even though it's TCP, we don't see a source or destination port because Wireshark isn't really sure what's going on because the packet just doesn't look quite right. So these sorts of packets are good for potentially evading IDS and firewalls, as I mentioned. They're also potentially really good at knocking over applications and systems and seeing if there's vulnerabilities there. Sometimes systems and applications don't do well with malformed data, and this is definitely malformed. That's hping. There are other packet crafting utilities. Another one is called packeth, and it's going to require administrative privileges as well, so I'm going to run it with those. And this is packeth, which is an Ethernet packet generator. This is unlike hping, which is a command line utility. This here is graphical in nature, which makes it easier to see the different things that you can set and the different variables. So with a MAC header, I can select an address, and in this case, I don't actually have one. So I'm going to leave all of that alone. I'm going to set a VLAN tag, which is the 802.1q, and I can make changes to the 802.1q VLAN fields. I can specify the next layer is going to be IPv4, IPv6, an ARP packet, or some user-defined packet. I can do things like change the IP version. I don't want to send an IPv4. I want to send an IPv5. I can change the protocol, which is the next set of headers, which is going to come below this. So I can change the protocol value here. And I can change all of the IP headers, basically. Everything that's available to set as an IP header is here. The next layer I can choose as TCP, and here I can set my source port and my destination port. And up above, I skipped over this, but it's sort of self-apparent where the source IP and the destination IP. Obviously, if I don't have a destination IP, I don't get the packets where I need them to go. I can set a TCP payload here. I can set a bunch of flags to anything that I want them to be. You notice here there's a pattern and a length. I can fill the TCP payload with a lot of data that's self-generated. So I could have a pattern of AB and a length of 500. If I did an apply pattern, it's going to fill the payload with all of that data. So you can generate a bunch of data automatically without having to do a lot of typing. Packeth also allows you to save a packet and then restore it later, which can save you some time. If there's a particular type of packet that you need to use on a regular basis against systems for whatever reason, you can save what the packet looks like and then reload it later. I can select the interface, and then I can just do send. In this case, I'm not going to do send, I'm just showing you what it looks like. But when I was ready and I had the IP address and everything in, I could just hit send, and when I was ready to stop, hit stop. So hping and packeth are both really good packet generating and packet crafting utilities. In this lesson, we're going to be talking about war dialing. War dialing is the idea of taking a whole block of telephone numbers and just dialing against them to see if there's a modem there. Now, you might think that modems are just really old school and nobody uses them anymore. The reality is that lots of enterprises and service providers even still use modems for out-of-band communication with their networking infrastructure. So if there's a critical error that causes networking to fail to those particular systems, at least they have a way to continue to communicate with them, even though it would be slow and you would also have to have a modem on your system in order to communicate with them. And as you may know, modern systems often don't have modems installed anymore, and modems can sometimes just be difficult to get, particularly with the type of interfaces that we've got on modern systems. However, there is still use in doing war dialing. There have been a number of war dialers that have been available over the years. Most of them haven't been updated in a long time, and it can be difficult to get your hands on them, and particularly it can be difficult to find a system that will actually run these older programs. For example, I am running Windows 7 as a virtual machine here, and I tried to download THC Scan, which you'll see here, and it won't actually run under the version of Windows 7 that I have. I get an error. But you can see there's a list here of the different war dialers that may be available. The first one is the classic DOS-based war dialing utility, and it's DOS-based. It can be challenging to get up and running, but it's kind of the gold standard in war dialing utilities. It's called ToneLoc. It may be difficult to get your hands on. You may have to do a little bit of digging to go find the program, and again, also find a system that may be able to run it. We've also got THC Scan and Phone Tag, which isn't quite as good as ToneLoc, and Phone Sweep. These generally run under Windows, or ToneLoc again runs under DOS. It's difficult to find scanners, war dialers that run under Linux, although if you've got a modem, you may be able to script that sort of communication and get a modem to just do the dialing for you if you know a little bit about modems and how to do dialing through them and how to interface. This is where THC Scan is available. Again, it came out in 1995 and it's at 2.0. It claims to run on all of these systems, but it hasn't been updated in a really long time. If you wanted to take a look at a movie on how to use THC Scan, you can certainly take a look at that through this website. Critical infrastructure across the internet is often attached to modems, and you may be able to get into routers or switches or even PBXs and be able to get in there and take a look at configurations and see what's available. Sometimes you can get in without passwords, or sometimes the passwords are really easy to get. And again, that critical infrastructure is out there and it is attached to modems. So having the ability to do dialing is something that you may want to have in your tool chest. In this lesson, we're going to be talking about IDS evasion. IDS is an intrusion detection system, and it's there to detect exactly the types of activities that we are engaged in. Sometimes you may be called in to work on a target where your activities aren't known and shouldn't be known by the operations people involved in monitoring and managing the network. The idea being, not only do they want to assess the technical controls that are in place, but they also want to assess operational procedures and ensure that systems and processes are working the way they are supposed to be working. When you are engaged with a target that you are in full cooperation with, you don't need to do these types of evasion tactics and techniques. But if you're asked to perform an assessment or a penetration on a target where they are not supposed to see your activities, then you need to know some different techniques to evade detection from an IDS. So we're going to talk about a couple of different things that you can do. So one thing that you can do is you can manipulate packets to look a particular way, and we've certainly looked at PackEth in the past. We're going to look at it quickly again because it's really useful as a tool to set up packets to look a particular way. One thing it can do is allow you to spoof IP addresses. So I could set a source IP address here that was something completely different from mine. Now, if I'm using TCP or UDP, I'm not going to see the response back, and in the case of TCP, I'm not even going to get the three-way connection made because the responses are going to go back to the source IP. But what you can do is, in addition to spoofing, you can set up particular ways that a packet may look by changing the type of service or by changing fragmentation offsets or different flag settings that may allow you through an IDS without maybe getting flagged. It might also allow you through a firewall. It's a slim possibility, but it is a possibility. Now, another thing that you can do is use PackEth to generate a lot of really bogus data. And what you might then do is hide in the noise generated by PackEth. So you could create some really bogus packets that are sure to set off IDS alarms, and then you can run some legitimate scans underneath and hopefully be able to get some responses back without being detected. So if we were to look at Nmap, I'm just going to look at the manual pages here. One of the things that I can do is set the throttle, in other words, the timing template, to go really slow. So if I do a -T0 with an Nmap scan, it's going to go really, really slow. If it goes really, really slow, there's a possibility it may not rise to the threshold that would trigger an IDS. And this is what we would call low and slow. Now, of course, this is only Nmap, and that would be a port scan. There's still a lot of other work that you would have to do, and you may have to find other ways to get around that. You can see also here on this page, there's some firewall IDS evasion and spoofing, and you can do things like fragment packets, where really fragmented packets sometimes will avoid IDS because an IDS is going to take a look at what's in front of it, and it may not have the ability to actually gather the entire packet and put it back together to take a look at what's going on. So sometimes fragmented packets can get through. You can also add decoys into a scan, and again, this is kind of doing the undercover friendly fire sort of approach, where Nmap will throw a bunch of decoys into the mix of the scan that you're doing, and hopefully you'll get lost amongst the decoys that are going on. I can also spoof the source address and do some other things around data lengths and TTL. I can also spoof MAC addresses and send packets with bogus checksums. So all of those have the possibility of getting around firewalls and IDSs and doing evasion. One of the downsides of using some of these techniques, and particularly the timing technique that we talked about a bit ago, is that you run the risk of really slowing down your work, which of course is a side effect of this type of approach where you have to hide yourself and your activities. But the thing to keep in mind is if you've got a limited time frame in order to perform these sorts of activities, you really want to keep that in mind and be aware of how long some of these techniques are going to take. So also under the line of friendly fire, you could do the spoof technique with a throttle of 5 and just throw a lot of really bogus traffic at your target while you're also running a separate Nmap scan with legitimate information. And again, hopefully you can get through underneath that friendly fire that's causing a lot of noise. Similarly, there is a tool called Nikto, and Nikto does web application testing. And you can see that it has some abilities as well. There are some IDS evasion techniques. So if you're doing web application testing and you need to do IDS evasion, what you can also do is throw a Nikto scan out and do it from another system. And again, you may be able to hide underneath the noise from the Nikto scan while you're doing some other techniques. Hopefully you can use enough of these sorts of tactics to hide yourself well enough to be able to get what you need to from your target without being detected by the target and the operations people there. In this lesson, we're going to be talking about banner grabbing. A banner is any message that an application provides. In the case of networked applications, which is primarily where we would be doing banner grabbing, a networked application would spit back a message, sometimes indicating the type of service that is actually running on that particular port on that server. In this case, I'm connecting to port 22 on my network, and port 22 is the SSH port. Now you can see that I'm running SSH 2.0 OpenSSH version 5.9 patch 1 on a Debian Ubuntu system. So this particular application has provided us a lot of useful information, which is of course the point of doing banner grabbing to begin with. You would do banner grabbing in order to figure out not only the type of application, which in most cases you could get from the port number. For example, if you connect to something on port 80, you can be reasonably sure that you are going to be getting a web server that responds to you on that particular port. Not always the case, but that's why we call them well-known port numbers. Now you can see that I used the application Telnet. Now, Telnet has a client component and a server component. And the server component is used to provide console access to remote users. The client can be used to connect to systems running Telnet as a server. However, it's also a good application for just simply doing a TCP connection. And as I did earlier, I'm going to connect back to this particular system. You can see I'm connecting to a host. That's the 192.168.1.39, and that's on port 22. Now, if I took that port number off, it would default to port 23, which is the Telnet port. I'm going to do 22 in this case, though, and that gives me my SSH connection. Now, I can do this on a number of different systems or different service ports. For example, I could do this to the web port. So in this case, I'm just typing raw HTTP, and I'm getting a message back. And if I scrolled up here, I could get the server name and version. In this case, it's Apache running 2.2.22 on a Ubuntu server. So again, we've got some information about a particular service that's running on a particular port. So Telnet, again, is really good for connecting to systems that are running TCP. And you can connect to particular ports and interact with them manually because, again, Telnet's a console application. Telnet is also available on pretty much any system that's running TCP/IP. Now, current versions of Windows, you have to go through a few extra steps in order to get the Telnet client installed. But it's pretty easy. You just go to the Programs control panel and you go to Add or Remove Windows Features, and you can go find the Telnet client and just add the client there. In this case, I'm running this on a Mac OS system. It's available for Linux. Like I said, pretty much any system running TCP/IP, you can find a Telnet client for. So it's pretty ubiquitous, and therefore it's pretty good to use for these types of banner grabbing applications. I can also use a utility called Netcat, and I'm running that here. NC is Netcat, and I'm doing -v for verbose, and I'm actually going to connect to infiniteskills.com, and we're going to connect to the web server. So I got my connection. It succeeded. It says on port 80, TCP, HTTP. In this case, I'm going to do a head rather than a get. And I'm using version 1.1 of the HTTP protocol, which means I have to specify a host. And then hit enter again, and it's running Apache version 2.2.3 on a Red Hat server. And it's running some different modules here. So again, you can see where we can get all sorts of useful information. Sometimes it's useful to be able to connect to mail services or mail service ports and figure out the type of mail server that is running there. So in this case, I want to figure out what the mail server is. So I'm going to go back to our old friend Dig. I'm going to do dig mx, and I'm going to do microsoft.com. And here it's mail.messaging.microsoft.com. I can see in my answer section. So I am going to mail.messaging.microsoft.com, and I'm going to connect to the SMTP port or the mail port here. And you can see I've got a connection that succeeded. Now you can see it's responded. It's the Microsoft eSMTP mail service ready. So that tells me that they're running the Microsoft SMTP server, which is probably Exchange. So I can also do another one here, digmx for sendmail.org, and sendmail is a different type of mail server. So I can connect to services.sendmail.com, and that again is on port 25. Now I've got my connection, and you can see I've connected to a server running SendMail 8.14.5. So again, I've got some useful information there about not only the service, in this case a SendMail application, but also the version number. So this is all well and good for clear text protocols like we've been using so far, HTTP, SMTP. SSH is a protocol that has encryption as part of it, but the banner I got back just simply from connecting to the service, which didn't require encryption. So we want to know how we are going to connect to systems that are using encryption, so web services, for example, that have encryption as part of them. So I can use the OpenSSL program, and the component that I'm going to use is the secure client. I'm going to tell that to connect to infiniteskills.com, and that's going to be on port 443, which is, of course, the HTTPS port. So it's going through the SSL handshake. It's giving me information about the negotiation that happened. The server public key is 2048 bits, and I'm doing TLS version 1, SSL version 3. The cipher is DHE RSA AES 256. So pretty strong cipher there. So not only am I going to get information about the service here, but I've also got some information about their encryption capabilities as well as the type of certificate that they're using. I'm doing a TLS version 1 protocol. Again, it's got the cipher there, and I've got information about the master key. And again, I'm going to plug in the host information. And same thing here because it's the same server, Apache 2.2.3 running on a Red Hat system. And I've also got some information here about the PHP version. So they're running PHP as a scripting language. That's a plugin that's being used with Apache. And I've got some version information about the PHP plugin that's being used. So you can see lots of different ways of pulling banners, whether it's encrypted protocols or unencrypted protocols. If you've got an encrypted protocol that you need to communicate with, you can use OpenSSL, and their S client will do that protocol negotiation for you if it's SSL or TLS. So that's banner grabbing. In this lesson, we're going to be talking about vulnerability scanning. Vulnerability scanning is, as the name would suggest, an attempt to find vulnerabilities on target systems. So we scan, or we send a lot of messages out to these target systems to figure out what sorts of vulnerabilities they have. There are a number of vulnerability scanners on the market. Vulnerability scanning goes back to the mid-90s or so with a project called Satan, which ran on Unix systems. Since then, there have been a fairly large number of vulnerability scanners that are available. I'll show you a couple here just to give you a sense of what's available. In subsequent lessons, we'll focus primarily on using Nessus, which you see here. What vulnerability scanners do is they probe for open ports. They do some banner grabs, try to figure out what versions are running. They also check operating systems. They'll check to see what services are available and, again, what version number that those services are running. So here's a login for Nessus. It's by Tenable Network Security. Nessus has long been a pretty well-respected vulnerability scanner. They do have a home feed that's available. It's free to use on your home network. The downside to the home feed is it's several days out of date from the professional feed. The professional feed is still a pretty reasonable price, though, compared with some of the more commercial offerings. There is another vulnerability scanner on the market that is available for free. That's the Nexpose community version, and you can use this to scan up to 32 IP addresses. That means you can scan 32 IP addresses. It will maintain 32 IP addresses in its database. If you want to scan more than that, you've got to delete the hosts, which can be a bit of a pain. Although if you're on a budget, you can certainly make use of this Nexpose Community Edition. Again, you can use this for commercial use up to 32 IP addresses, where Nessus offers you a free feed, but you can't use it for commercial purposes. So there's some slight differences there. One of the popular commercial offerings is Qualys Guard from the company Qualys. They do a lot of different things in terms of vulnerabilities and checking for malware, and it's a pretty comprehensive suite that they've got available. One of the downsides to vulnerability scanning, though, is you can't guarantee that a vulnerability actually exists based on a vulnerability scanner because, again, it's going on version numbers where it can find them in banners and all of those sorts of things. You can either hide or you can spoof them or do various other things to protect against these vulnerability scanners. So a vulnerability scanner can generate both false positives and false negatives. Just because a vulnerability scanner gets a result that suggests that you don't really have any vulnerabilities or many vulnerabilities doesn't necessarily mean that you do or you don't have a significant number of vulnerabilities, because the vulnerability scanner is making its best guess based on the information that it has. The vulnerability scanner does not go out and attempt to exploit these vulnerabilities to make sure that they really exist. That would be kind of bad behavior. So it does take a skilled user or a knowledgeable user to go through the results from these vulnerability scanners in order to determine whether the vulnerabilities exist or not, and whether the criticality types of severity or criticality that the scanner uses in order to quantify the vulnerability, whether you agree with that particular severity or criticality. You may have some sort of remediation in place that protects these systems. An example is if I provide credentials to a vulnerability scanner, it can log into the system and check for local vulnerabilities. And one of the things that a vulnerability scanner may come back and say against a Linux system, for example, it may say, hey, I can figure out all of the packages on your system. Well, congratulations, you are already logged in. That's something that anybody who's logged in can do, but you have to be logged in order to be able to get that information. So they may rate that a high severity because you can get packages and versions, but again, you've got to be logged in. So if you've got a strong password policy and you check against that on a regular basis, and you also do regular auditing of your users, that may be enough of a remediation or mitigation that you can say, hey, Nessus or Nexpose, you think that's a big deal, but I really don't. I think it's a low risk, even though you rate it higher. So again, it takes knowledgeable people to go through these reports and figure out whether the severities are really ones that you would agree with or not. So that's vulnerability scanners. Again, in subsequent lessons, we'll go through in more detail how to make use of these vulnerability scanners. In this lesson, we're going to be going over using Nessus to do vulnerability scanning. You can see that I'm logged in here to the Nessus web interface, and through this web interface, you can do all of the management of Nessus and start your scans and configure your scan policies. You can see here I've got a test scan running against a system, and I'm doing that in order to cut off some time here so I can show you a report once the scan is completed. In the meantime, let's go off and take a look at the different policies and how you would build a policy in order to do scanning against systems. You'll see here there are 4 policies that are in place, and these are ones that have been distributed by Tenable, and they're just built into Nessus. You can create new policies, you can modify the ones that are there, let's do an add a policy here and call it my policy. It's a private visibility, and I'm just going to add a description saying my policy for testing purposes. So you can see the different types of settings here under just the general tab. So for scanning, I want to do safe checks, which means I don't want to do anything that could potentially take a system down. If you were doing testing against a system where it didn't really much matter whether you knocked it over or not, you could uncheck this. Let's do an uncheck here. I want to log scan details to the server, so all of the scan details are going to be logged on the Nessus server. I can avoid sequential scans. I can consider unscanned ports as closed. I'm going to leave the TCP scanner off and just use a SYN scan. I'm not going to do a UDP scan because it takes a really long time. An SNMP scan, we're definitely going to do. We're going to check for SSH. We're going to ping. I'm going to change the default port scan range from the usual to 0 to 65535, which is all of the ports that are available. Under credentials, I can change Windows credentials or SSH credentials. As mentioned previously, if I add credentials, Nessus will log into the system and check for local vulnerabilities. You may want to do that type of thing if you're doing a white hat hack or an ethical hack where you've got complete cooperation from your target and they provide you credentials. This is a really useful thing to do, and just have Nessus run the local scans for you. So again, I can do Windows SSH. If you've got Kerberos configuration, you can do that. Here's some clear text protocols. So if you're using Telnet or RSH or RExec, you could have Nessus use credentials for those things as well. Here's all of the plugins. Normally, they would all be enabled by default. So we've got 49,340 enabled plugins. You can disable them as you need based on the type of scanning that you're going to do, but frankly, Nessus is pretty smart about what plugins it runs, so it doesn't have any harm in having all of them enabled. If a plugin doesn't make any sense at all to run, it's not going to. But if you had a specific thing that you were looking for, if you were just going to check databases, you could, for example, disable all and then just turn on databases. So it would check all of the plugins that it had for database vulnerabilities. I'm going to go back to enable all though. Now we can go to preferences, and there's a number of different preferences that you can set. You can do an HTTP login page. So if you've got a login page on a web server that you know is out there, you can set the login page in the login form and the different form fields that are used to do the login, and then set the credentials on that. I can do LDAP checks. There's some login configurations here, different settings for the Nessus SYN scanner and the Nessus TCP scanner, and a wide variety of other things. I can do SMTP settings so we can check things like open relays, SNMP settings. We'll get into SNMP in other lessons, but here's different settings that you can use in order to do some SNMP probing. Web application tests. You can either enable or disable web application tests. I'm going to enable it here in this case. And you can do other different things. I can check for HTTP parameter pollution just to see if I can get the server to do something funny and respond. So I'm going to submit that. And you can see my policy was successfully added. So in addition to the 4 default ones, there's now my policy. So I want to launch a scan using my policy. So I'm going to go to scans, and you can see the scan that I've already got running here. Looks like it's still running along. I'm going to add one. I'm going to call my scan. I can run it now, or I can do a schedule if I want it to start in the middle of the night when I'm asleep, for example, in order to not interfere with my Netflix streaming from home, or if I want to protect the client and make sure I'm only scanning during a maintenance window, I can set up a schedule. Now I need to select the policy. So we just did the policy. I'm going to do my policy. I could do a targets file, which would be a list of host names or IP addresses in just a text file. I can look for that, or I could just do 192.168.1.22, and I can launch my scan. Go over to reports here, and the test scan is completed. So I can open up my report, and I can see all of the different vulnerabilities that were found. I don't have any high-risk vulnerabilities. I did find that the SSL server certificate cannot be trusted because it's self-signed, and I can pop that open and get a description of the vulnerability, and again, what Nessus says that vulnerability is. And it looks like I found it on 2 different ports, 1241 and 8834. And I can do the same thing here. That's a self-signed certificate. So as I click down through the different lists here to see what I've got, it has in the middle the host and the port. And if there are multiple ports or multiple hosts, if I were scanning multiple hosts, I would see that. I've got an Apache Tomcat servlet running on port 8080, and Nessus believed that's a medium severity or a medium risk factor. And once I'm done looking at that, I can close it, and we go back to this view here. Looks like I've got IP forwarding enabled, and I've got some informational ones here. The Nessus SYN scanner just came back with the list of ports that it found that were available. It says under synopsis, it's possible to determine which TCP ports are open. Again, this is simply informational. If you are offering a service, obviously you want that service to be available, so the port should be found to be open when somebody attempts to connect to it. So that's as you would normally expect it to be. If you were to find some ports here that you wouldn't expect to be open, like this 1241 looks like an oddball port to me, and so that may be one that I go take a look at and figure out what it is and why it's open. We can close this down and go back to our list. This displays the SSL certificate. Looks like this is a Nessus certificate. Nessus Users United is the organization. So there's that certificate, 8834. Looks like a Nessus certificate as well. So there's a couple of different Nessus ports that are open, and Nessus found those. So that's the different types of things that you can do with a vulnerability scanner, and particularly with Nessus. In this lesson, we're going to be going over enumeration techniques. Enumeration techniques are ways of getting information from systems, specifically information like the versions and the types of applications that are running on those systems. This information can be critical to determining whether there may be vulnerabilities that could be exploited and whether those systems are at risk or not. So there's a number of different ways of doing enumeration. One of the ways is just simply doing banner grabbing. We can do things like telnet www.infiniteskills.com, port 80. I'm going to grab the head, and I can do some banner grabbing in that way. They didn't like that, but I can check for banners using something like telnet. And we've gone over banner grabbing in the past. That's a really useful technique for doing enumeration. We can also do things with DNS, which is really helpful. So I could figure out who the name servers for a particular domain is. And I've got this name server here. So I could do dig at this name server, and I want to do infiniteskills.com, and I want to see if they're vulnerable to domain transfers. So that failed, but that's another way of doing some enumeration. You want to get lists of the different types of hosts that may be available in a particular domain. So doing a zone transfer may be something that you would want to do. Another thing you can do is at this same name server, I'm going to see if I can get the bind version if they're running bind. So I'm looking for a particular object called chaos, and I want the text back, and the text I want is the bind version. So let's see if I get that. And what I get is DNS made easy anycast. That appears to be the version or the DNS server that's running. I'm getting DNS made easy anycast. So I can check other servers. This is a non-authoritative name server that's available on the internet, and I can do the same thing. And this tells me if I have a legitimate reason for requesting this information, please contact the host master so that I can get it. So that's interesting. Now I know that level3.net happens to own 4.2.2.1. I happen to know that previously, but if you didn't, now you know. So that's a different type of information that you can get from using enumeration. With different systems, you may want to enumerate users. You may want to get the users that are on a particular system. And there may be different ways of doing that. You may be able to do that using LDAP queries against Active Directory servers. You may be able to use built-in Windows commands to do this type of enumeration. One of the Windows commands that's built in that you can use for this sort of thing is netview. And I haven't actually provided anything here. I just want to see what kind of information I'm going to get back. It may go out and probe and just tell me what's going on. So I've got the list of servers for this workgroup is not currently available, so there's no domain controller or server available for the workgroup that we are part of. Now I could do something like this. Let me resize this so we can see everything here. I've got my IP address here, so I could run this against myself and do netview 192.168.1.27, and I get no entries in the list. But net is a helpful command, so I could do things like net accounts, net computer, net config, net continue, net session. Net is a way to make use of the SMB protocol in Windows and connect to other systems on the network. With netuse, I could set up a share. So if there were another Windows system on my network, I could netuse and map a share on that other system to a particular drive letter on my system. So I could use netuse to map somebody else's system to a drive letter on mine. So net is a really useful command that you could make use of to do some probing on a network that has Windows systems. In this case, you can see that there's a list price associated with it, and if you find it's useful, then you could certainly get the server resource kit. And the resource kit comes with a lot of different utilities, and some of those utilities give you the ability to do some deeper probing on Windows systems, and you can figure out what's going on and see if there's information that's available. One of the things that you'll find on several Windows systems in Windows networks is they have something called null sessions available. And what a null session means is you can connect to that system using no authentication, so no user and password. And even though you have no user and password, it will still provide you information, maybe about the types of shares or the share names, rather, that are available on that particular server. Sometimes with null sessions, you can get usernames, you can get the computer name, of course, and you can get the domain or workgroup that's associated with that particular computer. So sometimes, even though you haven't provided a username and password, you can get some really useful information from Windows systems and Windows networks. Certainly, there are a lot of different enumeration techniques that you can use to gather information that you will be needing as you continue going through this ethical hacking or penetration testing process. In this lesson, we're going to be talking about SNMP. SNMP is the Simple Network Management Protocol, and not surprisingly, it's used to manage network devices. By manage, I'm talking about extracting information and also sometimes setting configuration parameters. The Simple Network Management Protocol currently has 3 versions, started with version 1 that has been superseded for several years now, although it's still the predominant version that you'll see when you run across SNMP in network devices. Version 1 was very insecure. One of the reasons for that is it lacked any ability to do encryption, so there was no privacy involved with the communication between a system running SNMP and the server that it communicated with. So there was no privacy, no encryption, no ability to protect the information that was being transmitted. As you'll see shortly, there's a lot of very useful and important information that can be communicated over SNMP. And of course, there's also the ability to have SNMP set configuration parameters, and that can be really interesting and useful information as well. So on top of the lack of encryption, there was no real authentication involved in version 1. The way you authenticated with version 1 of SNMP was a concept called a community string, which is barely a password. And the community string was used to tell the SNMP system that you knew what this community string was, and so you were authorized to communicate with it. The problem with that idea, and why I hesitate to use the word authorized, is that typically the community strings with SNMP version 1 were well known and defaulted to the words public and private. The community string public referred to the ability to gather read-only data, meaning you could get information from a system running SNMP, and private was for write access, meaning you could set configuration parameters. So let me show you a way to get information from a system running SNMP. So I'm doing an SNMP walk, which means I'm going to connect to a system running SNMP, and I'm going to walk through the MIB, and the MIB is the management information base. And so SNMP walk is going to connect to this system, and it's going to pull all of the information that it can find from the system that's running SNMP. So I've just done an SNMP walk, and you can see all of this information. You'll see here on the left-hand side it says SNMP version 2 MIB, means the management information base is a version 2. You can see the description here. I'm running a Linux system, and it's running kernel version 3.2.0. It's also a Ubuntu system with a symmetric multiprocessing kernel. So there's some really interesting and useful information. I now know the kernel version, and I can look up vulnerabilities against that kernel. So that's really helpful information to have, again, which is why SNMP is a good protocol for extracting information, and why version 1 is so insecure that you can just connect using the community string public, which you saw me use. It's well known, it's a default, it's what lots and lots of systems use just because it's easy, and as I said, it's well known. Using that one community string, I can connect to this system and get all of this information. You can see all of these other variables that it's got, including system uptime, the system date, and right down here towards the bottom, you can see the boot image. So I know what file and the name of that file that was used to boot the device with. And sometimes that may provide me some additional information. The UUID of the system, the number of processes and the number of users, and a variety of other pieces of useful information. So as I said, SNMP version 1 is the predominant version that you will see out there. There have been 2 additional versions, and some intermediate changes in those versions as well. So we've got version 2, which tried to fix some of the problems with version 1. And finally, we have version 3. And with version 3, we finally get some stronger authentication and some encryption, although there were versions of the version 2 protocol that tried to fix some of those issues as well. But as I said, version 1 is kind of the one you're going to see a lot of because it's the one that's been out there for the longest. It's the one that all the vendors support. It's the one you're guaranteed probably to have systems be able to talk in. And so I think a lot of people find that it's just easier to go to version 1 and they don't really think so much about the security implications of using version 1 of this SNMP protocol. If just these lines of text are a little overwhelming for you, I can show you a graphical way of getting the same information. Here's a program. It's written in Java. I'm running it in a virtual machine, but running this under Windows. And as it's Java, it will run under just about any platform that will support Java. So I've got my server address up here, and that's the system I'm going to be connecting to. And you can see on the left-hand side, it's got a tree view of the management information base. And again, the management information base is the way that data in SNMP is described and stored. So I can open this up, and I can open up the system, and I can get the sys description. And you see the result table on the right-hand side. I've got the value again, which is the same that we saw before. I can get the object ID and the uptime, which is 11 hours and 32 minutes and 34 seconds. And then I've got my contact and name and location. And since the system I'm querying here is just kind of a default installation, I didn't spend any time actually putting a lot of data into it and making sure there were a lot of MIBs involved. If that particular MIB was installed on the system, I could get the number of interfaces, and then I could get information about the interfaces. I could get the interface type, the speed, the physical address, the status, and the number of packets and octets that have flown in and out of that particular interface. I've got information about TCP and UDP, and then I've got a lot of information about the devices that are attached, and of course the storage as well. So if I open up the storage table, I can show you the types of information that's there. So I can see the amount of disk space that's used. I can see the size of that storage. Here's a lot of different pieces of information that would be really helpful and useful as you're trying to extract information about your target. If you find systems that are running SNMP, that's a pretty great find, and you can pull a lot of information. And as I suggested earlier, some of these different parameters have the ability to be set remotely using SNMP as well. So in addition to just pulling the information, you can set different parameters and change the configuration of the running system using SNMP. So SNMP, pretty powerful information tool and a great way to get information about your target systems. In this lesson, we're going to be talking about LDAP. LDAP is the Lightweight Directory Access Protocol. When I'm talking about directory, I'm not talking about a folder in a file system. We're talking about a different kind of directory. We're talking about something along the lines of a phone book or a contact list. We're talking about that type of directory where it's basically a way of storing a lot of information in a way that can be found quickly and easily. In the case of LDAP, for the purposes that we're going to be talking about, one of the big things that you're going to be looking for with LDAP servers is a way of storing information about users, systems, printers, and other resources on a network particularly in a large enterprise environment. The reason for that is several years ago now, Microsoft moved to an LDAP model to store information in their Windows Server family. That became the way that they were going to move forward in managing their network and their systems. And you've probably heard of Active Directory. Active Directory is an implementation of LDAP. It's sort of like a database in that it stores information and we can query it easily. The difference with LDAP, though, is it's hierarchical in nature, and part of that comes from the fact that LDAP is lightweight. You'll see the word lightweight in Lightweight Directory Access Protocol. It's lightweight because it's a subset of a larger set of protocols that are related to X.509 certificates. And let me show you something quickly here. I'm going to connect to a server that's running LDAP, and I'm using a tool called JExplorer, running on a Mac OS system, although JExplorer does run on other systems as well. And there are certainly other tools that you can find that will connect to LDAP servers, and I'll show you another one for Windows shortly here. You can see here in the connection dialog box, I can select the protocol that I'm using. I'm going to use LDAP version 3. I can change my base DN, and the DN is distinguished name. So I'm not going to change my base DN. I'm just going to let JExplorer pull everything that it can. I'm going to connect with anonymous access, meaning I'm not actually going to authenticate. I've got a choice here of anonymous user and password, SSL and anonymous, meaning it would be encrypted. So the way I'm going to connect is completely unencrypted, which means anybody who has access to this network that I'm sitting on with this system could extract this information and see what's being passed forward. And in this case, they're not going to see an awful lot, because the LDAP server that I've got doesn't have a lot in it, just a simple LDAP server that's sitting there so that I can show you how to connect to it and how to get information back. But if I were to use this to connect to an Active Directory server and it allowed the connection and pulled information back, not only would I be able to see that without this encryption, but anybody else who had access to the network could potentially see it as well. I could also do encrypted plus authenticated, but in this case, I'm just going to do anonymous, and I'm going to connect. So I'm connected now, and the hierarchy on the left-hand side here, and I'm just going to show the attributes here on the right-hand side. You can see the common name here is administrator, and there's a description and an object class. And I could go to the table editor, and I could make some changes here if I wanted to do that. So I could set a password, and it would let me do that. Here's the organizational unit, the OU, and I could say, for example, IT. Here's the address and postal code, and I've got a fax number. So there's all sorts of information that I can set here for this particular object with the common name of admin. I haven't set a password. Looks like that's required. I'm not going to change that now. We can take a look at the directory schema. I'm going to discard those changes. You can see the directory schema here with all of the attribute types that are available, and there's quite a number of them. LDAP syntaxes, matching rules, and here's all of the object classes. You can see there's an application entity, an application process, a bootable device, certificate authority, country, IP host, IP network, IP protocol, and here's a person. You can see that a person must have a common name and a short name. and it may have a description and a see also, a telephone number, and a user password. So there's lots of information here, and you can see all of the information in the schema, which is similar, again, to a database, where a database has a schema defining the data that can be stored in it. Same thing here with LDAP. This LDAP server has a schema defining the data that can be stored in it as well. So as I said, LDAP is implemented in Active Directory, and so if you could make a connection to an Active Directory server with this, you may be able to get a lot of useful information from it, particularly if you were able to do username and password. If you can do an anonymous connection, you may be able to get some minimum amount of information if the system or network is properly implemented. With a username and password, you should be able to get a fair amount of information back. Another tool that can be used to connect, and this is under Windows, you can find it on the internet. It's called LDAP Miner. LDAP Miner is just a command line utility, and if I were to connect, I would just do LDAP Miner -H and the host, and in the case that I've just done with JExplorer, we used 192.168.1.39, so if I were to run LDAP Miner, it would be LDAP Miner -H 192.168.1.39. I would use the default port, and unless I had something specific that I wanted to look for, I'd probably use -D to just dump all the data that I could grab. So that's a tool that would run under Windows, and that would be able to extract the same sorts of information in a textual format or a text-based format, where we had JExplorer over here that was able to do it in a graphical format. So that's the lightweight directory access protocol, and Windows servers running Active Directory aren't the only kind of servers you'll run across. Active Directory servers, definitely good targets, but don't expect that that's the only type of LDAP server you're going to run across. You'll find LDAP servers storing all sorts of information. LDAP is a really useful way of organizing a lot of data about people and resources. And that's the lightweight directory access protocol. In this lesson, we're going to be talking about using proxies. A proxy server is where the web browser will actually send the request for web pages to a proxy server. The proxy server will make the request to the actual server on behalf of the client and then send the messages back. There's a number of different reasons to use proxy servers. Sometimes it's just to conserve internet bandwidth because the proxy server will cache the responses if it's possible, and the next request to that particular website will generate the cached response being sent back to the client rather than going back out to the internet. So what the proxy server will do will be just a quick probe to see whether anything's changed, and if nothing has changed, the content will be sent back from the cache rather than doing another request to the internet and the network, and as a result, you'll get some bandwidth savings. Another reason for using a proxy server is you may want to do some blocking of sites, and if you force all of your users to go through a proxy server, that proxy server can protect against users going to malicious sites, or in the case of enterprises, sites that may be not particularly constructive or conducive to them getting their work done. So we can block access to different websites using proxy servers. We can also use a proxy server to insert an antivirus solution in the middle of the web communication stream. Since websites are becoming more and more vectors for virus activities or just different types of malware, we may want to use an antivirus solution in the middle of our web stream, and so we can do that at a proxy server. The proxy server would check incoming traffic and see whether there's malicious software or malicious data there as well. So I'm going to show you the use of a proxy server for a different purpose. We need to configure Firefox to use the proxy server. So you can see here I've got my proxy settings. I'm going to use one on my local system. It's at port 8080, and I'm going to use that for everything. So I've got my proxy server all set up in my web browser, and this happens to be my proxy server. And you can see Firefox is already sending traffic through the proxy server. Another good reason for using a proxy server, and we will certainly get into this later on, is maybe I want to intercept requests and do some manipulation of them. So I've done my browsing to Infinite Skills, and you can see under sites here, there's the site Infinite Skills, and here's all of the pages that were requested. If I click on one of them, I can see the request and the response. If I needed to do some debugging, I could use a proxy server and actually grab everything that was going on and see what's happening between the client and the server. I can also do some banner grabbing here. This is kind of a heavyweight solution for banner grabbing, but certainly you can see the server line right there in the response, and it's got information about the web server that's being used as well as the operating system and some different modules that are used on Apache. So I can see all of the different requests that are going on. Also with a proxy server, as I noted before, you can see different things that are going on under the hood. Even though the only website I actually went to is infiniteskills.com, Google Analytics was also hit, which probably came from Infinite Skills. The other website here that you can see is safebrowsingcache.google.com, and that's something that Firefox does without you knowing. It goes out and checks this safebrowsingcache.google.com. Depending on the different types of plugins you may have installed in your browser, there may be a lot of web activity going on without you being aware of it, and Firefox or Chrome, or in some cases Safari, maybe Internet Explorer, will be sending lots of requests out to different servers. Firefox is one of the biggest ones that does this type of activity without you realizing. So if you were to install a proxy server like this Z attack proxy from OWASP, then you could see everything that's going on without you being aware of it. So this gives you some measure of information about what's going on. There are a number of different types of proxy servers that are available. You'll see Blue Coat proxies, and a popular one on Linux, which is open source, is Squid. And Squid is just a regular HTTP proxy that will do caching, and you can also get different plugins for content filtering. So that's how you would use a proxy and the different things that you would use a proxy for. In this lesson, we're going to be talking about using Tor and different anonymizers. One of the reasons for using an anonymizer is if you're doing information gathering about a target and you don't want the target to know that you're doing it, something like a red team approach where you've been asked to quietly go in and assess a network so the operations folks don't know that you're coming. You may want to hide your activities as much as possible, and so you may want to use something like Tor or another anonymizer to be able to get information about the target without it being connected back to you. So let's talk initially about Tor. Tor is the onion router, and it's really a network of a lot of different people, and they use virtual tunnels in order to connect all of those people. And the idea behind Tor is to give you privacy and security. Tor protects against traffic analysis. So your activities can't be tracked on the internet because they don't actually trace back to you in any way. So we've got the Onion router here, and you can see the Vidalia control panel, which is the piece that actually connects to the Onion router network. And I can show you the network here. I can do a view of the network, and you can see all of the different relays here on the left-hand side that are connected, and how long they've been up, their bandwidth that's available, the platform they're on, and the last updated. So there's a lot of information about the different relays that are being used. You can see at the bottom here, there's 1,704 relays online. I could set up relaying and become a relay myself, which would help the network grow. I can use a new identity. There's a message log and, of course, a bandwidth graph. And here's the Tor browser, which is just like any other browser, except it's configured to run through the Tor network. And you can see my IP address appears to be 77.247.181.163, which is not my real IP address. So that's the IP that I appear to be getting from the Tor network. So I can go to a website now, and we're just going to go to infiniteskills.com, and you can see here that the browser works just like any other browser, and Infinite Skills is going to see the IP address that the Onion router network provides me when my request exits that network in order to connect to Infinite Skills. This is sort of like a proxy in the sense that I'm not the one who's actually making the request when it hits the internet. I'm making a request to the Onion router network via this web browser, and something on the other end of the Onion router network is going to be sending that request on, and the response from Infinite Skills is going to be sent back to that relay, which would in turn come back to me and into this browser. So in that sense, it acts a bit like a proxy. And again, the idea is that you want to be anonymous and hide your tracks as much as possible. One of the anonymizers that you can find is this at Kotze.net, and Kotze is Church of the Swimming Elephant. And you'll find that a lot of these anonymizer services are pay for. What the folks at Kotze provide is private email service, SSH tunneling, and privacy proxies, much like the Onion router network. They also do virtual private networking and professional web hosting. And as it says here, all of their services hide your IP address. Another anonymizer is this one at anonymizer.com. They have services for businesses as well as for home users, and you can see here that these are pay-for services as well. While you may be able to find a lot of different anonymizers, you probably want to be a little bit careful about the types that you connect to, simply because, like any other service on the internet, you may end up finding rogue anonymizers whose purpose is really to seed you with malware, which isn't to say you should stay away from them altogether. Just be careful that you know what you're using and that they're clean from malware or other rogue purposes. So that's the Onion router and anonymizer services. In this lesson, we're going to be talking about tunneling. Tunneling in this case has to do with taking a bunch of data and stuffing it into another kind of data to get it from one point to another. So much like a real tunnel, in going through the tunnel, you can't be seen from above. You would actually have to be inside the tunnel to see what's there. If you're tunneling data, you can't see what's inside the tunnel without actually tearing the tunnel apart or digging into it. Now, there are a couple of reasons why you may want to tunnel. One of the reasons is you may want some privacy where the data that you're sending, you don't want that to be seen. Another reason why you may want to or need to tunnel is if there are restrictions on the network, like a firewall, for example, that prevent certain types of data from either entering or exiting. You probably need a tunnel to get that data through. Now, there are a few different ways to do tunneling. I'm going to talk about a couple of them here. One of them is we're going to go back to our old friend SSH. SSH is capable of doing tunnels. Now, there are a couple of different kinds of tunnels that you can do with SSH, and I'm going to do just some simple port forwarding here. When I connect to a port on one side, the traffic is tunneled through the SSH connection and let go on the other side, where it goes to a destination that's configured ahead of time. So I'm going to set up this SSH tunnel, and I'm going to go to my little standby Linux server. Now here's where I set up the tunnel. I'm going to say connections to local port 2300, and I'm specifying 2300 here because if I used the real port, I would have to have administrative privileges, and I can certainly do that, but this is a little bit easier. Connections to 2300 on this side are going to go to the server localhost on the other side, meaning it's going to terminate at this server that I'm connecting to. And I want to connect that to port 23 there. So what I'm really doing is I'm tunneling telnet from here to the other end, and I'm going to connect to a telnet server on that side. So I've got my SSH session open, and I should have a tunnel. And I'm going to check that now. So I'm going to connect to port 2300 on my local system, and that should connect me through to the other side. Log in here. Now I am logged in, and you can see that I am logged into the system bill, which you can see from my prompt here, which is the server that I'm connected to on the other side. You can see here I've SSH'd in, and I get the same prompt as when I did a telnet in. Now I can do this again, and this time, just to make it even more clear, I'm going to SSH, and I'm going to use the local port 23, which is the telnet port, and I'm going to do the same thing on this side. And in this case, since I'm using a privileged port, which is a port that's under 1024, in this case 23, I have to have administrative privileges, so I'm running this with sudo. And because I'm running it as root, it doesn't have the keys stored in that context, and so I've got to type my password here. Now I'm logged in, and I should be able to just telnet localhost. And it's skipping the username, but now it's giving me the password prompt, and so I can do this. And I am logged in to the system via telnet. But the telnet is being tunneled through this SSH connection in this first window over here. So that's one way of doing tunneling. You can use SSH to do your tunneling for you. One of the advantages of using SSH is, in addition to tunneling the traffic, it's also encrypted. You've got a layer of encryption, and then you've got a layer of tunneling of telnet traffic inside SSH. Another way of doing tunneling is using an HTTP tunnel. There is a package called HTTP tunnel, which allows this to happen. So I've got a server and a client. And in this case, I've just run the server with help to show you the different parameters that are required in order to get connections from a client. And in this case, the client is called HTC. And I've got mostly the same types of parameters here to start up the client. So you can see HTC is the client connection, and then I connect to a host and a particular port. And the default port for HTS is apparently 8888. I can use this client-server model in order to tunnel traffic that looks like HTTP traffic. Another way of doing the same thing is there's this company here that offers HTTP tunnel products, and you can see they've got an HTTP tunnel client. This is payware, although it says here the low bandwidth service features a free option for moderate users. So it looks like there is a possibility of doing this HTTP tunnel client for free without doing this subscription model here. So that's a couple of different ways of doing tunneling. Another option to do tunneling, and as I said, it's probably a good option because often HTTP and certainly particular ports are generally allowed through firewalls. So you could do your tunnel out through the firewall and be able to connect your data through without worrying about it being blocked at the network edge. In this lesson, we're going to be talking about penetration goals. So as with any activity or endeavor, it's useful to have goals set. You should have goals so that you can figure out whether you accomplished everything that you wanted to and how well you may have done. So the types of goals that we're looking for when it comes to penetration testing or ethical hacking or those sorts of activities really depends on the needs of your target. If your target is looking for just a check mark, for example, they're audited on a regular basis for compliance or regulatory reasons, and they're really just looking for a check mark on a sheet of paper, and they're not really going to do anything with the results. The goals you would have from that activity are probably going to be very different than the goals you would have from an activity where you've been engaged to be part of a red team and they want to see how deeply you can get into the organization without being spotted by the operational folks. So those are two very different scenarios where you would have two very different sets of goals, which isn't to say you should skimp on the first activity or do just a partial job, but the level of effort that you're going to put into and the types of things that you're going to do between those two sets of engagements is probably going to be a little different. It's important to note that malicious attackers will have specific goals. And our goals are going to be dependent on the needs of your target. If your target doesn't particularly care about one aspect of the type of activity you would normally go through in your methodology, that's part of your methodology, then you would probably drop that because it's not worth your time. That's not what they're paying for because they don't particularly care about that for a variety of reasons. Maybe they already know about it and they're involved in getting it fixed. So they're really interested in seeing you focus your time on some different things. So your target is going to have a set of needs and you should build your scope and your activities around what those needs are. It's just good business practice. So a malicious attacker is going to be looking for things like persistent access and control. So when we're talking about access, we're talking about were you able to break in? In other words, can you get shell access where you can be typing commands? Can you get desktop access in the case of a graphical interface? Can you start launching programs or copying files? Can you get access to a system? How easy was it to get access? Is it something that only a real expert with years and years and years of experience is going to be able to accomplish? Or is it something that a 12-year-old kid sitting in his parents' basement is going to be able to do? Can you repeat the activities that you performed to get the access that you did? Is it something that was just a fluke? Did it only happen once? Or can you continue to repeat it? And importantly, how were you able to get access? All of these are going to be interesting pieces of information for your target or the organization that has engaged you to perform these tasks. They're going to want to know, were you able to break in? In other words, is there something that we need to fix? How easy was it? Can you repeat it? Which goes back to the, do they really need to fix it or not? And finally, how, so they know what it is that they need to fix. In addition to access, sometimes you're just looking for information, and there are different ways of getting information aside from actually being on the system itself. You can gather usernames and passwords. You can gather information about other systems. For example, in the case of a web application, either the web server or the web application server may have a configuration file sitting around somewhere that's got the information about how to log into the database system. Otherwise, the application can't actually get access to the data that's stored in the database. So somewhere that's got to be kept. If you're able to find that, then that's really useful information. So credentials for other systems, really important, really useful to have. Also, credit card numbers or personally identifiable information. Malicious attackers are going to be going after those sorts of things. So your target probably wants to know whether you could find them as well, since that's going to be one of the goals of somebody who's really determined and really going after them. So they need to know whether that information is available, so they know that they need to do a better job of protecting it. So let's talk about persistent access. We've already talked about access. What's the difference with persistent access? Persistent access has to do with, can you get back in? Are you always able to get back into the system when you want to or when you need to? Can you log in anytime you want? Sometimes that isn't about continuing to come in through the same channel that you were able to get in the first time. Sometimes what you need to do is you need to install a backdoor. You need to set up a tunnel somehow from the system that you've managed to get into to another system so that you can come back in through the tunnel. Maybe you could set up a VPN and be able to get in that way when you need to remotely. So it's not always about being able to get back in the way you got in the first time. Sometimes it's about installing something that allows you to get back in whenever you want. Finally, we're going to talk about control. What does control mean? Well, it doesn't necessarily mean the ability to log in on a regular basis. Sometimes we're not so concerned about that. What we're concerned about is other things like, can I install a piece of software that allows the system to participate in a botnet? So, for example, can I get somebody to come to a website where I've got a piece of software that will exploit a vulnerability in the web browser and get my botnet installed that allows that system to participate in a botnet? That's a certain level of control. Can I use the system as a leaping off point to other systems? Maybe I don't really care so much about it and what it has as much as I care about the fact that I can get into it and bounce off to other more important systems. Can I get access to internal systems as I need? And some of that comes back to the jumping off point. Is the system that I have access to just a dumb system that sits on the edge of the network, but it somehow allows me access to internal systems through it? So I've got some control in that way. Could it be used as a tunnel point to other systems? It's really important to have goals as you come into a particular engagement so you know what it is that you're looking to accomplish. When you formulate your goals, you're going to want to make sure they are in line with the expectations of your target. So you don't have one set of goals and your target has a completely different set of expectations. So when you get to the end, they have no idea what you've done or why you've done it. You want to make sure that you're in line with your target when you formulate your goals and you go forward. In this lesson, we're going to talk about password cracking. You're going to run across instances where you can get hold of the password file, but of course, passwords aren't stored in clear text. And in subsequent lessons, we'll get into how passwords are actually stored. Let's just say they're not stored in clear text and you need to be able to do something in order to get a clear text password from these password files. So the first thing that we're going to look at is the little play on, of course, Jack the Ripper, the famous serial killer. It's called John the Ripper. The first thing I'm going to do is grab a copy of the password file that includes the encrypted passwords in it so that I can run John. So I've got my password file. I'm actually going to copy that into this directory where I've got my word lists. So I'm going to go into this word list directory here, Now, the thing about password cracking is it's not like, the movies where you just run through all of these things and very quickly you get a password. That can take a really, really long time, and probably a lot longer than your lifetime, in order to check through all of the various permutations and combinations of letters and characters and numbers. And so what we do is we create a word list of potential passwords, and then we go through the process of creating a password from it. In other words, doing the same process that you would use to store your password. So we're going to do a cryptographic hash of it. And then we compare the two hashes in order to see whether they match or not. And if they match, we know what the plain text password was, because that's what we used to create the hash. So what I'm going to do is I'm going to run John, and I've got my word list, and it's called all.lst, and I'm going to run that against my password file that I created up above. So what it's going to be doing here is running through all of the passwords in that file and checking them against the password file and seeing whether they match. And this could take quite a while. And so you're going to want to just let this run for hours and hours, if not potentially days. Doing this password ripping or password cracking can take quite a while. One thing that can help get around that is using something called rainbow tables. Now, rainbow tables are pre-computed hash tables that save the computation time of doing the hash on all of the passwords as you go through them. So here's a program called OPH Crack that's a free Windows password cracker, and it uses rainbow tables. So you can use this OPH Crack that you could download all over the internet, and you can use those tables with OffCrack in order to hopefully get some quicker times to get your passwords cracked. There's no guarantee, because if the password isn't in the list of words that you're checking, then you're not going to crack the password. And that's one of the places where complexity is really important when it comes to creating passwords. If you're just using a regular word, even if you, say, capitalize the first letter, there's a good chance that that may be in a word list somewhere that somebody can crack, which is why typically you'll see strong passwords recommending a combination of symbols and letters and numbers, as well as upper and lower case. If you do enough complexity and add enough variability to your password, you're not going to see that in a password cracker word list, probably, and it's going to make your password very difficult to crack, because what they would have to do would be to do a real, honest-to-goodness brute force where they do check all of the potential permutations and combinations. That's also why a longer password is better, because, of course, the more positions you put into a password, the longer it's going to take to brute force. The other thing is that word lists are often kind of up to 8 characters, because that's traditionally been sort of a standard password length. So if you make it a little bit longer, you make your password harder to crack and harder to find. So OffCrack here runs on Windows, Linux, and Mac OS. You'll see you can also get free tables for Windows XP and Vista. And when you download OffCrack, you'll be able to get those rainbow tables to go with that particular program. Another utility, though, that runs under Windows, Cain and Abel, is another password cracker. It does different things, though. So I could load the secrets from my Windows system, and you can see I'm pulling in the password file here, and I could run Cain against that to see whether it can crack them. We can also look for wireless passwords. It'll dump out your Internet Explorer passwords, as well as different edit boxes. It can do some sniffing on your network to be able to find passwords there. It also has the ability to do ARP poisoning, which means it can actually get a lot of data coming into it that you wouldn't normally have. So you can run this as a sniffer to go grabbing passwords and see what it can find on the network. There's a lot of different types of passwords that it supports. You'll see up above there's VNC and VPN. There's some base64 password decoders that it supports, Access Database password decoder, and a Cisco Type 7 password decoder, because Cisco stores passwords in their configuration files on their routers and switches in a particular format, and it's possible to break that and recover passwords that are stored in that Cisco 7 password format. You can decrypt WEP encrypted messages, and we'll get into some wireless in subsequent lessons. Cain and Abel supports a lot of different ways to grab passwords, both locally and remotely. So that's 3 different utilities that you could use to capture passwords and crack passwords in some different formats. In this lesson, we're going to be talking about password attacks. Now, in other lessons, we've talked about methods of doing password cracking, and that's kind of at a technical level, and we're really talking about more tools there than anything else, and I'll talk a little bit about tools here, but we've already kind of talked about tools in other places. What I want to talk about is the methods of doing password attacks, some of which may not be technical in nature. One tool that we didn't talk about elsewhere is Loftcrack, and Loftcrack is old, but it's also capable of doing password cracking, and they say it does password auditing and recovery. But what it's really doing, similar to John, is it's doing sort of a brute force attack where it's checking lots of different passwords against the passwords that you've got. So one password attack is just a brute force attack. And again, we've kind of gone over that a little bit. You have a word list and you go through and you check all of the entries in the word list and see if you can get the password to work, at which point you know you've got the password if it works. So we've got a brute force attack. Another type of attack is similar in that it's also a brute force attack. It just takes a lot longer, where you're randomly checking or systematically checking all of the different combinations and possibilities for each character position. Now, the problem you've got there is if you don't know how long a particular password is, then you don't know how many positions you've got, and so you've got to check multiple lengths. So let's say I'm going to check A0000 and then B0000, and you've just got to keep going through all of the potential characters in each position of, let's say, a 5-character password, a 6-character password, a 7-character password, an 8-character password. That's a different type of brute forcing. As you can imagine, it takes a really, really long time. Another type of attack is rainbow tables. Now, we've talked a little bit about rainbow tables in other lessons, and a rainbow table is also a brute force attack in that you are checking against known words. It's just you're doing all of the work for the brute force up front a little bit and then indexing the information so you can look it up again quickly. So what a rainbow table is just a table of information where you've got the password and the hashed version of the password so that you can look up the hash that you've got for the password you're trying to check against the hash in the table. In reverse, you can look up the password that's associated with that. Now, a couple of different types of attacks that you can use is looking for written passwords, and this is kind of a clean desk policy, where often people will write passwords down. And I know it's a bit of a cliche, but it certainly happens particularly in organizations where they have really strong password policies. Like if they've got to change their password once a month, it's got to be 9 characters. It's got to have an uppercase and a lowercase letter. It's got to have at least 1 digit, or it's got to have 1 special character. If it's got to meet all of those criteria, the human brain just isn't generally capable of storing that sort of information for easy retrieval and that often. So if they're changing their password on a regular basis and they've got some strong complexity rules, then they're probably going to be writing it down somewhere. So you can look down for written passwords if you've got physical access to the place where the people work. Another tactic that you can use is using mnemonic devices. So if I've got a word like elite, I might do some transposition in order to make it look like elite without actually spelling elite. So I could have, and that would sort of look like elite. I could also do something like, so I could use that for password, where you're doing transpositions of letters and numbers. So if you remember that 4 kind of looks like an A and 5 kind of looks like an S, and you're just transposing those numbers in for the letters in the word, I can remember that my password is in fact password, it's just got some numbers in it. You can also do things like checking for special characters between syllables, so maybe I'm doing something like this, and that's my password. Or if I want to do the same thing as above, where I'm doing the letter number transposition and also using a special character, I could do something like this as well, substituting the 0 for the O in password, and I've just put a % between the 2 syllables in that word. So there's a number of different types of password attacks that you may be able to accomplish. As I said, some of them are technical, some of them are really not technical. Some of it just has to do with understanding how people operate and the capabilities that they have in terms of the information that they can store easily in their brains. In this lesson, we're going to be talking about password storage, the different ways that passwords are stored in different systems. Passwords, of course, are typically not stored in plain text, and certainly at the operating system level, passwords haven't been stored in plain text in decades. They get stored in typically a one-way hash function. So you would send a plain text password through this one-way hash function that could not be run in reverse in order to get the plain text password back. So you have this hash at the end that the only way to get the plain text password back is to run a series of plain text passwords through the same hash algorithm and compare the hashes to see what worked and what didn't. In other words, whether the hashes match or not. Let's talk first about Windows and how Windows stores their passwords. Windows stores their passwords in SAM, which is the Security Accounts Manager, and it's stored in hashed format. With NT 4.0, Microsoft actually started to do partial encryptions of their database using this mechanism called syskey. However, we could do things like grabbing the passwords out of SAM using something like Cain enable. So you can see there's a password here that Cain enable has grabbed. We can also go into protective storage and see what we can get out of there. And in this case, it didn't actually find anything. But Cain enable has the ability to pull passwords that are stored locally from Windows. There's another utility called pwdump7. You can find this available for download. I can run pwdump7 here, and you can see that I've got administrator and guest, and it looks like that's the hash there, and guest has nothing at all. So that's a couple of different ways that even though Windows protects their password database, you still have the ability to go pull some information out of it, and then once you have that information, you can start running your password cracking attempts at it. Now, on the Unix-like side, for years, there has been a password file, and it's stored in the directory etc or etc. If I take a look at etc password, I'm going to see all of the users that are on this system. However, we don't see any passwords. So I can take a look at the password file, where the actual passwords are stored. except that I can't, because that requires administrative privileges to look at the shadow file, and the shadow file is where all of the hashed passwords are actually stored. So I have to have administrative privileges, and I can look at the shadow file, and you can see for most of these users, it doesn't actually have a password anywhere. There are a couple of users that have passwords, but the shadow file is where the passwords are actually stored on Linux and Unix systems. They're just plain text files or flat files, and they're stored in a tabular form where you have different fields corresponding to different things like a username, password, user ID, group ID, and that sort of information. A Unix-like system, though, that doesn't store your passwords that way is Mac OS. And if I go looking for the password file, there's one there. If I go looking for the shadow file, there's no such file as shadow. And that's because with Mac OS, Apple uses something called Apple Open Directory, which is an LDAP implementation, and that stores user data. So even though there's an Etsy password file, the user data, including the password, is actually stored in this LDAP format called Apple Open Directory. And that's how different operating systems store passwords in different ways. In this lesson, we're going to be talking about privilege escalation. So what do I mean by privilege escalation? Well, when you log into a system, you are given a certain number of privileges. And in the case of normal users, that's some small subset of the total number of permissions or abilities that users may have on a system. So when we're talking about privilege escalation, we're talking about getting more privileges than you would normally have. And there are several ways to do this. For example, in Linux, I could do something like sudo, and we've done this before. So this is a privilege escalation. I don't have the privileges with my normal user to be able to do the kinds of things that Nmap needs to do to send out those sorts of packets. Those require administrative privileges. So sudo is a way to get a privilege escalation from my normal user. As a matter of fact, it's the preferred way of doing privilege escalation on Unix-like and certainly Linux systems. So you could use sudo. If you want to jump straight to root, for example, I could use the command su, which is actually switch user, and I could switch to any other user that I want. But if I don't give a user, it's going to switch me to root. It wants me to give a password, and in this case, there's actually no password for the root user, so I wouldn't be able to switch directly to root. However, what I could do is this. And this is going to authenticate me as the root user because I have root privileges using sudo. And you can see here that I am now logged in as root. The big key is the hash sign or the pound sign at the end of the line. That indicates that you are a root user, and I'm going to log out from there. So that's a couple of ways of getting legitimate privilege escalation using Linux. In Windows, starting with Windows Vista, Microsoft started to lock down the abilities. You'll see where you'll get a message from time to time popped up saying, hey, this is going to require some administrative privileges. Do you want to continue doing this or not? So that's actually a privilege escalation. Microsoft has given Windows the ability to automatically grant those privileges, but it requires that you log in and authenticate as a user that has that higher level of privileges. Same thing on Apple in Mac OS. When something requires administrative privileges, you'll get a dialog box saying, hey, this action requires administrative privileges, so log in as an administrative user or a user with administrative privileges, and we'll be happy to continue. So I've got this services application open, and you can see that most of these services here log on as local system. Local system has just about the highest level of privileges that you can get. So if you were able to compromise one of these programs or services, then you would automatically have about the highest level of privileges that you can have. In that case, you wouldn't need a privilege escalation. Or if you were a normal user and you were able to compromise one of these from a normal user context, you would automatically get your privilege escalation because you would then become local system. Sometimes programs need administrative privileges, and the way that Unix has typically handled this is there is a bit that gets set. So you can see here with all of these files and programs, there's a number of settings. You'll see read, write, execute, and we've got the user group world sort of concept when it comes to permissions. There are a couple of additional permissions that you will sometimes see, and one of those is the setuid bit. So if the setuid bit is on one of these files, then executing it causes the context of the program to get switched to a different user ID. And in that case, it would be the user ID of the program's owner or the owner of the file. We can take a look at programs that have the setuid bit. I'm going to look for files of type F with permissions that have the setuid bit, and then I'm going to list those out. And of course, I need administrative privileges for that. We're going to try that again with administrative privileges. And you can see here right off, there's a couple. There's the mount sifs program and the Unix check password. So that's a couple of programs that require that they be run under a particular user context, and in this case, the user context would be root. But privilege escalation, as just a general concept, as I mentioned earlier, is the idea of getting a higher level of privileges than you would normally have in the way that you would normally log in or get access to the system. When we're talking about breaking into systems or penetrating systems, sometimes you'll get in as a regular user, and what you will want to do is a privilege escalation to get to an administrative user or a super user in order to do more interesting and important things. But that's privilege escalation. In this lesson, we're going to be talking about spyware, rootkits, keyloggers, and other types of nasty, unpleasant software. So you may be wondering what spyware is, if you've never run across any and have been fortunate in that regard. What spyware is a type of software that installs on your system and harvests information from you and any other users on your system. Now, it may take advantage of vulnerabilities in your system in order to be installed. Like you could go to a website and have no idea that there's something that's taking advantage of a vulnerability in your browser in order to get itself installed. Installing itself with something that you actually want or think that you want. So let's look at a couple of types of spyware, and we can discuss as we go how some of these actually get installed. Here's one that's been around for a really long time. You may have actually run across it before. This is Cool Web Search. And if you've got this, you may actually see it manifest itself as having taken over the home page that displays when you start your browser up the first time. You may see a toolbar that's Cool Web Search. But what it really is adware. In addition to being adware, it's also been flagged as spyware. Now, there's a difference between adware and spyware. Adware is software that displays advertising while the program is running, but spyware is something that goes even beyond that and takes information from you and sends it back to somewhere else for either sale or additional processing. a number of different types of spyware you'll run across. Cool Web Search happens to be one of them. Here's another one called HuntBar, and that's also considered to be spyware. In addition to installing itself quietly and silently, it can actually download and execute other types of code, including just updating itself. So in addition to Cool Web Search and HuntBar, we have things like Internet Optimizer and Weather Studio and the Zlob Trojan. So spyware comes in all different shapes and sizes. It's something that you probably really don't want on your system. However, as an ethical hacker, there's a possibility sometimes that you may need to use these different types of software in order to perform some activities that you need to do. Like you may need to use social engineering as an example to get somebody to go to a website that will install one of these products. If it installs and it is able to extract information, then you've got a finding about the vulnerability in the web browser and the fact that the users aren't as educated and as aware of these types of issues as they probably should be. You may also go to websites that have these types of software attached to them in some way. So in addition to spyware, we've got something called keystroke loggers. Now, keystroke loggers come in both software and hardware forms. In the case of a hardware form, it would be inserted in line between your keyboard and your computer. And it would do exactly what it says. It just logs the keystrokes. In the case of software, it does the very same thing. It logs keystrokes. And the difference between hardware and software is with a hardware keylogger, you would need to come in and retrieve the keylogger at some point to pull the data off. With a software keylogger, it probably would have some sort of phone home component that would take your keystrokes, and it may actually do some processing in order to find, for example, usernames and passwords or credit card numbers or similar types of useful and interesting information. So keyloggers have been around a long time, actually. One of the early keyloggers was written for Unix systems in about 1983. So for about 30 years now, we've had keyloggers in one form or another, and it's one thing that you want to keep an eye on as best as possible. If you see something attached to your computer or your keyboard that doesn't look quite right, definitely do some investigation. These other keyloggers, which are software, are ones that you would need like an antivirus program in order to go hunting for and removing. The last type is a rootkit. A rootkit is designed to hide the existence of other types of malware. Now, how it works is it usually replaces system processes, so when you do things like a directory listing, it will hide the programs and files associated with that malware from being displayed. So if you did like on Windows, if you went to Explorer, the Explorer program would have been replaced with something that worked exactly like it, but that hid the files from this rootkit from you. In a Unix system, if you did an ls, it would hide these files from being displayed in the file listing. It will also hide itself from process tables. So if you go to Task Manager in Windows, you won't see this show up because it's been hidden by the rootkit. Hiding the existence of the malware may also enable continued privileged access to systems, not only by evading detection, but sometimes there may be a backdoor associated with it as well that you're not aware of. This is where we get back to the concept of ethical. And there's a really fine line here in the use of these tools. You want to be really sure that you know what you're doing and how they work so they don't get out of control. You want to make sure that if you start playing around with a rootkit, that it's not installing this other type of malware on your target systems. Otherwise, you're violating probably the terms of your agreement. And certainly you're violating their trust as you're introducing actual bad software into their environment that they certainly didn't want, and you may not even know is there in order to be removed. You'll find a lot of different utilities around to look for and remove rootkits. Here's one here, the anti-rootkit utility TDSS killer. And on Unix systems, you'll find something called RK Hunter, which is Rootkit Hunter. And Rootkit Hunter will look for rootkits on Unix systems and look to remove them. So that's a few different types of potentially malicious software that may actually have some useful benefit to ethical hackers or penetration testers. In this lesson, we're going to be talking about a program called Metasploit. Metasploit is a penetration testing framework or an exploit framework that makes the job of penetration testers much easier. And the way it does that is it provides a quick and easy way of writing your own exploits against systems by bundling a number of payloads and quick mechanisms to get some exploits written pretty quickly and easily. Now, the other thing that Metasploit does is it bundles a lot of already written exploits for a lot of different software and operating systems. And so it gives you the ability to make use of the work of other people with these exploits, so you're not starting from scratch every time. So Metasploit was actually written by a guy by the name of H.D. Moore, written with the idea of being a framework that you could use to do a job more easily. At some point in the last several years, it was purchased by a company by the name of Rapid7, and H.D. Moore now works for Rapid7. It was originally written as a command line tool. Eventually, they added a GUI to it, and now with Rapid7's involvement, they actually have this web interface. So the very first thing that I would do, create a project, and I'm going to call it home. And here it's already got a network range populated, so I'm going to make use of that. And I'm going to initially just do a scan. I'll do a couple of addresses here just for fun. So I'm going to launch a scan. And it's really going to go off and do the same thing that Nmap does. It's going to do some port scanning to see what it can find about the operating systems as well as the system software that is running on those different systems. If you can see the Nmap command here, it's actually going through a really fast probe. So we're running through this as well as some other scans that Metasploit has access to. You can see it's all done now. We can take a look at the hosts that we've got. And if I click on here, we can see what vulnerabilities there may be. So we've got the list of services here. And if I go to the list of vulnerabilities, we actually don't have any vulnerabilities. So I can go back to another host, and I've got my DSL router. So there's no vulnerabilities associated with this. But I've got operating system and the operating system flavor and my Ethernet address. Certainly you can use this to do some discovery of your systems, and if there were vulnerabilities, this would give you an easy way to run the exploits on there. There's a lot of different ways to look at the data that I've got. You can see there were 13 services that were found. And I can go back to my hosts. I didn't bother scanning the whole network. I just wanted to give you a sense of what Metasploit is capable of doing. And you can see here that once it's done the scan, it sort of figures out what it may be able to do with the information that it's found. And in this case, the two systems that I had it scan actually don't have any vulnerabilities that Metasploit knows about. This is not a vulnerability assessment tool along the lines of Nessus or Nexpose, and you can see references here to Nexpose Metasploit integrates with Nexpose, and Nexpose will do the vulnerability assessment and then feed the data back to Metasploit to provide details about the types of services that you may be able to exploit. So this is really looking for some vulnerability data from a vulnerability scanner. Now, the other thing you can do from this Metasploit is you can go to the modules and take a look at the different types of exploits that are available. This is a starting point for Metasploit. In subsequent lessons, we're going to take a look at the command line interface for Metasploit and see how that works and how that's different from this web interface. In this lesson, we're going to be talking about auditing and logging. Most systems that you'll run across have the ability to do some level of logging, meaning applications and the operating system can write out messages to files so that you can do troubleshooting or debugging or just generally figure out what's going on. Now, from the perspective of ethical hacking or penetration testing, there's a couple of reasons to be aware of auditing and logging. One of them is being aware that activities that you perform on systems are probably going to get logged. If they get logged, there's a possibility that they can be detected at some point. So you need to know where logs are on different types of systems so that you can clean those logs so that your activities aren't detected anymore. So we're going to start on a Linux system here. Logs are typically stored in the directory /var/log. And the reason for that is, from a historical perspective, the /var file system, or mount point in the file system, is where variable data gets stored. So since logs are written to on a regular basis, and certainly their size can change pretty dramatically, those would get written out to /var. And you can see here the types of log files that are stored. Files that you may particularly be interested in would be, for example, syslog. These are all protected files, so I need administrative privileges. So I'm going to run sudo, and I'm going to take a look at the syslog file. Now you can see all of the messages that are in syslog, and you can see some cron messages and some dynamic host client. So DHCP client messages are in here, and if we skim up, there continue to be those types of messages. Another file that you may find interesting is the auth log. Now that would have information about authentication that happens, and you can see here the use of sudo commands, and also there's some cron messages in here, and there would be information about when users logged in, and you can see here some SSHD messages. Now, different types of Unix or Linux systems may use different file names, syslog and auth.log. The syslog file may be called messages. You may also find one called security, which may have some of the information that we're seeing here in the auth log. Now, the dmessage file is all of the kernel messages. So I can cat the dmessage file, and you can see all of the messages that the kernel has spit out. Now, I could also accomplish the same thing by running the command dmessage. And all that does is it prints out the information from, in this case, the dmessage log. So that's Linux or Unix-like systems. And again, those are in /var/log. Different flavors of Linux and different versions of Unix may have file names that are a little bit different, but if you look around a little bit, you'll pretty quickly become acclimated to the types of data that you're going to see in the different logs and which log file you're going to be finding the information you're looking for in. Let's move on to the Mac OS now. Very similarly to Linux that we just looked at, primarily because it's a Unix-like operating system, you'll see this console, and on the left-hand side you can see the files that we are looking at. I can look at diagnostic and usage messages, and you'll see these are some application-specific messages here. I can look at user diagnostic reports, system diagnostic reports, and those have to do with application crashes. I can clear the display, I can hide the log list. What this really is just a graphical interface to the types of data or the specific data that we were looking at in Linux in the various files in /var/log. On Windows, we're talking about something a little bit different. We are looking at something called the event viewer, and I want to look at Windows logs here, and you can see my application log. And here's a lot of different application messages. Most of these are information, although there's a couple of error messages. There's a lot of different reasons for logging messages to a log file. In general, as people are writing applications, having some sort of trail from the application as to what it's doing is a really useful idea. Sometimes things just break, and you want to be able to have a place to go figure out why it broke, and going to the logs is a really useful thing to do. Now, much like the Macintosh, Windows is really pulling up basically text files that are sitting on the disk and presenting them in a way that makes them easier to understand. You can see here in the security log, we've got some keywords called audit success, and this is where we get into more specifics about auditing. Under Windows, you can set up policies about things that you want to audit. For example, I could set up an audit for failures on logins. I can set up audits for success or failures on object or file access. And what that does is it generates log messages when those activities happen, whether it's a success or a failure. So you can see here that I've got a success audit turned on for logons. So I can see that I've done some logons and tells me the computer and some different information about it. Now, Windows isn't the only system that has auditing capabilities. Any system that will do logging has auditing capabilities. With Windows, it's called out specifically in their policy managers where you can turn on auditing of events. But going back to the logging, as you can see, the Windows logs are broken up into application, security, setup, and here's one called forwarded events that would come from other systems. We also have applications and services logs, and you can see hardware events and then a log from Internet Explorer, a key management log, Media Center, and Windows PowerShell. They all have their own individual logs. So no matter what system that you are talking about, there's probably some sort of logging involved with it. Now, whether you want to extract information from the logs that may be useful to you to perform some other activity, or whether you want to hide something that you've done editing logs, here's a few different examples of logs on different operating systems. In this lesson, I'm going to be talking about using Metasploit. And while we've used Metasploit from the web interface, this time I'm going to be using it from the command line, and we're going to be running MSF console command line access into it, and just the ability to type commands and do things straight from inside Metasploit. So I've got Metasploit open here now, and I've got the console. You can see I've got 922 exploits and 496 auxiliary, 251 payloads. It's got a lot of information in it that provides you the ability to build exploits and also just run existing ones. So one of the things I can do here is I can run nmap straight from inside Metasploit. I'm going to set a very high timing rate, And I'm going to run it against 192.168.1.245. And you can see some results here. So I can show you the hosts that I've got in my database, and Nmap uses Postgres on the back end. So when I run this command, I'm actually checking the Postgres database that Metasploit connects to. So you can see here I've got a Linux system in my database and a Windows XP system. Another thing that I can do is I can import this Nessus report file, and what that should do is it should populate some vulnerabilities for me so that Metasploit can tell me what vulnerabilities that I have. So I've done a DB import on this Nessus file, so I exported the report in the Nessus XML version 2 format, and now I've imported it in here, and from here should be able to see the different vulnerabilities that we've got. I've got a whole lot of vulnerabilities that have been noted against this particular system. And in order to find the vulnerability module here, I'm going to search MS08-067. I've got a Microsoft vulnerability from 2008 that hasn't been updated as near as we can tell. So I'm going to use that particular vulnerability. Now you can see the options that I've got here. So I'm going to set our host to 192.168.1.245. And now I can just exploit. And so it's going to run the exploit against the system, and you can see it's running. We've sent the second stage, and now I've got a Meterpreter session open. You can see that we're in system 32. Now I could run get system here and attempt to get a privilege escalation. The reality is I've already got system, because what I exploited was running at local system, so I already had administrative privileges. Now the other thing that I can do here, I can print out the passwords. You can see all of the users and passwords that are here. Another thing that I can do is I can get a screen grab right there. And you can see the system that I have just broken into. I could do a webcam snap if there was a webcam that was attached to it, so I could get a picture of the room that I was in. I can do a print out of the information about the system, so you can see that it's running Windows XP, build 2600, Service Pack 2. So those are different things that you can do from Metasploit and Meterpreter. In this lesson, we're going to be talking about malware definitions and history, so different types of malware and what it all means, and when did it all start. In 1947, actually, the first bug was found. In reality, it was an actual bug, which is where the term comes from. Grace Murray Hopper, who was in the Navy and was working on computer systems, found a moth inside of a system that was causing a system failure. And ever since then, every problem with computer systems, we've called them bugs. In 1961, researchers at Bell Labs created a game where programs killed other programs. That kind of falls in the line of the types of activities that malware accomplishes. In 1971, we had the first case of a virus on the ARPANET. It was the creeper virus. Very, very benign. It was just a message that would pop up on systems saying, I am the creeper, catch me if you can. 1974, another virus on the ARPANET. It was the rabbit virus. Getting into the PC era, the very first virus that was found on a personal computer was actually on the Apple II. It was a boot sector virus, and it was called Elk Cloner. That was back in 1982. It wasn't until 1986 that we find the first IBM PC-based virus. That was the Brain virus, and it was worldwide. And you have to remember that back in 1986, we had primarily floppies to store information and transmit them from one system to another. We didn't do a lot of modem communication, didn't do a lot of network communication back in 1986, so it was primarily people handing viruses to another system or to another person that then infected their system. In 1987, we run across the first virus that's known to destroy data. That was the Vienna virus. It wasn't until 1989, though, that it was recognized to be enough of a problem that IBM actually introduced a piece of software called VirusScan. That was the first commercial antivirus offering. The first theoretical work was done by John von Neumann in 1947. What a virus is a self-replicating program. It has the ability to move from system to system. So a virus is going to infect one system and different pieces of software on that system. And when those programs or files are copied to another system in some fashion, then the virus can go infect that system as well. A virus may or may not be destructive in nature, and it makes use of other programs. In other words, a virus attaches to a host, much like a virus in the real world where it transmits from human to human. It can't survive or do much of anything without the human being involved. And here, a virus needs a program to attach itself to in order to maintain its existence and keep multiplying. A worm, on the other hand, is self-replicating. It is a standalone program. In other words, it doesn't need to attach itself to another program to exist. The worm has two goals, one of which is to continue to replicate to other systems and hosts, and the other thing is to do whatever it was programmed to do. Trojan horse, in the case of viruses, you could call them Trojans, much like the original Trojan horse. It's malicious software that looks like something else. So the original Trojan horse was a wooden statue of a horse that actually held soldiers who were supposed to slip out in the middle of the night and attack a city. Same thing here. We've got some malicious software that's hiding in some software that's innocuous looking. You run the innocuous looking software and you get hit with the malicious software at the same time. And now we've got rootkits. A rootkit is going to go hand in hand probably with some other type of malware, because its reason for being is to hide the existence of certain other types of software. A rootkit is there simply to make the work of another piece of malware possible. It may also be used to maintain privileged access to a system, and that may be through a backdoor. So lots of different types of malware, and we're going to go into some more details and what they do and how they work in subsequent lessons. In this lesson, we're going to be talking about detection of malware. The first thing that we want to do is talk about a couple of different ways to do malware detection. And you'll find that whether we're talking about intrusion detection or antivirus programs, you'll find that there are commonly a couple of different ways to do this. The first is called anomaly-based. Now, anomaly-based has to do with figuring out what's normal on either a system or a network, and then alerting based on anything that deviates from that normal behavior. With anomaly-based, you have to have a baseline that you can check against when you see anything happening, and anything that deviates from that baseline would be considered anomalous, and therefore you would alert on it. The other type is signature-based, and it's the one that's more commonly used. Signature-based, of course, is based on a number of signatures. So you take, for example, a virus and you develop a signature of that virus based on what the file looks like, what its characteristics are. You check any program that runs or file that comes in against those signatures, and determine whether you've got a piece of malware on your hands or not. Everybody, I think, is pretty familiar with antivirus programs, and we'll talk about one of them here, although there are several. Now, Microsoft used to have this program called Windows Defender, and they've since changed that into this Microsoft Security Essentials. It's a free program, and it not only is antivirus, it checks for other types of malware as well. There are versions of malware that attack Linux. There are versions of malware that attack Mac OS. In terms of Linux and Mac OS, you'll find that ClamAV is a free and open source antivirus solution that will run on both of them. Another way of doing detection of malware is using something called intrusion detection. Now, intrusion detection can be either host-based or network-based. When we're talking about host-based, we could be talking about programs that check the signatures of files. So you might run an MD5 hash against all of the critical files on your system and all of the system programs, and you would create a database of all of those. You could check against that database periodically to see whether anything has changed. If something has changed, then you may very well have a piece of malware on your hands. So that's a version of host-based intrusion detection. And I'm going to take a look here at a network-based intrusion detection system. This one is actually called Snort, although the interface that I'm looking at is Basic Analysis and Security Engine, or BASE, and Snort runs primarily on Unix-based systems. There are some fairly complicated rules that go along with Snort. You kind of have to know a little bit about some network filtering syntax to be able to write Snort rules. You can see these rule sets in this directory. These are all of the rules that are on this system. So I could take a look at backdoor rules. For example, the one at the top says alert on a TCP packet, any external network, and the source is any, and the destination is the home network, and these variables that have the $sign in front of them are defined in a configuration file. And there's a lot of other details here about flow bits and offset and some other stuff. You have to know a fair bit about what the packet looks like in order to write these rules for this. The backdoor rules has about 119 rules in it. Each of these files is going to have several dozen rules in them. And again, these are signatures, so you could see that signature is based on what the packet looks like. So for example, source or destination, IP address or port, and some other information. And that would be the signature that the rules are based on. So we can go back to base now that we've taken a quick look at Snort, and you can see the different alerts that have popped up from Snort. I'm going to take a look at the unique ones. You can see there's a shellcode alert, and shellcode could be something to do with a piece of malware. It could suggest that somebody has tried to break into a program, so there may be some malicious behavior or malicious intent with that one. Now, another way of doing malware detection is to look at web connections. A lot of malware comes through web requests and interactions with web servers. One way you can detect malware is using a proxy, and you would use a proxy that you were able to inject some sort of malware detection engine into the middle of, or that the proxy had that malware detection engine built into it. And here's a pretty common proxy server that does that sort of detection. It's Bluecoat, and you can see the different products they have here. The Bluecoat proxies have the ability to filter different websites, and they can also check for different pieces of malware to see whether they are coming through or not. So that's how you would do detection of malware, whether you're doing network-based or host-based. In this lesson, we're going to be talking about antivirus evasion. Being able to deploy a piece of malware without your antivirus software detecting that the piece of malware is running on your system or is installed on your system. So how would you go about doing that? Well, the first thing you have to remember is that antivirus programs are typically signature-based. And since signature-based relies on something looking the same every time, what you can do is make sure that the malware that you're using doesn't look exactly the same as the malware that there is a definition for in the antivirus program. I'm going to create a little text file here. So you can see the hash there. All I added was a 1 and a space, so not significantly different. But look at the hash now. The hash is very, very different. And this is why malware sometimes will morph itself as it continues to spread. So every time it infects something, it tries to look a little bit different. And this is because it's trying to evade antivirus scanners so that it can continue to live a long and healthy life. So this malware is doing things like rewriting its own code as it continues to propagate. Something else that you may be able to do in addition to just simply making some changes is you may be able to do some sort of encryption or decryption, or even stagger your encryption or decryption. So once you use AES, another time use DES, and sometimes use blowfish, sometimes use twofish. So you can use different encryption mechanisms that may actually get you around antivirus software as well. We'll talk about packing in a little while, and packing is a way of stuffing your executable inside of something else, and this other new executable would have to unpack your software. So if you use different packing schemes, you may be able to avoid antivirus detection as well. Another thing you can do is you could encode it, or you could encode portions of it. And let me show you a little bit of encoding here. I'm going to do just some base 64 encoding. So I'm creating a string, and I'm using Python for this because Python is pretty quick and easy, and it will actually interpret on the fly. I don't have to spend time writing a program and then having it run or compile or any of those things. I can just run it right on the fly. So I'm going to print out the base 64 encoding of that string that I just created. So base 64 encoding is another way of obfuscating data so that it's harder to determine what it actually is. And so your program may end up looking a little bit different every time you compile it or run it with a different encoding algorithm. Now, we're talking about signature algorithms for doing antivirus detection. With anomaly detection, it's a little bit harder to get around because anything that looks different can cause an alert in an anomaly-based detection system. Here's an advantage, though, with anomaly-based. This is another one of those cases where you may be able to generate a lot of alarms with a lot of different things looking different and then be able to slip in amidst the noise. In spite of the fact that signature-based has its problems, anomaly-based actually causes a lot of work with a lot of potential false positives, and you end up having to do a lot of maintenance and running down things that aren't really issues. And that's a pretty big problem when it comes to manpower and resources. The last thing they want to be doing is chasing down a lot of false positives and doing a lot of maintenance just to keep up with changes in the environment. So a few different ways of doing antivirus evasion. In this lesson, we're going to be going over deployment of malware. In order to get the malware onto a user system, you've got to have some sort of mechanism to get them to execute it, because of course what you've got in your hands is an executable, and they don't typically run automatically without some sort of mechanism in place, either having the operating system deploy it automatically in the form of a service, something in the startup folder or something like that, or just getting a user to trigger the run of a program. So what we've got here is Zeus again, and Zeus is one of those pieces of malware that has a botnet connection associated with it. And the nice thing about Zeus is you don't have to worry too much about creating the malware yourself. They've got this nice little builder app, and you can decide the various things you want to do with it. It comes with a configuration file, and of course we can edit that configuration file. We can make all sorts of changes. Now, once I build the bot executable here, I've got a little dialog box here saying where do you want to save it to. So it's calling it bot.exe. Now what I want to do probably is call it something like Elf Bowling, or some sort of name that is going to get people to install it or run it, or something along those lines. I'm going to save it like that. You can see here that the build succeeded and I've got myself a bot. Again, though, you've got to give it a name that somebody is going to want to execute, and you've got to be able to get it to that person. Another way of getting malware into the hands of users is to use something like a wrapper. And what a wrapper does is it takes a piece of malware in the form of an executable and it wraps it inside something else, and what we end up with is basically a Trojan horse, because it looks like one thing when really something else is going on. So I've got here a directory with Elite Wrap, and Elite Wrap is a piece of software. It's about a dozen years old or so now, but it still works pretty well. A wrapper for a piece of malware, and I don't really have a piece of malware. What I'm going to use is the system notepad, which I've copied into the directory here, and I'm just going to use that as the example of my piece of malware that I can wrap up. So I've got Elite Wrap, and I'm going to say that the name of the output file here, I'm just going to say is install.exe, and I happen to have it here anyway, so I'm going to overwrite that. I'm going to perform CRC checking, and in this case, I only want a packet. So what I'm going to do is I'm going to use something called stuff.txt, and the operation I'm going to do is I'm just going to packet. My package file is going to be notepad.exe, and in this case, I'm going to execute that one. So I'm going to say operation 8, and for the command line, I'm going to say is stuff.txt, and I don't have anything there, so I'm just going to hit enter. And I've got my wrapped application here. So I'm going to go over to my Elite Wrap directory, and I've got this install.exe, which won't actually run under Windows 7 because of all the protections that are in place. But if you had an older version of Windows, this would work. And what it would do would be to open up Notepad and also open up that text file. And that would be this text file here. So that's how you would use Elite Wrap in order to wrap a malware executable so that you could get it to somebody in the form of a Trojan horse, so that they would run one thing expecting one result, and in the background you would be having something else going on, like you'd be installing your piece of malware or whatever it happens to be. So there are a lot of different possibilities here for getting malware deployed. Here's one example that I just showed you, which is Elite Wrap. Different ways that you may think about doing malware deployment. In this lesson, we're going to be talking about virus types. Now, there's a few different types of viruses, and some of them are really kind of hybrids because they take a couple of different types of viruses and use the behavior from those, and we classify them as a new type. One of the first ones I want to talk about is a boot sector virus. some examples here of boot sector viruses that were collected. And there's really not much to them. They're probably encrypted in some way or packed, and so there's really not an awful lot to see with them. But you can see there's a couple of different ones here. I could even do a diff between them and show you that they're different. These are boot sector viruses, and the way a boot sector virus works is it replaces the boot record on your system with a piece of code that will run the virus prior to launching your existing or old boot sector. So it copies your boot record off to somewhere else that it knows about. The very first thing that it does is to run the virus and make sure that you are nice and well and truly infected, and then it actually goes and executes the code from your old boot record in order to load the operating system. There's a number of different types of boot sector viruses, 4 different types that I've got stored here, which is not to say there are only 4. Boot sector viruses have been around for a really long time. So another kind of virus that we can talk about is a shell virus. And the reason it's called a shell is it wraps a shell around a particular executable. So it would infect your system by taking an executable that you would run a lot, like maybe Notepad on a Windows system, for example. It would wrap Notepad inside this shell that would actually run the virus code first before launching the actual Notepad. So you end up running the virus when you think that you're running a legitimate application. So shell viruses can be challenging because you're running something that you think you're sure about. The only way to actually know whether your system is infected is to check a known good version of the executable against this one in some way. And of course, that's what antivirus programs do, is they check for things like that. Particularly if you're running a signature, it will look for the signature in all of your executables to see whether the virus is hidden inside the executable that would normally be considered good. Another type is a multipartite. It's a combination of a boot sector and a shell virus. So a multipartite infects both files in the boot sector. It's really a boot sector and a shell virus all wrapped into one. We also have macros, and macros are usually written in Visual Basic for applications, and it runs inside of Office applications. So you could open up a Word document again thinking that it's good, and you get infected with this virus because it's embedded in a macro inside of your Word document or an Excel spreadsheet or any number of documents associated with Microsoft Office applications. Now, Office has gotten a lot better about how it treats macros, but macro viruses have been around for quite a while and were really popular for a really long time. We also have polymorphic viruses, and polymorphic does code mutation, so signatures change. This is Zeus, which was a pretty popular piece of malware. It's actually a botnet, so it's a pretty bad piece of software. And it can look different based on how you actually generate it. So you can see here there's some configuration that goes along with it, and we could install web filters and do web fakes and a number of other things. There are some rules that it's got about how it's not allowing you to go to anywhere at Microsoft.com. Similarly, not allowing you to go to MySpace. We've set up some web filters, and these all get set up when you build Zeus. And there's a little builder program that you run, and it actually creates an executable for you to distribute. The thing about Zeus, though, as I said, is it looks different based on how you configure it. And so it's a bit of a polymorphic virus because the signatures can change and look different based on what you do with it. Now, comparing a polymorphic virus to a metamorphic virus, a metamorphic virus rewrites itself every time a file gets infected. So where a polymorphic virus may have a number of different signatures for different systems, a metamorphic virus would be one that, let's say it found 5 files to infect on your system, it would look different in all 5 of those files. So polymorphic does code mutation. It's going to change and look a little bit different. It's going to have multiple shapes. Metamorphic is going to rewrite itself every time it finds a file to get infected. So that's some different virus types that you are going to run into as you start digging around through malware and doing malware analysis and malware work. In this lesson, we're going to be talking about malware analysis. Malware analysis is a pretty big topic. We're going to just skim over a couple of things quickly. You could probably find a college course somewhere that would cover this in pretty great detail. There's a lot of knowledge that goes into malware analysis. The thing about ethical hacking is it requires a fairly broad level of information just so you get a sense of what's involved. If you're interested in learning more, of course, you can take this as a starting point. But let's take a look at a couple of ways that we can do malware analysis. Now, the first thing we can do is go to this website called virustotal.com, and it will do an analysis on suspicious files and URLs. I'm going to find a file that I'm pretty sure has some problems with it, and I'm going to send it to them. So it's this one here, and I'm going to say scan it. So it's uploading, and it looks like this file was already analyzed by VirusTotal, and so we can take a look at the last analysis. This happens to be a botnet. It runs on Windows 32. Here are the different names that it has been classified under with the different antivirus engines. You can see Nod32 actually identifies it for what it really is. It's a variant of Zeus. And you'll also see some of these others calling it Zbot. For example, Microsoft calls it Zbot, which is another name for what this particular piece of software actually is. It's a Zeus variant. I happen to have it for purposes of analysis and doing some work with it to see what it is, what it does, and just take a look at it. So you could use VirusTotal if you don't want to go digging around yourself, and it can provide you information about what all of these different antivirus companies think that it is. So I've got these different executables here. I'm actually running this on a Linux system because it's the easiest way to run this particular utility. And what strings will do is it will find ASCII strings in this executable and print them out for us. You can see all of the different strings that are in this file, and it looks like a lot of them look like garbage. Towards the bottom, though, you can see the different DLLs that this pulls in. So like Shell 32 and Olay 32, Common Controls 32. We can also see there's some XML information here as well. And it looks like this may be something to do with .NET because this is an assembly definition, this little piece of XML here. So we could use strings to look at human-readable information that's in executables. Sometimes just the human-readable strings that are in a program can give us some information about maybe who was involved with it or where it's come from or what it does. And you can certainly see that there are some different function names here at the end, and usually these are functions that are being imported from some other library somewhere. And again, you can also see the different libraries that are involved, these DLLs here. These are ones that get loaded as external libraries to this particular program. So again, I did this under Linux. You can get versions of strings for Windows and do the same thing on a Windows platform. Another program that I can take a look at under Windows is this PEID. This will give us information about the program executable. And I'm going to go take a look at the file that I looked at earlier. the zsbcs.exe. And the thing about this PEID program is, in addition to things like the entry point and the file offset, the linker info, and the first bytes, the subsystem that is involved with this executable, it will also tell you whether it's been packed or not. So you can see this particular one has been packed, and it uses the UPX packer. You can see the EP section is UPX1, so the very first thing that this executable is going to do is unpack itself before it goes and runs the main portion of the executable. Now that's for a packed program. Let's just take a look at one that probably isn't packed, and you can see there's no packer here found. We've got an entry point and a file offset here as well. The linker info is 9.0 as opposed to 10.0, which the other one was. And this is a Win32 console application. We'll also get into using debuggers in subsequent videos, and you can use debuggers to pull malware apart as well. Of course, that requires some knowledge about programming, or at least a willingness to just roll your sleeves up and dig in and learn an awful lot about program structure and memory layout and those sorts of things in terms of how programs get loaded into memory by the operating system and executed. But that's a starting point on malware analysis. In this lesson, we're going to be talking about Windows alternate data streams, or Windows ADS. So what's an alternate data stream? Well, when you've got just a typical file, let's say a text file, that's sitting on your file system, that text file has a single data stream, and it's the text that sits inside the text file. So you've got that one single stream for that one file. With an alternate data stream, you have the possibility of having multiple pieces of data in different streams attached to one single file. So we've had this ability to do alternate data streams in the Windows NT line for something near 20 years now. Windows used to support multiple file systems natively, and one of them was the Apple file system. So Windows actually created this alternate data stream as part of their support of the resource forks that were in the Apple file system. Now, a resource fork is a little bit different than an alternate data stream. A resource fork exists solely for the purpose of storing resources like icons, for example, or other similar types of resources that are required by the application. They're stored in a resource fork, which means that a user won't get to see them or won't get to manipulate them directly in normal circumstances, but they are still there and available so that the applications and the operating system can do what they need with them as the applications run. So Apple has their resource forks, Windows has their alternate data stream. The thing about the alternate data stream is it never had an explicit purpose and never had a particularly good reason for being. It was just always there. People who are involved in malware realize this alternate data stream exists, and they can start stuffing their malware into these alternate data streams and have a way of hiding them. So I'm going to show you here a way of creating an alternate data stream. So the first thing I'm going to do is I'm going to put some text into a file. So I've got this just a bunch of garbage, and I'm going to put it into something called garbage.txt. And I can even spit it back out. And you can see just a bunch of garbage. So now how do I create an alternate data stream? Well, I've got this other file sitting in this directory here, and it's called streams.exe. And I'm actually going to attach streams.exe into this text file as an alternate data stream. So let's take a look. and it's still 26 bytes. Now, how does that work? Well, it's because when you're looking at a directory listing, all you're looking at is the data that's associated with the primary stream. The alternate stream is actually hidden, and that's what makes this a good way of hiding information inside your file system. It used to be that there were ways of executing programs from inside these streams. I would do like start, and I would do garbage.txt, and I would run streams.exe from there. You can see that Windows 7 actually generates an error, and that's because Windows 7 now prohibits the execution of programs from inside an alternate data stream. So this streams program is from Microsoft sysinternals, and it actually will look at files to see whether there are alternate data streams associated with them. And you can see here I've run streams against my garbage.txt. It says that there is some data that's associated with that, and there's an alternate data stream called streams.exe, which is a data file that's about 87K. You have to have one of these programs in order to find the streams that are on your system. So as I said, alternate data streams, they're a pretty good way of hiding information, and they don't show up in things like a directory listing or in Windows Explorer. You wouldn't see that there was an alternate data stream there. Their file size wouldn't increase. You just wouldn't know unless you knew to look for the alternate data stream that there was some additional data that was attached to that file. The one thing that you can't do anymore since Windows 7 is you can't run executables from inside an alternate data stream, so you'd need to be able to stuff the data into the alternate data stream and get it back out again in order to run the executable. But that's Windows alternate data streams and some uses and how you would go about using it. In this lesson, we're going to be talking about debugging. Now, you may be thinking that debugging isn't something that you need to know because we're not talking about writing programs and doing big programming tasks. The thing about debugging, though, is if you're going to be looking at malware, for example, or if you're going to be writing program exploits, you need to be familiar with using debuggers and how they work and how they're all laid out and what you're actually looking at. It's also really helpful to be familiar with assembly language because that's the language that you are going to be looking at once you're inside the debugger. So what we're going to be looking at here is a couple of different debuggers under Windows. First thing I'm going to do is I'm going to open up a program, and I'm going to grab this one here. And you can see that what OllyDebug is doing is it's launched the program. And OllyDebug is a free debugger that you can get. There are a couple of different versions of it now. 2.0. something is the most recent version, and that's the one I'm working with at the moment. So here's the assembly language code that we are looking at, and this is the actual program. This is what's sitting on the disk. And of course, this is the mnemonic version of that code. It's not the binary that you would actually be looking at on disk. This has been translated to something that's somewhat human readable. So in the right-hand corner, you can see the registers, and there's a couple of useful ones to make note of. There's ESP, which is the stack pointer. That's the current position in the stack, and you've got the base pointer, which is the bottom of the stack, and you've also got the EIP, which is the instruction pointer. So that's the place in memory where we are executing code from, and that's the current instruction that we're sitting on. You can see it's 401130, and if you look in the upper left, you'll see all of the addresses down the left-hand side, and that's 401130 as well that we're sitting on. Now, we're just kind of sitting there because that's what the debugger is there for. It's launched the program, it's got to the starting point, and it's stopped waiting to figure out what we want to do. So there are a few things. We could just run the application, and this would be useful if we had breakpoints set up. So we could just let it run and go to a breakpoint, at which point we could take a look at what's actually going on. We can do step-by-step execution of the program. So I'm going to do steps here, and you can see the stack pointer and the base pointer down underneath the execution, the main thread. And you can also see I'm moving slowly through the threaded object here, or the program that we're running. And now here it's going to call a particular function that is at the address 401020, and so we should jump off to that address. And now it's asking me, because this is actually a server, so it's asking me whether I want to allow access for that server to listen, and I'm going to say yes. We're at a point now where we're not actually doing anything because the program is waiting for input. But these are sort of common steps that you would take as you're debugging. You would want to know how to just step by step go through your program one line at a time, or one instruction at a time. And you would do that using the step into, step over, or trace into, those different commands here. You can also see in a couple of other sections of this window, you can see the different addresses and what's located in them. So if you want to see what's in memory, or what's at any particular point in memory, and you want to see both the ASCII and the hex, you would use this window in the lower left. And in the lower right, we've got a different section of memory, and this is where the actual code would be stored, or a different portion of the code would be stored. And it looks like these are all different libraries here. So this is a pretty typical debugger setup. Now I'm going to close the debugger, and it's going to stop the program. And so it's got the process closed now, and since there's nothing loaded up, all of the windows are blank. Now what I'm going to do is I'm going to show you the same thing in a different debugger. This is the immunity debugger. You're probably not going to find an awful lot that's going to be hugely surprising to you when you go from one debugger to another. The first thing that you notice is its color. There's color coding to make understanding what's going on a little bit easier. So you can see the actual instructions are in a green. We can see load instructions and move instructions and add instructions, and then some calls and returns. And so any place where we're jumping out of the current execution path, so like a call or a return or a jump, those are in red. And the white ones are registers. And we've also got different chunks of memory. Those are different colors, so addresses are different colors, and just raw pieces of information are different colors as well. You can see on the right-hand side, we've got the same thing more or less as what we had with Ollie debug, and you can see the registers, and you can see the base pointer and the stack pointer and the instruction pointer. In this case, the instruction pointer has stopped inside NTDLL, which would be a dynamic library, and it's holding on there. Same thing here, though. We could just let it run, and we can step into. So I can just click through here and let this process run. You can see the instruction pointer on the right-hand side is incrementing. But pretty much the same thing as what we had previously with the Ollie debugger. So it takes some getting used to how all of this works, and this is certainly not something we can do in a short lesson here. It's something that you need to spend a lot of time digging into and learning some assembly language and seeing how all of it works. And once you get to the point where you understand assembly language a little bit better and can see what's happening inside the program as it actually executes, you could move towards doing things like analyzing malware inside a debugger and seeing what the code is actually doing. Because without the source code, this is the only thing that we've got. We've got the actual executable, and you need to be able to understand what the executable is actually doing. And there's no way of actually masking that. The executable is going to do what the executable is going to do. We can't play around with that inside the debugger because you're going to be able to see every instruction as it processes. That's just how these debuggers work. So that's why I wanted to introduce just a couple of debuggers to you, and there's certainly other debuggers as well. Microsoft's got a debugger. There's one called IDA Pro, which is kind of top of the line from a debugger standpoint. On the Linux side or Unix-like side, we've got GDB, which would be a debugger, and there are graphical versions as well, like DDD would be a graphical version of GDB. So we've got different types of debuggers. They run on different operating systems, but ultimately they have the same object in mind and the same core functionality, which is to run through a program and show you instruction by instruction what's happening as well as what's going on in memory. In this lesson, we're going to be talking about packing and packers with regards to malware. And you can actually download this. It's called FreeUPX. It takes files that have the Microsoft Portable Executable format or the COF specification, executables for Windows, and it will do the compression on them, and then it will wrap the application with something that will decompress the actual executable code. So what you're running when you get it is first a decompressor to decompress the executable, and then it launches the executable. And that's kind of the idea of a packer. You can see all of the different types of options that I've got here. So I can set my compression type, either the UPX default, or I can set different levels of compression. I can do brute or ultra brute compression. I can force compression, and I can either create backup files or overlays, have export sections be compressed or not, and here's the relocations. And all of these are set to UPX default. I could have it show a particular icon or compress the icons or not compress them. And then here's all of the different advanced settings that we've got. And what you do is you just add files, and then it works to compress them. So we're going to go into Documents, and let's just compress this one here. Now I can run my compressor on it, and I've just compressed the file vulnserver.exe. So that's a free compressor that's available. As I said, it's called FreeUPX, and you can download that, and you could use that to pack your malware in order to hopefully get it by different detection techniques. And also, since it's compressing it, it's going to keep it a little bit smaller. So that's helpful. Now let's look at an actual piece of malware that's got some packing functionality built into it. So right here, I've got the Zeus builder, and Zeus is a particularly infamous botnet. And one of the things about it is it's got an automated builder here. And here's the configuration file it's using. These are some different settings that are going to be built into the executable that we end up getting. Now I could run build the bot executable here, and it's going to go build that bot, and I'm just going to call it bot.exe. So I've got an executable now, and I've got it right there. And I'm not going to run it because it's a piece of malware, but That's the bot executable that I just created, and if I were to run the PEID against it, it would show me that it is UPX packed. So it's got the packer built into it. So that's packing and some automated tools that you can do packing and malware creation with. In this lesson, we're going to be looking at more ways to do some program analysis. I'm going to start under Linux here, and there's a couple of utilities it's worth knowing about. strace, which is going to trace the system calls that are used with this particular program that I'm going to run. So this is sometimes useful to see what's going on inside the program. This is one way of doing some static analysis and a little bit of dynamic analysis in terms of the different system calls. Now I can do the same thing with library calls. So we've got system calls and library calls, and I'm going to use ltrace, and in this case there's not really much. There's malloc and strncopy, and that's really all that's involved in this particular program from a library perspective. So a couple of different ways you can see what's going on the Linux side. I'm going to look at a couple of others on the Windows side now. The first thing I've got here is the Process Explorer. And the Process Explorer shows me all of the processes. It's kind of a more detailed version of the Task Manager, and it provides me a lot of really useful information. So it shows me the process as well as the process ID and the amount of CPU that's being used, as well as the amount of memory. You can see when I run my mouse over one of the processes, it shows me the command line as well as the path to that particular executable. So that's useful to have. Now, if I were to just double click this, I would get a property sheet with a lot of useful information as well. So I've got my parent process ID here on the bottom of the page. I've got the user that it's being run as well as the date and time that it started, and you can see that it's a 64-bit image. I've got some performance statistics, so it shows me the CPU priority, the kernel time, the user time, the total time, information about virtual memory and physical memory, as well as I/O information, the reads and writes, and the number of bytes that are involved in both. A performance graph, I've got the disk and network, so I can see how much network it's used. I've got a graph for the graphical processing unit, and I can see here the number of threads that are involved. So I've got 3 threads for this particular one, and it shows me what the start address of the particular thread as well as the thread ID. I can also see these individual thread IDs. It shows me the number of cycles and context switches, all sorts of useful information about what's going on in the CPU. I can see information about TCP/IP, so there's a local address and a remote address associated with connections here. And then I've got some security information. There are different settings and privileges here. And I've got my environment variables. And also this will show you all of the strings that are stored in this particular binary or executable. So you can see there's a lot of information here in Process Explorer, and you can do a lot of digging with the different processes to see what they're doing and what they're involved with. Now I've got another one here called Process Monitor. Process Monitor is in some ways a little bit like strace. I can see the process name, and I can see the operations that the process name has done while this has been running. So I can see this prl_cc.exe. It's done several operations, and these are like library or system call operations. So I've got a notify change directory, a create file, and I've got several of those. I've got a registry open key on behalf of explorer.exe, and it shows you the key that it's opening. And on the right-hand side, you'll see the detail about it. Query name and query handle tags. So I've got registry opens and registry closes and registry queries. I've got read files. It tells me the offset in the file as well as the file length and the I/O flags. I've got more registry information and registry querying going on by Explorer there. And we're back to PRL_CC. It's doing a query information volume. So you can see all of the different operations that are running on your system. And if you want to get really detailed information, you can look at this process monitor. And here's where I can actually get the stack trace. And it shows you the module that was involved for a particular call and the location and the address. So again, if you're doing some analysis on malware or just executables in general, here's some different tools that you can use. We looked at ltrace and strace on the Linux side, and on the Windows side, you can use Process Monitor, and you can also use Process Explorer. One of the other functions of Process Monitor is I can enable boot logging. So if I turn this enable boot logging on when I boot up the next time, it will generate a dump of all of the things that were involved in the boot, and that can help you find bootloader viruses and bootloader malware. So lots of really useful tools for getting a lot of really detailed information. In this lesson, we're going to be talking about denial of service attacks and distributed denial of service attacks. So there's actually a difference between a denial of service attack and a distributed denial of service attack. Where a denial of service attack, the goal is just strictly to deny service to a particular resource, whether it's an application or a system. A distributed denial of service attack actually looks to accomplish the same goal with a host of coordinated systems. So a fairly large number of systems get told to simultaneously do a particular action that's launched at a target. That would be a distributed denial of service attack. A denial of service attack would be if I were to launch a SYN flood against you. A distributed denial of service attack actually requires an additional piece of software. So one of the very earliest pieces of software available to do distributed denial of service attacks is this program called Stacheldraht. And Stacheldraht is German for barbed wire. It actually came out of the work of a guy by the name of Mixter, who wrote the Tribe Flood Network. And subsequently, the Tribe Flood Network became this other piece of software called Trinu. And finally, we end up with this thing called Stacheldraht. Now, Stacheldraht, in addition to having the ability to do denial of services, has a command and control network. And by command and control network, I mean it has a bunch of clients or bots out in the internet somewhere. And somewhere else, there's a master server that tells those zombies or bots or clients what to do. So you have this client, and it has to know where a particular server is. So I've actually got the source code here for this, and it's asking me for a host for the master. So when I actually build it, I need to know who the master host is. And I actually need to know two of them because it's going to ask me for two different master hosts. And in this case, it doesn't actually build, but you can see that this is one of those cases where they didn't create configuration files. The master hosts are actually hard-coded into the application, and they're done during the make process. We run this program called setup, and it actually asks for the master host, and then it gets built into the client application. The other thing that you can see here about this is it's using encryption. That's the blowfish.c. It's using a blowfish encryption cipher in order to encrypt the communication between the master and the client, or the master and the zombie. Makes it a little bit harder to see what's actually going on. But again, in order to do this distributed denial of service attack, you need an additional layer. And that additional layer is usually in the form of a master-slave, master-zombie, client-server sort of model of software, where you have a master directing the activities of a bunch of zombies or slaves or clients, whatever the terminology you feel most comfortable with. For a long time, they were called zombies, and more recently, as the term botnet has really taken hold, they're often called bots. But it's still the same thing. It's somebody's desktop system at home that's been infected with this software, and the user doesn't actually know that it's there, but their system is being used to do a number of things, from sending out spam to attacking different sites to any number of activities. So that's really the big difference between a denial of service and a distributed denial of service, where the distributed denial of service requires a coordinated effort on the behalf of several slaves or zombies, potentially hundreds of slaves or zombies, all doing the same sort of activity, and they get directed by this master host that's sitting around somewhere talking to all of them. So you get a command and control infrastructure, typically, that comes with the software required to actually do a distributed denial of service attack. In this lesson, we're going to be talking about DOS attacks, or denial of service attacks, as opposed to disk operating system attacks. So let's talk about some denial of service attacks. And what I've got here is the website packetstormsecurity.org. And Packetstorm Security goes back a long ways now. It actually got bought by, I believe it was Symantec, it got bought by, and eventually got spun back out, and so it's independent again. One of the things that makes Packetstorm Security really useful is that they store a lot of files and a lot of information. So I can do this search here, and I can look up some information about a denial of service attack. And I'm looking up Nestea, and I'm not looking up Nestea as in something I want to drink. There is a particular denial of service attack called Nestea. And you can see, if I click on it, it actually shows you the source code for this particular type of attack. So this is a particular denial of service attack that was popular a dozen years or so ago. It doesn't really work so well anymore against modern operating systems because it took advantage of some vulnerabilities in the IP stacks that have pretty much been cleared off. So Nestea was, as I said, a popular attack a dozen years or so ago. And there are several other attacks, many of which don't work so well anymore. This is a pretty good attack tool, and it's spike.sh, and what it does is it kicks off a lot of different types of attacks. And again, these are all sort of old school attacks that work against like out-of-band information in packets. They work against vulnerabilities having to do with broadcast systems, like a Smurf attack was a ping message that you sent to a broadcast address, and all of the systems within that network would reply because they got it since it was sent to a broadcast address. That type of attack has long been closed down in most of the world, although there may still be ICMP amplifiers or Smurf amplifiers around in the world. You can do the same sort of thing with UDP that you can with ICMP, and that particular type of attack is called Fraggle. And we should see a lot of other attacks here, like you can see the Nestea, and there's also a teardrop and new tier. Those are all related attacks. There's also the Smurf attack here as well, and there's the land attack, which was an out-of-band message attack against Windows systems. You can do a ping flood. There's a Jolt and a Coke and a Pepsi and La Tierra. So if you want just a list of a lot of different old school kind of attacks in order to figure out what you want to look up here for source code, you could go to spike.sh, and as I said, here's just a list of all of the different types of attacks it supports. Just for fun, let's look up Pepsi and Coke. and see what we've got here. So here's Pepsi.c, and here's the source code, and right here's the usage. They'll happily tell you how to make use of it, and it doesn't look like there's anything in here to actually tell you what it does if you don't actually know. But there's that one. Let's take a look for Coke and see what the Coke attack does. And they don't actually have the source code here for Coke. And it looks here like Coke was another out-of-band attack to the 135 port. But Packet Storm Security has a lot of useful information. It's kind of a news clearinghouse, and as I said, it stores a lot of files as well. If you want to get into some old school DOS attacks, and understand how they work and get a better understanding of how they are coded, and you want to run them against different systems just to see what they look like and do Wireshark packet captures and see what the packets actually look like, you can just grab these from PacketStorm and you could compile them and get them running and just run the attacks and see what they look like. But that's a number of different types of denial of service attacks that you're going to run across, and these are, like I said, very old school attacks. More commonplace are where you're going after the application and trying to send malformed data, which of course these are going against as well, but most of the old school ones are going against the actual operating system or the IP stack. And since we've cleaned up most of the IP stacks out there and gotten rid of those vulnerabilities, what's left is really application level attacks or just simple flooding attacks. As people get more and more bandwidth, it doesn't cost nearly as much to just send a whole boatload of data to somebody and just see if the application can handle it or if their connection to the internet can handle it. So that's denial of service attacks. In this lesson, we're going to be talking about cybercrime. Now, there's a reason for talking about cybercrime. There's actually a couple of reasons for talking about cybercrime. One of the reasons for talking about cybercrime is criminals who are involved in this are using many of the same strategies and tactics as what we are discussing here. So while it's certainly good and useful to know this type of information, it can definitely be used for malicious purposes, which of course one of the reasons why we study it, because we want to know what the bad people are doing so that we can protect ourselves against it. So we need to understand the different types of attacks so that we can understand how to mitigate them. Another reason for talking about cybercrime is one of the reasons why companies are hiring ethical hackers and doing penetration tests is because they're concerned about cybercriminals and their effect on their security posture and what their risk profile looks like. And here's an example of that. Does cybercrime really cost $1 trillion? So General Keith Alexander of the NSA is talking about cyber attacks and their actual cost. So cybercrime, there's no question, is a very costly thing. It's not only costly for individuals because their identities are being stolen, their credit cards used, credit card fraud, and all sorts of other information being made use of, not to mention just the resources of having their computers taken over and the time involved in cleaning those up once they're discovered and the potential loss of data. There's a lot of cost associated with individuals being attacked by cyber criminals. There's also a pretty significant cost to businesses being involved as well. So businesses can be the target of cybercrime, and you can see here from this article, they're suggesting that because the US and Israeli governments were involved in Stuxnet, that could actually increase attacks against US firms. And they're saying the U.S. painted a target on its back because they were involved in these attacks, and there's a suspicion that there may be retaliation against U.S. businesses. Now, it's been alleged for a large number of years that the Chinese have been involved in cybercrime, and portions of the Chinese army are dedicated to these sorts of activities. Not only are they involved in espionage from a governmental standpoint, but they've also been alleged to be involved in the theft of intellectual property. Several years ago, there was a pretty famous case where Cisco accused the company Huawei, which is a Chinese company that manufactures networking equipment. Cisco accused Huawei of stealing and making use of significant chunks of its Internet Working Operating System, or iOS, which is the software that operates its Cisco routers and switches. So Cisco has alleged that Huawei got a pretty significant leg up by making use of Cisco intellectual property. And this is a case where lines really kind of get blurred, because if the allegations are true, you not only have cyber criminals in China, but they are affiliated in some way with the Chinese government, whether the Chinese government is aware of it or not. Again, that's if the allegations are true. But this is something that's been alleged for several years now, and there are people who claim they have some significant evidence indicating that that's true. It's not the only place where cyber criminals reside, though. Cybercrime is all over the world, and cyber criminals are there. And the reason why is because we don't understand security nearly well enough, or don't practice good security habits nearly well enough on our individual systems or our enterprise systems, in part because there's no real return on investment. If you spent $10 million on security, you're not going to say, hey, I added $20 million to the bottom line because I spent that money. It's really sort of you throw the money away right up until you actually need it. So in that sense, it's sort of like insurance. You keep writing checks to the insurance company, you never have an accident on your car. It's kind of like you're throwing money away right up until the moment that you have that accident. So spending on security is kind of the same, where companies don't spend a lot, sometimes because they don't see the value of it, but in not spending that money, they open themselves up to theft of intellectual property, theft of resources, theft of money directly in some cases, if you can get hold of banking information, for example. So cybercrime is a real big problem. And sometimes cybercrime isn't as straightforward as just criminals looking to steal something. Here's a case of the group Anonymous attacking Sony because they were protesting a lawsuit against somebody who was involved in trying to make alterations to PS3. So Sony sued that person, and this group Anonymous went after Sony. Now, Anonymous got hold of some information from Sony. Is that cybercrime? Did they cost Sony any money? Well, we do get into some blurry areas a little bit here. It's definitely a case of hacktivism, and it may also be a case of cybercrime. But there's absolutely no question, this particular case aside, that there are cases of cybercrime. They go on all the time, and law enforcement agencies are well aware of them. For years and years now, law enforcement agencies have started creation of cybercrime task forces and other organizations within these law enforcement agencies in order to attack the problem of cybercrime. In this lesson, we're going to be talking about botnets. If you don't know what a botnet is a network of bots, not surprisingly. And what we mean by a bot is it's a computer system that's got a piece of software that basically turns it into a zombie or a robot carrying out the wishes of some master somewhere. And so what we've got is a network of all of these little slaves or zombies running around performing tasks given to them by a master from a command and control server network. Now, typically botnets are used in carrying out criminal activities or annoying activities. For example, spam. You could argue in some cases that spam is illegal, but it's certainly annoying, and botnets are sometimes used to send out spam. They are also used to spread viruses and perform attacks and just generally commit other types of crime and fraud. So that's what a botnet is. Now, why are we going to study botnets? Well, one of the reasons for studying botnets is you may actually run across botnets as part of your ethical hacking activities, and it's useful to know what it is and how it operates. You also may have a very slim chance of actually deploying your own botnet as part of your ethical hacking activities, and so it's useful to understand what botnets are from that perspective. That's sort of dependent on the rules of engagement you have with your target as to whether a botnet would be useful for you. Finally, another reason for understanding botnets is understanding the protections that may be in place at your target, because they're concerned about botnets or the vulnerabilities that may be exploited if there's a botnet that's available somehow. You may be able to get in through the botnet infrastructure, or you may be able to exploit the same vulnerabilities that the botnet used in order to get in to begin with. So again, there's lots of different reasons why botnets are used. In this case, here's an example of a botnet that was used to spam different people, and this is the Grum botnet. And there was some activities by different engineers who were involved in taking this particular botnet down, and there have been a lot of activities actually in recent years focused on taking different botnets down. Occasionally in the news, you'll hear stories involved with the FBI and a command and control network. DNS changer is a fairly recent example where the FBI was involved in this particular botnet that had this DNS changer software, and so they took control of the command and control network in order to extend its capabilities so that people wouldn't lose their internet because they no longer had working DNS. So here's another botnet here, and we've talked a little bit about Zeus. And Zeus is a botnet, but what it really is primarily is a toolkit that provides somebody with the abilities to build and administer their own botnet. So Zeus is a toolkit that generates this piece of software that can be installed. And the interesting thing about Zeus is that it's one of those things you have to purchase. And you can see here where it's talking about the latest version of the toolkit typically sells for about $700 only to trusted buyers. So it's not one of those, hey, I want to buy this, and you can just go down to your local computer store and buy a copy of Zeus. First of all, you have to know somebody who has it or is distributing it, and you have to be trusted by them in order to actually purchase it. And we do have a copy of the Zeus builder here. We've looked at this before. We will be looking at it in subsequent lessons a little bit in more detail as well. So that's the Zeus builder. Now, botnets actually go back for several years, and we've talked a little bit about the history of botnets and where they got their start. Here's an example of an analysis of one of the very early botnets called the Tribe Flood Network. And the Tribe Flood Network is written by a guy by the name of Mixter, or he goes by the name of Mixter. And the Tribe Flood Network is used on compromised Unix systems on the internet, and it was used to implement distributed network denial of services, doing things like ICMP floods and SYN floods, UDP floods, and Smurf-style attacks, which end up having the same sort of result as an ICMP flood. You could also get just a shell on the system of the computer that had this particular botnet client installed on it. So this goes back to 1999, and we were dealing with some of the early proof of concept origins of botnets at that point, and certainly by early 2000, we were dealing with the repercussions of those botnets as they were used to take down a number of sites on the internet or partially take them down. And there was definitely a lot of anxious moments over the course of a few hours as we were dealing with trying to figure out where the attacks were coming from and trying to mitigate them as best as possible, given the sorts of tools that we had available at the time. So again, botnets may be something that you run across for a variety of reasons. You may actually need to be able to implement one yourself, or you may be able to take advantage of vulnerabilities that they have either introduced or taken advantage of, or just in general, a company that's got a botnet or a target that's got a botnet installed inside of it. You can get a better understanding of what their taste for risk is and what their willingness to spend money on their security infrastructure is. So lots of different reasons why understanding botnets a little bit better is a good idea. In this lesson, we're going to be talking about attack countermeasures. So we're going to talk about some countermeasures for network attacks and specifically some flooding attacks. So it's useful to know countermeasures to attacks, partly because as you're working with your target as part of your engagement, you're going to want to educate them on the way to mitigate the problems that they have. That's where your best value is going to come, is from being able to help them solve their problems. It's not really useful for somebody to walk up and say, hey, look, you've got a door that I can break into easily. What's going to provide them some benefit and some value is to say, hey, look, you've got this door that I can open really easily. And by the way, here's how I opened it. And even better, here's how you can fix it so nobody else who may have more nefarious schemes in mind is going to be able to attack your door. So let's talk about from a Linux perspective here, because this is really useful to know. Let's talk about IP tables, which is the firewall software that is part of most Linux systems. And if it's not actually part of the Linux system that you've got, it's certainly something that you can go get. So this is a list of IP tables rules, and they look a little bit cryptic and a little bit mystical perhaps, and maybe a little bit confusing. But once you know the basics, you can start sorting out what it all means. First of all, IP tables rules are created by running the IP tables program and either adding or inserting rules or making changes to policies. So at the beginning of every line here, you'll see IP tables. This isn't a rule per se as much as it is a command and a set of parameters that's going to put a rule into place in memory for the Linux kernel to obey as it's looking at network packets. So the first thing I've got here is just a flush. We're going to flush all of the existing rules. Now we've got 3 policy statements, and there are a number of different chains and tables that you deal with IP tables, and that's where it gets a little confusing, is chains and tables. And what we've got here is 3 different chains, and I've got an input chain, an output chain, and a forward chain, and I'm going to set a policy, that's the -P, that I'm going to drop everything. So by default, everything through this IP tables firewall is going to get dropped. Then on line 5, we start doing some specific things. So with this one, I'm going to say on my input chain, in other words, packets coming into this system, anything with a source address of 192.168.1.0 with a network mask of 255.255.255.0. So those 254 or so hosts in that network, I'm going to say accept those. The next rule is a useful one to prevent attacks, because often you'll get spoofed packets as part of attacks. And here's a packet that you're never going to see on the open internet. It's one of the RFC 1918 addresses, and that RFC, request for comments, defines a series of addresses that are for use on private networks, and by convention, those addresses are not routed. So on the open internet, you're never going to see the 192.168 block, you're never going to see the 10 block, and you're also going to see a range of addresses starting at 172.16. So these next two rules on line 6 and 7 here are both about the RFC 1918 addresses and how you would block messages from those addresses from coming into your system, because if you're not using those on your local system, then you're not going to see them, or you shouldn't see them as part of normal day-to-day activities. Now, I've been using source addresses here to specify rules. I can also specify interfaces. If I've got multiple interfaces on a system, let's say I've got an ETH1 and an ETH0, and my ETH0 is on my internal network, I could specify that on ETH0, if I see a source of 192.168.1.0/24, I'm going to accept it. Similarly, if I had an ETH1, I could have that rule say -I ETH1 -S and then the network address, and I could do a -J drop. Because outside of my internal network interface, I should never see that address on the external interface. So the next couple of rules are all about allowing for pings to go out. So I've got an echo request on line 9 that's allowed to go out, and then I can allow the echo reply back in. Because I don't have any state associated with that, any echo replies are going to be allowed back in, whether they're attached to an echo request or not. So this could open the door to some flooding attacks with echo replies. Now, the next rule is where I start getting into some state rules. You can see that on line 11, I'm allowing destination port 22, and I'm going to match based on state. So IP tables keeps a table of state flows where if I am sending an SSH communication out, then it knows that that's established. So I've got an established connection through the firewall because I originated it, I allowed it through, and it now knows that it has an established connection. So on this rule on line 11, I'm going to allow a new state and an established state to go through, and I'm going to accept that. And on my output chain on line 12, I'm going to allow established messages through. So what this would be is if you've got the firewall sitting in front of an SSH server, I'm allowing new and established messages into the network, and I'm allowing established flows out of the network. So the next one, we start getting into rate limiting. On line 13, we're doing some rate limiting to the HTTP port or the web port. So I've got my D port is 80, that's my destination port. And on the M, I'm doing a limit. And so I'm going to limit that to 25 connections per minute, and I am able to burst up to 100, and I'm going to accept that. So anything beyond that isn't going to be allowed. Anything beyond that rate limit is not going to be allowed, and that's going to help prevent flooding attacks against my web server. So the next line on line 14, I am doing a similar sort of thing. I'm allowing related or established messages through, and I'm doing a limit of 50 per second with a limit burst of 50. And that is not based on a particular port. That's just in general over the entire interface. Any packet that comes through, I'm going to do a rate limit on it. So another thing that I can do to protect against network attacks is I can drop messages with an invalid state. You can see on line 15, I'm checking against state. If the state is invalid, then I drop it. Something else that's going to be useful is the ability to log. So I've got a bunch of things, and maybe I don't always want to drop them. I want to log them and send up alerts so that I can see what's actually going on. In line 16, I'm doing something where anything with a source address of 42.42.42.42, I'm going to log that no matter what port it's going to, no matter what port it's coming from. I don't really care about services at that point. I'm just looking for anything from that one IP address. I'm going to log the connection request, and then on line 17, I'm going to drop it because I don't want to just log it, although I do want to alert on it. I want to drop it as well. So IP tables can be a really effective tool when it comes to attack countermeasures and preventing and protecting against network attacks like flooding. In this lesson, we're going to be talking about web application testing. Specifically, what is web application testing? Web application testing is where you go to a website that's got some functionality that is programmatic in nature. In other words, it's interactive with the user, and that becomes a web application. And I need to be able to test the functionality and security of that web application. Now, in order to perform web application, I need a tool that's going to do that for me. And usually you end up using a browser as part of your tool set. And I need to do some configuration so that I can run through my tool. And the tool that I'm going to use here is one that's called Burp Suite. Now, Burp Suite is an intercepting proxy. It's a proxy-based web application testing tool, and it requires a browser to be configured to go through it in order to do some of the testing. So I'm going to go to a web application page, and I've actually got to pop up Burp Suite because it's intercepted the request and I want to forward it on. So I'm going to turn off the intercept there rather than continue to forward. So there's a website that I've got, and it's part of the Vicnum project, which is an OWASP project, and it's got a lot of different vulnerable web applications, and there are several common security problems here. So I'm going to use this as the foundation to talk about web application testing. So what I would do in order to do web application testing is, in this case, I'm going to go back to Burp Suite, and then I'm going to go back to my target. And here's what I've got for a target. And you can see some related links there. I actually want to spider this and get a list of all of the pages that are on this particular website. So web application testing is pretty comprehensive. You've got to find all of the functionality for the application before you can start testing. And part of that finding the functionality has to do with getting a list of all of the pages that are involved. So the quickest way to do that, rather than manually clicking through all of the links, is to just use a spider. So that's what I've done here. I've used a spider, and I've got a list of all of the pages from this particular web application, and you can see I've got them all right here. Now, in order to do web application testing, I've got to do the spider. Once I've done the spider, I can actually do a scan of this particular web application, and I'm going to kick off a scan, and then I can go over here to the scanner tab, and you can see that it's found a number of results already. I've got a couple of cross-site scripting, and we'll talk a little bit later about what cross-site scripting is. And you can see all of the different types of problems that we've got. Some of these are going to be issues that we can exploit, and some of them are simply ways to get additional information about the web application that you may be able to use to do some attacking of it later on. But in general, this is what web application testing is. There's a lot of manual work that's involved. Even though I've done a scan here, I'm going to have to do a lot of manual effort later on, either to verify the results from this scanner, because scanners aren't always 100% accurate. We need to make sure that what they have found is legitimate. And there's a lot of individual pages that I want to test in more detail than maybe this scan is going through. So web application testing is really about finding all of the functionality that's involved in a dynamic website that has some programmatic access, which makes it a web application. and I need to find that functionality, and then I can go ahead and do some testing in order to find problems like cross-site scripting, cross-site request forgery, SQL injection, and those sorts of things. So that's web application testing. In subsequent lessons, we'll get into more specific types of web application testing and how you would go about doing those. In this lesson, we're going to be talking about web application architecture. Now, there's a lot of different ways to do architecture for a web application, and some of it has to do with the types of components that you have. Some are more complicated than others, and some are simpler and don't require nearly as many components. So we're going to talk at kind of a high level here of what the different pieces that are involved in a web application and the architecture for that web application. So at a high level, what we've got is the presentation layer and the user interface components and the process components, and those would take place in a browser. So all of your presentation layer would be done in a browser. That's where your user interface would be. That's where all of the different components that manage the user interface and any processes that were involved in that user interface. For example, you may have JavaScript to verify that particular form fields are filled in. That would all take place as a process component within the browser. Now, at some point, you've got some data that you want to send to the web server. And what you're going to do is send it off to the web server. And in that case, you would go through the services interface, which would be the web server. So the web server would handle all of the HTTP requests. It would handle serving up HTML. It would handle all of the static components involved in your web application. When you had dynamic components, your web server may or may not have the ability to do this depending on what web server that you're using and what application layer components that you're using. But beyond the services layer, what you need is an application server. So you may have a Java application server like JBoss or Tomcat. You may have Ruby on Rails. You may have some other type of application server that's responsible for your business logic. And that has to do with any workflows and any business components. It handles all of the business logic layer. And that's where all of your application logic would take place. So anything that involves transforming data or massaging or manipulating data in a particular way, that would get handled at the business layer or the application server. So again, we've got the front end, which is going to be the client or the browser sitting on the client's desktop. And then that communicates with a web server, and the web server communicates with an application server that's either a component of the web server or it's something the web server forwards on to a separate either system or application, and that would be the application server. Behind the application server, we've got the data access layer and the data storage, and that would be the database server typically. The data access components would reside in both the application server as well as the database server. So the application server has to have the ability to make connections to the database and store and retrieve information out of the database. And then the data stores, obviously you'd have the database, and the database would manage the physical storage on the storage device, as well as indexing it and keeping it all together and in a way that can be accessed quickly and efficiently and easily. So that would be the database server. So we've got 3 tiers or so, maybe 4 tiers, depending on how it's all done. You've got the presentation layer, which is all handled in the browser on the client side. That connects to a web server, which may have an application server that's a component of it, or it may be a completely separate component. And then we have the database server. So that's kind of a 4-tier model of a web application. And these different servers may or may not compose physical servers. They may just be services that all reside on one physical server. They may also be multiple virtual machines inside one physical server. But the idea behind the architecture is at a high level, you break out the individual components to their functional details, and that's how you would organize an architecture and represent it. And that's more or less what's done here. So that's a web application architecture. In this lesson, I'm going to be talking about web testing tools. So there's a lot of different types of web testing tools that you may make use of. The first one that you're going to need, obviously, is a browser. And I'll get into the browser a little bit more in just a couple of minutes here. The first thing I want to talk about, though, is a web application scanner. And in this case, I'm using Burp Suite Professional. And that's a pretty good web application scanner that comes at a pretty reasonable price. It's got a lot of functionality in it. It's got an intercepting proxy, which is useful if you want to test the application and be able to manipulate data outside of the context of what's going on in the browser. So an intercepting proxy is really useful. You also want something that's going to be able to quickly and easily get all of the pages in the website, and that's your spider. Now, you also need a scanner, and of course, that's here in Burp Suite as well. Burp Suite also has some other capabilities, like there's an intruder, a repeater, a sequencer, a decoder, and all of those are useful for different purposes, and in subsequent lessons, we'll get into some of the different purposes that these types of functions have. Another tool that's similar to Burp Suite is the Z Attack Proxy by OWASP or OWASP. Now, the Z Attack Proxy is actually based on an older proxy called Peros, and it's got some other functionality built into it. And you can see that there's a lot of capabilities that are more or less the same. It's an intercepting proxy as well. You can see the request response. And there's a tab for doing spiders. You can do a scan with it. And one of the things that this has is a fuzzer. Now, I can also do some fuzzing attacks with Burp Suite. That's done with a piece of the application that's named differently. Zap actually has a component that's called fuzzer. And fuzzing you can do a lot of different things with, from doing SQL injection potentially to just manipulating pieces of data in particular ways in hopes of trying to break the application. So that's got the fuzzer component here inside of Zap. There are several commercial products that are available, from Sensix Hailstorm to HP has Web Inspect, and there's other ones that are available as commercial web application scanners. There are also other open source tools that are available, like Nikto, for example, where you have some command line ability to do web application scanning, and it's less proxy based than it is just going out and running a number of attacks to see what it can get. Let's get back to the browser, though. With the browser, I have the ability to do add-ons. And what I can get with add-ons is some functionality that's directly in the browser that will allow me to do particular things. Like I can get a tool called Tamper Data that will allow me to manipulate requests and responses from more or less right inside the browser without actually having to fire up a separate proxy to get the intercepting component. I can run things like cross-site scripting attacks or SQL injection attacks in an automated way with some different add-ons. There are add-ons that provide toolbars to do decoding and encoding and those sorts of things. So there's a lot of different abilities that you can add into the Firefox browser because of the large number of people who are working on these add-ons so that they can have them available in their browser. The browser has become far more than just, hey, let me display a web page for you. With add-ons both in Firefox and in Chrome, and to a lesser degree in Internet Explorer, you have the ability to have a program or an application where you can bolt a lot of different functionality onto it outside of just the core function that it was originally designed for. So add-ons provide a lot of power to the browser and certainly give some additional and sometimes very unique testing tools that you can run from right inside of the browser. So from a web application testing perspective, again, you probably want some sort of scanner like an intercepting proxy that has some scanning abilities. Obviously, you have to have a browser. You may want some different add-ons to go into your browser, and you may need some additional tools as well, but that's certainly the core of what you're going to need to get started to do web application testing. In this lesson, we're going to be talking about cross-site scripting. Cross-site scripting actually is a bit of a misnomer almost. What it really is the ability to have scripts execute from inside form fields in a web application. So there's a lot of value in doing that, although what you usually see to prove it is just popping up an alert box, which isn't particularly interesting. What you can use it for, though, is to manipulate the page and also grab data from the user's machine, whether it's cookies or whether it's some other type of information that JavaScript has access to or another scripting language has access to. That's what cross-site scripting is really all about. The goal of cross-site scripting is primarily to obtain information and to do malicious things. Now, there's a couple of different kinds of cross-site scripting. One type of cross-site scripting is what we call persistent cross-site scripting. Persistent cross-site scripting simply means that it's stored somewhere that it can be retrieved later on. Non-persistent cross-site scripting means that the script element needs to be plugged into the form field at the time that the page is accessed. So there needs to be some sort of social engineering attack that goes along with that type of cross-site scripting. So if I were to just do some testing for cross-site scripting, what I may do is something like this, and just see whether I can actually get this to execute here. As I said, the alert box is kind of the classic check for cross-site scripting, and I'm going to see whether that actually works or not, and I get an error back. So because I ran a scan on this earlier, this actually says that guessnum5.php is something that's vulnerable to cross-site scripting. So I can go back to my browser here, and it says guessnum5.php was the page that was vulnerable. Oh, and this is really helpful because it has information about the database query that's being used. So you can actually see the query that's being used here. And we'll get into SQL attacks a little bit later on. So let's try it here. Let's try the same attack here in the search field. And that attack actually worked. So that field is vulnerable to cross-site scripting. So you can see it popped up an alert dialog box that said hi, just as I had told it to with this script here. Now imagine if that script was doing something like grabbing a cookie and transmitting it back to somewhere so that somebody may be able to log into, for example, Amazon on your behalf. Now, Amazon, I'm not saying is vulnerable to that type of attack. I'm just using it as an example of something that an attacker may be able to do would be to potentially log in as you to another website if there were other conditions that were available, like the cookie was vulnerable to not being associated with a particular machine, for example. So we'll talk about cookies in a subsequent lesson. But that's really what cross-site scripting is all about, is the ability to plug JavaScript or VB script or some other type of scripting language that the browser supports into a form field and having it execute. And that's really the essence of cross-site scripting. And as I said, there's a lot of potential really negative ramifications to applications that don't have protections against that. In this lesson, we're going to be talking about SQL injection. Now, SQL injection has a different goal altogether, or potentially a different goal altogether, than cross-site scripting. Where cross-site scripting is targeted at the browser or the user specifically, SQL injection is targeted at the web application infrastructure and, in particular, the database server. So a SQL injection attack is really targeted at doing something to or with the information that's stored in the database. One attack for SQL injection is if you are using a SQL database to store usernames and passwords, you may be able to do a SQL injection attack that would allow you to log in to a site without actually passing the correct username and password parameters. You could also get data back from the database depending on whether there is a vulnerability to SQL injection in the web application. So theoretically, I can issue queries directly to the web server. So I could issue a SQL query and just see what I end up getting back. In this case, I actually get a useful error back. So it's showing me the select statement that it's using, and it also gives me the user that is being used to access the database. And worse than that, it's actually saying there's no password for that particular user. So the www-data user on the database server has no password. So that's kind of interesting to know. Now, that's just kind of a manual attack, and there's a lot of different ways of doing SQL injection attacks. And I can actually use Burp Suite to do those types of attacks for me. So I'm going to go back to my target, and I'm going to find Union 1. So I'm going to send this to the intruder. And I'm going to go back to the intruder tab, and I've got my attack target, and then I've got my positions here. And you can see it's got some things highlighted. Those are different payload fields. And I'm actually going to select a sniper attack, and I'm going to, for payload set 1, I'm going to add in a SQL injection attack. And you can see these are all of the different ways of potentially doing SQL injections. I'm going to change my payload set. I've only got one payload set, so that works fine. And I don't really have any options that I want to play with, so I'm going to start my attack here. Now I'm running a SQL injection attack, and you can see I'm getting 200 OK messages back, but I don't really know what those look like. And so what I'm going to do is I'm just going to grab one and pop it open and see what I get. So this is the request, and let me take a look at the response and see what I get. And this is the raw HTTP. And in this case, I get the error again. So we can take a look for some of these others, and I'm going to look at the response. And again, I'm getting the errors from these SQL injection attempts. So definitely there are some problems with the SQL here, and it's generating a lot of errors which could be used for other types of attacks. But again, these are the different types of payloads that Burp Suite has that they would run SQL injection attacks with. And again, the goal of an SQL injection is to get the database to do something that it wouldn't normally do, whether that's to provide you access or to provide a bunch of information back. And as you can see here, there's a lot of different potential ways of performing a SQL injection attack. So it's not as simple as, the place that I started with, just close a quote and provide some SQL on the back end of that and hope that that works. So there's a lot of knowledge of SQL that's involved in being able to perform SQL injection attacks and get them to actually do what you want them to do. But that's SQL injection attacks. In this session, we're going to be talking about cross-site request forgery. Now, cross-site request forgery is a technique where you can get a user to perform a function on a web application without them actually being aware of it. So cross-site request forgery, which is sometimes known as get for post, is where you're actually sending data to the server where you're using a get request rather than a post request. Post requests are requests where you're sending data to the server, and get requests are where you want to get data back from the server. So you can see there's an example here of where this is potentially a cross-site request forgery, and this may be a get for post sort of thing. You can see there's a request here that's a get, and it's actually got some parameters, or what looks like parameters here, where the question mark C equals D, semicolon O equals A. So it looks like there's a couple of parameters there, and that's in a get request. Now, if you're sending parameters for some sort of query or some sort of CGI interaction with the web server, you really want to be using a post. The reason for that is a get request can easily be stuffed inside of an image tag. So in this case, I could create a web page with an image tag in it that has a 0 size, and so the image that's really non-existent won't show up on the page, but what the image source is going to be is this particular request. And so if you have access to this web application and I can get you to go to the page that has my particular image tag in it, you're actually going to be generating the request from your browser to the server where this is located. You're not going to know it because the request is actually buried inside the HTML, and the image tag generates a GET request. Since this server appears to allow GET requests with parameters, there's a possibility I could get you to do something on this server without your knowledge. So that's cross-site request forgery, and it's all about putting together an attack where I can get you to go to a page without you actually being aware you're going to a page. And that's because I'm using something like an image tag to store the request in. When you go to this particular page, your browser is by default going to start pulling the images, including generating this programmatic request, which could be something like a balance transfer at a bank website. It could be a server shutdown. It could be any number of things that I may be able to do with this particular technique. So again, this is sometimes called a get for post vulnerability, where you're allowing a get message where you should be using a post. And in this case, when you're programming the site, you really want to make sure you're paying attention to the HTTP request and making sure that if there's data that's being sent up to the server, that it's a post and not a get request. And that's because it's a lot harder to forge post requests without the user being aware that something is going on. Get requests are trivial to manufacture and get you to actually generate a get request that you're completely unaware of. And here's an example, actually. So I was going to this 192.168.1.39, and you can see at the bottom of this window on the left-hand side, there are 4 sites that were referenced in the various pages on that site. I had no idea. I wasn't going to any of those. I wasn't going to ciphertext.com, but somehow there were requests issued to go to pages on those 4 different sites, and they all originated from pages on this one site that I've been working with. So there's definitely some danger in cross-site request forgery and allowing GET requests where you should be using POST requests instead. And that's cross-site request forgery. In this lesson, I'm going to be talking about session hijacking and session-based attack. The thing about HTTP is, even though it's a pretty good protocol for transmitting information back and forth between web server and client, it was never designed with application programming in mind. It was really just a way of sharing simple documents that had references to other documents built into them. That was really its initial design. And frankly, it was really about sharing laboratory research papers between scientists. That's kind of what was the original intent and purpose. It has really taken off to a far greater degree than probably Tim Berners-Lee ever had in mind when he first formulated the idea of HTTP and HTML. So HTTP is not a stateful protocol. In other words, the HTTP server has no idea that I've been there before. It doesn't keep track of any sort of state involving me. So if I go to a web server and I issue a request and then I go back to issue another request, the server itself has no logic built into it to say, I recognize you. So as a result of that, web applications have needed to develop their own capability to do sessions to manage state. So a web application would generate a session ID for me and then keep track of that session ID. And if I were able to capture that session ID, I may be able to make use of it in order to hijack your session and use it for something. So for the example of shopping online, if you're going to a business online to do some shopping, and again, I'm going to pick on Amazon just because it's easy. I'm not suggesting at all that Amazon has any of these sorts of vulnerabilities at all. It's just if I say Amazon, people generally know that we're talking about web shopping. So let's say you go to Amazon and they generate a session for you because of this shopping activity that you're doing, and your session ID attaches you somehow to a shopping cart as well as an account identifier. If I were able to grab that session ID and make use of it, I would have your shopping cart as well as your account information potentially, and if there were no other protections in place, I may be able to place an order as you using your credit card information because Amazon does store that for you. Now, again, Amazon has far more protections in place than that, including typically requiring you to put your username and password back in. If you are doing something like making a purchase, you would have to log back in to make sure that you are really the person who owns that particular account. So sessions are there to maintain some sort of stateful relationship between the server and the client. And where you would find those session identifiers is in a place like this. So you can see here under the response in the bottom right of this window, it says set cookie NID equals 61 equals NUA HTHF. So that's really something like a session identifier. Even though it doesn't say session ID, that's something like a session identifier to identify me to this particular web server. In this case, it's actually Google. And the way that we store session identifiers is with a cookie. And a cookie is actually a piece of data that is stored on the client side that's generated by the server. And the server actually sends cookie requests to you to see whether you've got the cookie that it may have generated for you at some time in the past. And again, that's how it figures out who you are, because it stored a little piece of information on your system that it can use to identify you with down the road. So if you were to go to weather.com, for example, it may remember the different locations that you've looked at before, and that has to do with cookies that are stored on your system, and you would use that cookie to transmit the data back to the server in order to exchange information about who you are so that the server can give you a more personalized experience. It can make you feel like you're special and unique, and it stores information about you so that you don't have to go searching for it. It's really useful from a usability standpoint. Of course, from a privacy standpoint, that's another issue altogether. But cookies are used to store information on the client side. And again, that's really all about the fact that HTTP was never designed as a stateful protocol. So it's got no capability to do things like store information about you and maintain all of that data. That's all done with stuff that's outside of the HTTP protocol. And in this case, we're talking about cookies. So you can see here in this particular response from the server, it's doing a cookie set. And if it wanted information from me, there would be a get cookie, and I would be transmitting my cookie back to the server so that it can look up things about me, probably in a database somewhere. So session IDs are typically stored using a cookie, and that's how the application maintains a level of state, is with the session ID, where it can map things that you are doing to activities using this particular session ID, and the session ID is stored on your computer using a cookie. You can get extensions for your browsers, or you can get other applications that will allow you to look at all of the cookies on your system, or if you know where they're stored, you can go directly to the hard drive and take a look at them there. But it's not something you can look at directly inside the browser, although there was a time when you used to be able to see cookies from there. They've taken a lot of that functionality out, and now there are other ways to get access and manage your cookies. So that's session identifiers and sessions and cookies. In this lesson, I'm going to be talking about password attacks. So similarly to just normal password attacks against systems, what you're usually doing is some form of brute force. And I'm going to do a quick search here for a user, and I'm going to find web pages that have come from my scans that have a user associated with them or a UID. And here's a good one. Here's a login form, and it looks like there's a user ID and a password that's associated with it. So I'm going to actually send that one to the intruder. And I'm going to go to the intruder. I'm going to take a look at my positions. So I've got a number of attack types that I can use, and I'm going to use a cluster bomb approach because that gives me the ability to manipulate the user ID and the password with two different types of payloads. So in the first payload set, I am going to put in usernames, and Burp Suite has a number of usernames that are built in. And the second payload set, I'm going to put in passwords. And I'm not going to do any options here. I'm actually just going to start my attack. Except that it requires me to plug this in, and so I'm going to do a simple list. And I'm going to go back and actually add the value back in. So I'm not actually playing with the value at all. I'm just going to use one payload to use what it was, and then I am going to go run my attack. And what this is doing is it's brute forcing. So what it's going to do is check all of the usernames with the first password, and then it's going to go check all of the usernames with the second password. And you can see there are like 30 million requests that we're going to be going through here just to do this brute force password attack. Now, one of the interesting things here is that the different payloads have these special characters in them, and usually you wouldn't have special characters because that may open the door to things like SQL injection or cross-site scripting. So normally you would do some sort of input validation on any data that you get, and it's useful to do the input validation at the border between different layers in your application architecture. You wouldn't do the validation strictly at the browser, for example, because that's going to be done in JavaScript, and I can always run a proxy behind your JavaScript and undo any validation that you may have done there. So while validation is useful to do in JavaScript, and you can certainly do it in the browser, there are ways of getting around that. And you also can't guarantee that there may not be something happening at different layers, and so it's useful to do some level of input validation at the different layers between your application architecture. So that's always helpful to do. Now, this is going to take quite a while to run, and I'm not going to actually run it to completion. I'm going to pause the attack here because the goal was simply to show you a different way of doing a password attack and just the ways that password attacks work. So it actually showed me some different things here with regards to the passwords. Another way of doing a password attack against a web application is in cases where there is a clear text submission of a password. So you can see here there was actually no encryption involved in this particular submission of this password. It was all done in the clear, and because of that, I could actually run a sniffer on the network and be able to capture the username and password. So that's another type of password attack that you can use. And it's not commonly one you could use against systems, but often web applications are done without SSL or TLS involved, and so there's no encryption. And sometimes I guess people believe that because we're primarily in switched architectures these days, that they're sort of invulnerable to grabbing passwords like that. The reality is they're just not. And so encryption, particularly since it's pretty easy to do, encryption is just really something that you should be doing anytime you're transmitting data between a client and a server. So input validation is a really good thing to protect against cross-site scripting and SQL injection and other types of attacks. And also you want to be doing encryption on your communication between your web server and your browser. In this lesson, we're going to be talking about encoding. And not only are we going to be talking about encoding, we're going to be talking about decoding as well. So when you're dealing with web applications, often data is encoded in a particular way. And many web testing tools provide you the ability to not only do encoding, but do decoding as well. And you can also get browser plugins like Hackbar, for example, for Firefox that will do some encoding and decoding for you. One of the common types of encoding is base64. So I can do base64 encoding here, or base64 decoding. If it looks like I've got some base64 data, I can use this to do a base64 decode, and you can see down here, that's my plain text for the base64. I can also render this as hex, and you can see the different hex digits in the bottom box here. One thing that Burp Suite has the ability to do is a smart decode. Now, I can do a smart decode here and see whether it will actually render back to the plain text if it can guess whether it's base64 or some other type of encoding. Now, I can also encode this as other types of data. I can do HTML encoding. So you can see this is HTML encoding here. It's actually rendering this in a form that HTML would be able to understand. So you've got the ampersand indicating it's a special character, and then I've got the number sign indicating that I'm going to be giving you ASCII digits here. So if I were to do, let me see, this, it's actually rendering it as an ASCII character rather than typically you would do something like ampersand LT semicolon because it's a less than sign. But what it's actually doing here is it's rendering it with the ASCII character number, and so that's an HTML encoding. We could do ASCII hex, and that's the same sort of thing without all of the HTML bits in it. And I could do a URL encoding, and this is the same sort of thing. It's still the ASCII equivalent, but it has the percent sign, so if you put the percent sign in front of it, you can actually use this in the URL in place of characters. And if you want to do some obfuscation so that it's not clear what's going on, you can stick these into your URL as parameters, and on the server side, it will actually decode it correctly as what it really is, but a normal user is going to look at that and not have any idea what's going on. It's just going to look like gibberish. So you can do decoding and encoding here. The other thing I can do is I can do different hashes, and we've talked about hashes before. So I can do an MD5 hash, and I can do a SHA hash here. And you can see that I've got the hash that comes out of just this short bit of text. So that's encoding and decoding and the different types of things you can do, in particular here with Burp Suite. Although, as I said, there's certainly plenty of other ways that you can do encoding and decoding. In this lesson, we're going to be talking about wireless networking. Wireless networking is pretty much as the name implies, it's networking without wires. Actually, the idea of wireless networking goes back a really long way. We've been doing packets over wireless since the at least 80s and 70s, if not earlier than that. There was an Aloha net for a while in Hawaii that used radios to do wireless networking, and that goes back a really long way. The wireless networking that most people are familiar with, though, comes from the 802.11 standard. And the 802.11 standard is actually maintained by a group called IEEE or IEEE. It's also called Wi-Fi, and Wi-Fi means wireless fidelity. It's a layer 2 protocol that defines connections between endpoints, and in this case, they're using different frequencies in the gigahertz, multi-gigahertz range in order to transmit data from one point to another. Now, there are multiple types of 802.11, and I've actually got something called Wi-Fi Explorer up on my Mac here, and you can see that there's a network that it's found, and it's actually running 802.11bg. Now, 802.11b ran in the 2.4 gigahertz range, and it supported speeds up to 11 meg. G also ran in the 2.4 gigahertz range, and it supports transmissions up to 54 meg. There are a couple of other types that you may have run across before. The first one is 802.11a that runs in the 5 gigahertz range. It was actually adopted in 1999, and it runs up to about 54 meg. So there are 4 primary types of 802.11 wireless at the moment. Although there are new standards being worked on, there's currently one called 802.11ac that supports up to 866 meg for transmission speeds. And there's additionally one called 802.11ad that's in a draft stage now. It's also called Y-Gig, and that will support transmission speeds up to 7 gigabits per second. So Wi-Fi uses this idea of an SSID or a service set identifier in order to give a name to the network. So when you connect, you actually know what network you're connecting to. It's not like with a wire, you pick it up, you can trace it back to the wall and figure out where it's plugged in. With Wi-Fi, since they're radio frequencies, you don't know who you're connecting to without there being a name associated with it. And so there's an SSID. Now, in this case, you can see the channel that's associated with it. It actually gives me a signal strength as well. And I can go to a signal strength graph. Here I've got a signal strength graph for this particular SSID. So Wi-Fi is actually becoming very common. You'll find it all over the place. A lot of places offer free Wi-Fi, like Starbucks, for example. You can get free Wi-Fi, McDonald's. It's becoming just a cost of doing business for some companies because it's really pretty cheap and easy to use. Now, the one thing that you don't get in this particular case, I've got a wireless network with no security on it, so there's no encryption. The reason that I do that here is because I'm kind of out in the middle of nowhere. There's nobody else anywhere near that would be able to jump on my signal, and it's just easier and more convenient for us in the house to not have encryption or have to deal with passwords in order to connect to the network. So if you're out in the middle of nowhere and don't have to worry about people parking nearby and jumping on your wireless network, you can certainly do open encryption and not have that encryption. The downside to that is it's easy to see what's going on, which frankly isn't very different from a wired network where if I can get on your wired network, I can see what's going on there as well. But Wi-Fi does support encryption in a couple of different types, and we will talk about those in a subsequent lesson. But for now, that's just some of the basics of wireless networking and Wi-Fi. In this lesson, we're going to be talking about encryption over wireless networks. When 802.11 was first published, a portion of that included a section for Wired Equivalent Privacy, or WEP, sometimes called WEP. WEP was a way of getting privacy and encryption into this over-the-air transmission medium. And people figured that because we're doing transmission over the air, we don't have any control over where it goes, unlike with a wired network where the wires are only going to go where I put the wires or where somebody puts the wires who has access to the network infrastructure. In the case of radio transmissions, they go absolutely everywhere within a certain range. And if you're within that range, you can pick up these radio signals. So as a result, people decided that we needed some ability to have some privacy so that anybody who could hear those radio signals wouldn't necessarily be able to jump on and hear our transmissions. As a result, we ended up with WEP. WEP was kind of a weak protocol. It used 10 or 26 hexadecimal digits for a password. It also uses a stream cipher, and the stream cipher that it uses is RC4. Now, there's a couple of different ways of doing authentication. You could do open system or you could use shared key. With a shared key, it's basically you've got a password and you use that password to authenticate. And as a result, you get the encryption that results from there. There was a vulnerability in the initialization vector of the algorithm, though. It was small, it was weak, and as a result, WEP can actually be cracked after gathering enough data. Now, I've got here in my Mac OS, I've got my system preferences up with the network, and you can see I've got my Wi-Fi. It happens to be connected to this particular network. I could have it join another network, and I could either do no security, which is the open system. I could do WEP, I could do WPA personal, or WPA2, or I could do one of these enterprise ones as well. So here's the different types of security that I have available, and even though this is on the Mac, you can do the same thing under Windows. If you bring up your network connections, you can start doing different types of connections over wireless, and you can have the same support for WEP or WPA or WPA2. Now, while I'm talking about WPA, let me tell you what WPA is. It's actually a Wi-Fi protected access, and the original WPA was actually an intermediate measure because they knew there were problems with WEP, and they were eventually going to move on to something else. And the thing that they were going to move on to was a better, stronger version. And that was called WPA2. WPA and WPA2 can use a pre-shared key, and that would be for WPA personal and WPA2 personal. That would use a pre-shared key. And the thing about the pre-shared key, it could be a passphrase of variable length, and you weren't restricted to either 10 or 26 digits for your password. You could have however many number of digits or characters that you wanted to in your pre-shared key or your passphrase. In addition to the personal, we have the ability to do enterprise. And let me show you this enterprise here. Is actually a mode called automatic, or we could do EAP TLS. And EAP is extensible authentication protocol, and TLS is transport layer security. So we could use EAP TLS to do our authentication for us. And in this case, it's actually asking for a username and password. So with enterprise encryption for Wi-Fi, you authenticate with a username and password, and there's typically a Radius server on the back end that supports doing the actual authentication with the username and password for you. So that's on the end where the access point is. If I were to go to WPA2 personal, you can see it's just asking me for my password. So the thing that the enterprise components bring is the ability to have individuals log in, and that gives us the ability to have some accountability. So if I connect to a network, I'm going to pass my username and password, and if I get logged in, that will get logged somewhere. And people will know by looking at the logs when I was connected to a particular wireless network. So from an enterprise perspective, having that auditability and accountability is a really good thing, because you know who's been using wireless and who hasn't. And if something happens, you can make a determination as to who was using wireless at any given point, theoretically. So that's WEP and WPA, WPA2 personal and enterprise. That's how you would do the authentication. Now, depending on the implementation of Wi-Fi, there's a Wi-Fi protected setup, and that allows WPA, WPA2 to be broken. If you don't have Wi-Fi protected setup implemented, you're not actually vulnerable. But if you do have Wi-Fi protected setup, there were some vulnerabilities in it that allows WPA and WPA2 to be broken. So even though WPA and WPA2 are newer protocols and they are generally better than WEP, they are not invulnerable themselves. So there have been vulnerabilities in even the newer wireless encryption and wireless privacy protocols. And that's the different ways of doing wireless encryption and having some encryption and some privacy on your Wi-Fi network. In this lesson, we're going to be going over finding hotspots. You may want to find places where there's actually wireless networks available, particularly if you're doing a pen test. You probably want the ability to find all of the wireless networks that are available within an organization, whether you're in the parking lot because you're doing this in a stealth mode, or whether you're in the building. You need to be able to find all of the different access points. And this is the same idea as just being out in the real world looking for hotspots that you could connect to. So we're going to talk about some different ways of locating hotspots and some different types of software that you can use in order to find these hotspots or access points in wireless networks that you can connect to. The first thing I want to talk about is just the idea of using your operating system and using the tools that come with it. In this case, I'm using the Mac OS, and I can just do a little pull down there on my little radio, and it's going to show me all of the networks that are available within a particular range and anything that it sees transmitting. So I can do that. Windows has a similar function where you can use your wireless network adapter and have it show you the wireless networks that are within range, and you can make a determination as to whether to connect or not. Now, with this particular setup, I can see whether one has encryption or authentication associated with it, and that's the little lock. You can see Kilroy WLAN has a lock next to it, and that's because it uses WPA2 in order to do the privacy extensions and have encryption and authentication. So I can see whether something is encrypted or not, and that's just from using the operating system. I don't need any special tools. I don't need to go download anything to be able to do that, just to get a list of the networks that are either known or are broadcasting. Now, mobile devices, most of them these days have Wi-Fi capability, so you can do the same thing. You can walk around with your Android phone or your iPhone or your iPad or your Android tablet or whatever you happen to have. You can walk around and just get it to pull up the list of available Wi-Fi networks. In some cases, it just pops up automatically. Hey, guess what? You walked into range of this Wi-Fi network. Do you want to connect to it? And you can say, yeah, I want to connect to it. And if it's protected, it will ask you for a password. But you can use your mobile device to do the same thing. Now, for years, there have been pieces of software that will do this for you. And here happens to be one of them. This is Kismac. It's actually an implementation of Kismet, which runs under Unix-like systems. And the thing about Kismac is it hasn't been terribly well updated. So there's a problem with actually getting it to work. I've gotten Kismac to work, sort of work on this. And by work, I mean it doesn't crash on me anymore. But it also doesn't generate anything useful from the scan. So while it actually runs and doesn't crash, it's not really what you would call useful at this point. You may have better luck with it. So Kismac is out there, and I think it runs better on older versions of macOS. I have a recent version of macOS, and actually the most recent version fixed some problems that I had running it in older versions. So there's Kismac. As I said, Kismet is available. It's the same sort of thing. It runs under Linux. If you've got a Linux system with a wireless adapter, you can use that. Here's NetStumbler, and NetStumbler runs under Windows. And you can see I've got it running here. The problem I've got with NetStumbler is I'm running it in a virtual machine, and so there's no wireless adapter found. But NetStumbler works pretty much the same. Before you can turn the scanning on, it will pop up the list of SSIDs that it found, as well as the MAC addresses for them, and then the information about the name, the channel, speed, vendor, and all of the other information that you want. And then you could filter that by channels and by SSIDs. So it's got some interesting and useful information. If you have multiple devices, you can select which device, or in this case it says use any suitable device, and there's actually no suitable device available on this system to do that. But works pretty much the same way as Kismac does. We'll show you the list of SSIDs that it's found. Now let me show you one that actually does work. This again is on the Mac, and it's called Wi-Fi Explorer. It's available in the App Store. And you can use Wi-Fi Explorer to get a list of all of the SSIDs and networks that are available. This one provides the same sort of information as Kismac and NetStumbler do. They've got a signal strength, average MAC, signal to noise, and the channel number. Also tells you whether there's security involved in the vendor for the particular access point that we are talking to. In this case, there is only one network that it's finding at the moment. And you can see on the far right column, it says it was last seen. So if you've got an access point that comes and goes, you could leave Wi-Fi Explorer up and it would show you when it last saw it. So you'd have an idea of when it appeared. If you've got rogue access points, sometimes a rogue access point will be turned on and it will show up for a little while, then it'll be unplugged and it will go away. It's where if you run Wi-Fi Explorer for a little while, you'll get a list of everything that it's found, and you'll see whether it's available now or whether it's not. There are other utilities that are available to find hotspots or wireless networks, and you can certainly use any one of those things. As I said, sometimes the easiest way is the best way, and you can just use your operating system. The thing about the operating system is it won't find networks that don't have their SSID broadcast, and you have a better shot of finding those with some of these other tools. So in order to connect to a network that didn't have its SSID broadcast, you'd actually have to know what the SSID was in order to connect to it. So the operating system won't actually show that to you in a list of networks that are available. So he said these other tools have a better shot of finding those networks and displaying them to you. But that's some different ways of finding wireless networks and finding hotspots. In this lesson, we're going to be talking about breaking WEP. Now, as I've mentioned previously, WEP, or the wired equivalent privacy, has been broken, and it's possible to decrypt messages that have been encrypted using WEP. So the way you would do that would be to gather a whole lot of data in order to be able to do this WEP breaking. Now, there's some tools that are available that will do this for you, and one of them I'm going to look at here just to demonstrate how it might be accomplished is called AirCrack. And AirCrack comes with a number of different utilities that do different functions. One of them is called AirMon, and AirMon will actually show me the different interfaces that I've got installed on this system that are capable of doing wireless. So I've got AirMon, and I've got two different interfaces here. I've got Mon 0 and I've got WLAN 0. WLAN 0 is the physical interface that's there, and it looks like Mon 0 is just a duplicate of the same thing. So I've got AirMon going now. I've just started it up on WLAN 0, and what it tells me is monitor mode is enabled on Mon 1. So what I want to do is I want to run arrow dump on Mon 0. And you can see that arrow dump is running now. It's flipping through channels looking for different SSIDs, and this is actually in a location that's probably not going to see a lot of wireless activity, but there is a possibility that an SSID may actually show up here. But what you would do would be to run arrow dump, and it would actually capture a lot of the packets for you, and you'd be able to use that to run AirCrack with. So what I'm going to do is I'm going to let me open up another window while that's running. So I've got another window open here, and I can show you AirCrack. Even though I don't have anything to run it with, I can show you how it's run. So I've got AirCrack here, and I can do different options, and I can feed it a capture file. So I could do force attack mode and use either WEP or WPA PSK. I can select the SSID or the network identifier. So out of the capture, there may be a lot of different SSIDs, and I'm going to tell it which ones specifically. If I've got multiple CPUs, I can tell it to use different CPUs. And here's the different cracking options that I can use. So I could specify the WEP key length, and I could specify the WEP key index. I could disable brute force multi-threading. So there's a lot of different options that I've got here. But in order to run AirCrack, you really need a capture file, which is what arrow dump would provide for you. So you run arrow dump, you grab a large amount of data, multiple hundreds of meg to maybe a gig or more, in order to have enough data for aircrack to be able to brute force the password with. And here you've got the ability to feed it word lists in a file. So the -w and then word list, and you could do the file with all of the words in it that you want to run your crack against. So going back to AeroDump, you can see that I actually found an ESSID. It's gotten 3 packets so far. It's lost 0, and it looks like the power is at -75. And now we've actually lost that SSID. It's disappeared. We've been running for 4 minutes at this point, and we haven't really captured any data. So again, that's because this has actually got a very weak Wi-Fi adapter in it, and it's in a place where the signal isn't going to get to it very well. So the SSIDs will kind of come and go, and it probably won't capture enough information. Certainly won't capture nearly enough information in the amount of time that we've got here in order to be able to do this. But you can get aircrack running on Linux systems. It's actually been ported to other systems as well. Theoretically, you can get it running under Mac OS. It's got binaries available for Windows. You can run aircrack on a Windows system. There are other utilities that are also available that will do web cracking, and you can certainly go out looking for those. This is a pretty common one that you would find mentioned if you were to go looking for information about cracking web. So you may want to take a look into AirCrack. It's actually AirCrack-NG for next generation at this point. They've been using it for a while and actually rebuilt it, so we're on the next generation of AirCrack rather than the old version of AirCrack. So I'm going to kill that. We didn't actually generate any packets, but that's how you would use AirCrack. You would run airmon, get your list of network adapters. You would start up aeromon, and then you would run AeroDump NG in order to get your packet dumps. And then you could run AirCrack against it in order to get the web password and have the ability to log into a web network without actually having the web password been given to you by an administrator or someone who had the rights to give it to you. So that's how you would go about breaking web. In this lesson, we're going to be talking about rogue access points and attacks. Now you can see here I've got up the Wi-Fi Explorer, and again that's pretty typical of a program of this type that is looking to find Wi-Fi networks or wireless networks and displaying information about them. You'll find that NetStumbler is similar to this, Kismet, Kismac, those types of programs are very similar to this. The interfaces may look slightly different. The information is all going to be there. So I'm just using Wi-Fi Explorer here for ease of use and for demonstration purposes. Now you can see I've got 2 network names here, and there's all of the related information associated with them. There's one method of doing a rogue access point, and sometimes you'll find this in the case of enterprise networks, where somebody will bring in an access point and plug it in and give themselves access reasonably close to where they've plugged their access point in. And so that gives some people some rogue wireless access. And in that case, that may provide access to individuals who shouldn't have network access in your building. In an enterprise, people can sometimes plug in access points that will allow them or others to circumvent a wireless access policy on behalf of the organization. And as an ethical hacker, that's certainly something that you want to look after. Another thing that you can do, though, is you can get an access point and have it look very similar, if not identical, to the access point that we've got here. So let's take a look at Kilroy WLAN. Because it's using WPA2 personal, what I could do would be to create a Kilroy WLAN myself and set up an access point for it And instead of giving somebody network access, what I'm really doing is copying the authentication for this particular network. So in that case, the rogue access point isn't about providing convenient wireless to employees or circumventing access policies on behalf of an enterprise. What it's about is gathering data, and specifically gathering authentication data for legitimate access points. Now, you run a risk there of whether it looks identical enough or not. If it doesn't look quite identical enough, there's a possibility of it being detected. The other thing that you need to do is make sure that somehow you get the legitimate access point off the air, whether you do some sort of denial of service attack against it, or if you've got physical access, you just simply unplug it, or whatever you do, you need to get the real access point out of the equation so that yours shows up. Another way of doing rogue access points, and you'll find this sometimes in public places, you just stick up an access point where there is no authentication. So like Speedwell Home here has no security. It's just an open authentication, open access point. You throw it up, and sometimes people will just connect to those and start transmitting data. In that case, if you've got control of that access point, you could be sniffing the data that's going along, and you may see usernames and passwords being sent across. You may see credit card information. You may see a lot of different details. You may see intellectual property. So you could set up an access point that just has open access and put it in a public place, and you would see a lot of people, particularly if it's a busy public place, getting access to your access point and bypassing the ones that have passwords associated with them or have some authentication mechanism. Give somebody free Wi-Fi, they're probably going to take advantage of it. That's another different way of doing a rogue access point. And if you are doing a penetration test, you certainly could set up an access point or even set your computer up as an access point and use it to start gathering data from the employees at an enterprise or an organization if you are doing a penetration test or an ethical hack against them as a target. In this lesson, we're going to be talking about wireless sniffing. So sniffing over wireless networks obviously requires a wireless interface, and it requires a sniffer. So I've got a sniffer here, and that's Wireshark, and I do happen to have a wireless interface. And so I can start up sniffing on my wireless interface just like that. And you can see all of the network traffic that's going across here. So depending on the type of sniffing that you want to do, something like this may be adequate for you, where you really just want to sniff a wireless network. You want to look at the traffic going across it. You are not as concerned about specific portions of the wireless protocols themselves and what's happening there. You're really just interested in the network details, so all of the packets that are flowing across the network. You want to sniff as though you were plugged into the wire. So something like Wireshark is perfectly adequate for those types of situations where you've got a wireless card and you need to do some sniffing, so you grab Wireshark or something similar to it, and you can just start sniffing on the wireless network. If you are more concerned with wireless activity in terms of the things that are going on at layer 2 and layer 1, then you probably want something like AeroDump. And here's AeroDump. It's part of the AirCrack suite of programs. And here I'm going to run AeroDump, and I'm going to specify that Mon0 is my network interface. So you can see it's skimming through all of the channels looking for any sort of traffic that's going on the wireless networks. And here's one of the differences between this and Wireshark. With Wireshark, I have to be connected to the network in order to actually get packets from it. So it's like I'm plugged into it even though it's wireless. Here with AeroDump, what I'm doing is I'm grabbing all of the Wi-Fi packets that are coming over the air, and I don't really care whether I'm attached to the network or not. I'm just grabbing everything that comes off the air. So here's where I have the potential to grab packets that are part of a wireless network that I'm not attached to, and it also gives me the ability to see details at the really low layers of the protocols. Of course, as we've discussed previously, this sort of tool gives you the ability to capture data that can be used to crack wireless encryption protocols. So here's another reason why you may want to use something like AeroDump as opposed to Wireshark. So really there's a couple of different ways of thinking about wireless sniffing. One is just sniffing wireless networks that you're on, which again, you can use just any common sniffer like Wireshark or TCP dump. And another one is actually sniffing the air for actual wireless information or Wi-Fi data that may or may not belong to networks that you are attached to. So you can see here on AeroDump, I've actually picked up a station, and it doesn't seem to have a name attached to it that the program is displaying. It's just got the BSSID, which is hexadecimal, and the station's MAC address. But I could use this to start capturing a lot of packets if I let this run long enough, and if it had a network interface that was capable of pulling a lot of data in, I could certainly do that. And that would be a way of doing wireless sniffing, particularly if I were interested in doing something like encryption cracking for WEP encryption or WPA encryption. But those are a couple of different ways of doing wireless sniffing. In this lesson, we're going to be talking about protecting your wireless setup against attack. So how would you go about protecting your wireless networks? Well, there's a few different ways of protecting your wireless networks, and I've got the configuration up for an access point here, and I'm going to talk you through some different things that you can do that would protect your access point or your wireless network. So we're going to skim by turn wireless on because we're going to assume that wireless is on. I can change the SSID, and one thing that you may do to change the SSID is to give your wireless network a name that's maybe not so obvious as to what it is or what business or enterprise it belongs to. You could set it to a string of random numbers and digits and hope that somebody doesn't figure out that it's something of interest. Of course, if you've got a particular curious mind like me and several other people who do this type of work, then that's just going to be a red flag for somebody and say, look, this is something that looks a little odd, and so maybe we should go take a look at what it is. So there's a bit of a juggling act here. Do you want to give away information about what it is and what it's for? Do you want to potentially call attention to it by giving it a completely random name, in which case it's going to stick out a little bit? So think a little bit about what you want to name your wireless network and what SSID that you're going to use. You can set different channels, although frankly, wireless scanners are going to be able to pick up all of the different channels that you've got or that are available through a particular subset of the 802.11 protocols. But you can definitely select channels, and some of this has to do with where there's interference and where there isn't interference. Sometimes if you're getting bad transmissions and slow speeds over your wireless, you can choose different channels and maybe get better performance. So one of the first things that you want to do, aside from what we've talked about, is make sure that you've got some sort of encryption turned on. In this case, I've got WEP turned off. And that's because where I'm located, there's nobody nearby. There's almost no chance of anybody coming anywhere near where this is transmitting to be able to see any of the data that's going across it. And so for ease of use here, I've just turned WEP off on this particular wireless network. If you do turn WEP on, you have the ability to set your wireless key. And you can set either hex or ASCII, and you've got an opportunity to set 64 40-bit key or 128 104-bit key. And the difference there is the key length, obviously, and the amount of characters that you have to type. I would strongly recommend going to a 128 104-bit key for your password. And that's for WEP, or the wired equivalent privacy. And again, you can choose hex or ASCII depending on how good you are at remembering things. You run the risk of, if you're going to do a long hex password, of needing to write it down somewhere, and that can be a bit of a challenge. Now, I've got some advanced security settings over here, and I've got the ability to either turn on or turn off my SSID broadcast. So wireless networks typically by default will broadcast their SSIDs, and that makes it easy for users to connect to them because they see that there's a wireless network and they know that they need to connect to it. It's one less thing that they have to configure or type. And so turning on the SSID broadcast in most circumstances is probably a good idea. Again, it's an ease of use thing more than anything. If you're really paranoid and you're really security conscious, you can disable the SSID broadcast. That doesn't guarantee that you won't be seen, however. There is a possibility that wireless scanners will pick up your network even though you're not broadcasting the SSID. As a matter of fact, it's a pretty good chance that Wi-Fi scanners will pick up your network. Another thing that you can do to protect your network is basically put up some access policies. Now, this takes a lot of administrative overhead and there's a lot of work associated with it, but if you don't have a lot of users and you're really conscious about who you're going to allow to access your network, what you can do is require that the MAC addresses match what you've put in. So you can set MAC authentication. In other words, your layer 2 or physical address, your MAC address, has to be in a table of addresses on the access point before the access point will allow the communication between your device and itself. So that's another way of really restricting who gets access. And that's not even a measure of who has a username and password or who has the passphrase for the wireless network, which can be shared or overheard or read if it's written down. This comes down to, do you have the right piece of physical equipment to gain access to this network? And you either do or you don't. If you don't, game over. You don't get to go any further. You don't get to plug in the passphrase that you think you knew. You are just done. So that's a way of really locking down your wireless network. Again, though, as I said, that's a lot of administrative overhead. You've got to go find all of the physical addresses and plug them in. And anytime you want to add a device, then you need to add that MAC address. Anytime you've got a visitor of some sort or another that you want to give access to your wireless network, you've got to add the MAC address. So there's a lot of overhead to doing that. But these are all different ways that you can use to lock down your wireless network. In this lesson, we're going to be talking about evasion, and specifically, what is evasion? Evasion is what you would expect evasion to be, just simply based on the definition of the word. When you evade something, you're trying to get away from it. So evasion, in terms of ethical hacking, what is it we're trying to avoid? Well, for a start, we're trying to avoid getting caught. We don't want to have the people at our target find out what it is we're doing, particularly if what we're doing is sort of a red team approach where they don't know that we're trying to attack them. In more practical terms, what are we trying to avoid? we're trying to avoid detection by a firewall. In other words, we want to be able to get through the firewall, so we don't want the firewall to actually be able to block what it is we're trying to accomplish, so we want to evade the firewall. We also want to evade intrusion detection systems because that's going to set off alerts as to what it is we're doing. So using evasion, there's lots of different techniques. We've got things like log alteration, where you can't see what I've done if I've removed the evidence of it. You can hide amidst noise. In other words, if there's a lot of things going on, you may be able to slip some things in. You can do a low and slow approach, where you're only sending messages to your target on a very infrequent basis, so they're not going to notice something like a fast and heavy-handed port scan. If you were to slow it down and only send a couple of packets here and there over the course of several hours or days, they may not be able to see what it is you're doing. There are other types of evasive tactics. Unicode attacks were pretty popular for a while, where rather than sending single-byte ASCII characters, you would send multi-byte Unicode characters. And if the IDS or the firewall weren't capable of seeing that sort of thing, then you may be able to get in that way. Fragmentation attacks also have been popular from time to time, where if I send a fragmented packet, a badly fragmented packet, these different systems may not have the ability to stop and put the whole packet together before sending the fragments on their way to the eventual destination. So as I said, there's lots of different techniques and tactics involved in doing evasion, and it takes a little bit of practice and a little bit of skill and some understanding to know what sorts of techniques and tactics you can use at any given point. Sometimes it's just a matter of brute forcing it and trying a lot of different evasions in order to see what's going to get through in the case of trying to get through a firewall, for example. But doing evasion, understanding evasion is a really good strategy. It's a good set of tactics and techniques to have under your belt so that you can continue to be successful in getting into your targets as you go forward with your penetration testing and ethical hacking activities. Why evasion? You want to be able to avoid detection. The other really important thing is that malicious attackers are going to have similar strategies, and so if you can get in and avoid detection, or if you can slip attacks in using these evasive maneuvers, then it exposes additional weaknesses in your target. In this lesson, we're going to be talking about steganography. And steganography always reminds me of the movie Yellowbeard. In the movie, Yellowbeard's a pirate, and when his son Dan was an infant, he had a map to a particular treasure location tattooed on his son's head. When the hair grew, it obscured the fact that the map was there, and you had to know that the map was there or just shave the head in order to find the map. So that's an example of steganography. Steganography is hiding information inside something else. So in that case, I'm hiding a map underneath a head of hair on a head that wouldn't normally have a map tattooed on the top of it. So there are several examples of the use of steganography where I may have text that I want to embed in something. And one of the really popular uses of steganography is to take an image and hide some other piece of data in it, whether it's an image or whether it's text or whether it's something else. So I've got this program here called QuickSteg, and I'm going to open an image. I'm going to open this one of a koala. And I've got some text here. And now I'm going to hide the text inside the image. And I'm going to save the image. And I'm going to save it as something different here so I know. Now let me just exit so there's nothing up my sleeve here. There's no trickery involved. I'm going to go back and I'm going to launch QuickStego. I'm going to open my image. Obviously, if I were doing this for real, I wouldn't call it Koala Steg. I would call it something else. I would either use the same name or I would pick something else. So I'm opening up my Koala Steg image, and you can see it shows the text that was stored in that image. So that's a quick way of sending messages to people without actually having the message seen. You could have an arrangement with a friend where you would send an image to them. It would have a message hidden in it, and they would know to open the image in their steganography program, and it would display the text for them. So that's on the Windows side. On the Linux side or the Unix side, there's a program called StegHide. And it does the same sort of thing where I can take this program StegHide and I can either embed data or extract data. So I can say I want to embed data and I want to embed a file inside another file. So here I've got the embed file and the cover file. I could also specify a passphrase, and the passphrase would put an additional layer of protection on it where there would now be a password associated with it, and in order to get the hidden file or the hidden text, you would have to know what the passphrase was. So I have also got an option here to do a stego file. And if you didn't want to write the results back to the cover file, you would write to this stego file as well. And you can see there's a number of other options. But it uses the same sort of techniques that we just saw in QuickStego. It's a command line program with Linux, and you can put images inside images, which is something that QuickStego actually didn't have, was the ability to embed an image inside of an image. And sometimes that's useful if you're doing espionage or some other sort of activity where you need to send pictures to somebody. Or another way of doing it is if you've got some material that's particularly sensitive in a picture form, you could hide it inside something else, and that way only the person who was supposed to be seeing the sensitive picture that was hidden inside the other picture would know to open up a steganography program and pull that hidden picture out. Everybody else would see a picture of a koala or a bunny or whatever it was you were sending along. So that's steganography, which again is really just hiding one piece of data inside another piece of data. In this lesson, we're going to be talking about stacks and heaps. Stacks and heaps are two different ways of storing information inside of memory, and they also have two different uses. So in terms of the memory layout, I've got a diagram here. This is how a program's memory would be laid out. So when you get allocated a chunk of memory, this is how the program would put all of the different sections that it has into place in memory. So the low memory, so let's think about low memory as being address 00000. And high memory, let's say, is FFFFF. So the low memory is where we would start what we call the text segment. Now, the text segment is where all of the program resides. So all of the actual executable code lives in the text segment. Underneath that, we would have the data segment. Now, the data segment is where any data that we know about during compile time would live. So if you've got global variables that have actual values that are associated with them, those would get put into the data segment. Underneath that, we have the heap. Now, the heap gets any memory that is dynamically allocated. So if you have a program that's using something like malloc in C, that's doing memory allocation, and it's doing that dynamically. It's doing it at runtime. That memory would get allocated off of the heap, or those variables would get stored in the heap or on the heap. Now, underneath the heap, we have the stack. And the stack is a chunk of memory that gets used in a particular way. So when the program is running, as different functions are called, we put stack frames onto the stack. So the stack is going to start at the highest point in memory and grow down, or if you're looking at it from the perspective of this diagram, it's actually going to grow up towards low memory. But it grows towards the heap, and the heap actually grows towards the stack. So we start the stack at the highest point possible, and we start adding memory to that in the case of putting stack frames onto it. And the stack is used just like you would think of any sort of stack, and the classic example is a stack of dishes. You've got a stack of dishes, you throw more dishes on top, you're always going to use the most recent dish that's on the stack. So you're going to use the topmost piece of the stack. Same thing here. When we are running a program and we call a function, we put a stack frame on there. And you can see the stack frame consists of function local variables. So any variable that's local to a particular function and is not dynamically allocated. In other words, you've declared it at compile time and you're not doing any sort of dynamic allocation of memory using a function like malloc, for example. Underneath that, we have the base pointer, which points to the bottom of the stack. And then we have the return pointer, which is an instruction pointer. And the return pointer actually points to the instruction where we need to jump back to when we have finished with this particular function. Underneath the return pointer, we have calling parameters to that particular function. And it's this stack frame where we end up getting into a certain amount of trouble when it comes to attacks like buffer overflows and sometimes attacks like format string attacks. So we're going to get into buffer overflows and format strings in some subsequent lessons, but keep this diagram in your head as we're working through some of those so that you can remember what the memory layout looks like, where the stack is located, where the heap is located, and particularly what a stack frame looks like, and how a stack frame is associated with a particular called function, and how all of the data in that particular stack frame is associated with that particular called function. So that's stacks and heaps and how memory is laid out for a running program. In this lesson, we're going to be talking about buffer overflows. Now, a buffer overflow is when you have a chunk of memory and you've allocated some amount of space to it, and the amount of data that you are trying to put into that actually is longer than the amount of space, or bigger than the amount of space you've allocated to it. And the reason that buffer overflows actually work is because of the way the stack is put together. Let me bring up the memory layout diagram here again, and you can see the stack frame. Let's say I've got a local variable in a function, and I actually try to stuff too much data into it. What I have the possibility of doing is putting that data into the space in memory where the return pointer is. And if I can manipulate the return pointer in a particular way, then I can have some control over the flow of execution of the program. meaning if I can place an address in memory into that exact spot where the return pointer is, I can actually manipulate where the function is going to return to in memory. And if I can also put a bunch of code into memory and send the program back to where that code begins, then I can have the program do what I want it to do, as opposed to what it was originally designed to do and what the program and what the code was designed to do. So let's go back to talking about buffer overflows. Let me show you a piece of code here that's actually vulnerable to a buffer overflow. Now, this is written in C, and you don't actually have to understand C, although I'm going to walk you through a little bit. The top two lines are where I'm including some chunks of code from libraries that live outside here. So I'm doing an include for a standard I/O library and a string library. The line that says int main actually defines a function. So main is the function, and it's the function that the compiler knows is going to be the entry point. So this is the place where the program is going to start. So when the compiler puts the program together, this is going to be the entry point for the program. This is that one function. It's a function just like any other function in terms of it getting a stack frame. The difference with this, though, is it's a special function because the compiler knows to do something particular with it. So I've got two parameters being sent to the main function. The first is the count of the number of arguments on the command line, and there's always at least one argument. That one argument is always the name of the program that has been run. So I've got the count of arguments, and I've also got an array of strings with all of the other parameters in it. So my first line in the actual function defines a character array, which is a string, and that string is going to be 10 characters long. So I've only allocated enough memory for 10 characters inside that string. Now I'm using a function called strcopy, and I'm copying the second argument into the string. And you'll see the number 1 inside of the brackets there with argv. And the reason why it's 1 is because all arrays are 0 based. So the first string inside the argv array would be the name of the program, and the second one is the one that we're going to be using here, and that's the number 1 because we would have started with 0. So I am copying argv1 into this variable that I've called str. So I'm using this strcopy to perform that copy function for me. And finally, I am printing out finished along with a string, and I'm passing the variable str into there to be slotted into the space where the %s is. And we'll get into the %s when we start talking about format strings, but that %s is actually a format string that defines the format that printf is going to use to do the actual printing of the data. So I've run the compiler on this. I've got an executable out of it, and I'm going to show you using this. Now I'm going to make use of Perl here. So I'm just doing a simple Perl program. And these backticks, like this one right here, say run what's inside of here and then use what comes out of that on the command line in its place. So what this command line here is going to do is it's going to run that little Perl program, which is just a print statement, and it's going to take the result of that print statement and put it on the command line after this program call buffo. So let's see what happens here. So actually nothing happens here. You can see that I've actually managed to cram 12 characters or 12 bytes into that program space, or into that space where that variable is. So let's try it with some more. Looks like I can do 20. Let's do 30. Here we go with a segmentation fault. Now, a segmentation fault means I have tried to access a piece of memory that I don't have access to or I don't have rights to. So I've tried to jump to a place in memory that's not actually part of the memory allocation that I have been given. So that's what the segmentation fault is. And that segmentation fault is actually the opening for a buffer overflow attack. So what we've done is we have done a buffer overflow, which actually we did with the 12 characters that we put in. We actually overflowed the buffer, just nothing bad happened as a result of it. It wasn't until we got to 30 characters or 30 bytes where we actually ran into the return pointer so that we were unable to complete the program without a segmentation fault. So that segmentation fault is an indication that something has gone wrong where we've tried to jump to a memory segment that isn't actually part of the program. So that's what a buffer overflow is. That's what goes into a buffer overflow, and that's a small program or a program fragment that actually incorporates a buffer flow in it. In this lesson, we're going to be talking about format string attacks. So I've got this program here that's vulnerable to a format string attack. And again, this is written in C. And I'm going to walk you through the program here. Again, at the top, we've got 3 include lines where we're including definitions from libraries that are external to this particular program. So I've got the standard IO and I've got the string library. And then I've got just the standard library. And the standard library has functions that don't really belong in any other specialized library. It's just the collection of a bunch of miscellaneous functions that are part of the C standard. And so it's the C standard library. So we've included that as well. We've got the main definition for the function. And then I've got a variable underneath that I'm calling x, and x is a pointer. And I'm not going to get into a lot of detail about pointers, but a pointer is a variable that's actually an address, and it points to a chunk of memory. And since I'm doing a dynamic allocation with malloc, it's going to point to a place in the heap. So this variable with the address is stored locally in the stack frame, but the address that it points to is actually in the heap. And I'm doing a string copy here, and then I'm just calling printf. Now, normally I would call printf with something like this. And I would have my format string, which is the %s, which tells printf, this is the format that I'm printing out in. I've got a string that I want to print, and then X is that string, and that's where I want to put it. But what I've done here is I've just done printf without any format string, and so that's where I become vulnerable to a format string attack, because I haven't provided the format string as a programmer, and so I open the door to an attacker actually creating a format string and passing it into my program. So what I'm going to do is pass a variable in as an argument, and in this case I'm looking for a hexadecimal value. So I didn't print out the %x, even though that's what you would think would be printed out here because of the way the program is. I've got the printf, and in parentheses I've got x, which is the variable. So I'm printing the variable x. And normally you would expect that %x would be my variable, except that I didn't provide a format string in printf. So printf took that first piece and assumed it was the format string. And so it took the %x and said, you're looking for a hexadecimal value. And then it grabbed the next thing off the stack. Since that's what it's programmed to do, that's how a function call works. It just starts grabbing values off the stack. So That's what printf did, is it grabbed the next value off the stack, which could be anything. And you could do this a couple of times and see whether you get different values. So I could put quotes here around this, turn it into a format string, and in this case I get that value and I get a 0 for my second one. So this is how a format string works, though, where a programmer is calling a function that requires a format string and they don't actually provide the format string. That allows an attacker to provide the format string, and because of the way stacks work, it has the possibility of grabbing data right off of the stack. And that data isn't part of the function that has been supplied by the user. It's some other piece of data. Now, with format string attacks, you can do things like getting return pointers if you can dig deep enough into the stack. You can also use a particular format, which is %n, sometimes in order to inject code into the stack or inject data into the stack. And that's something that you may be able to do as well. So in general, though, this is a format string. This is the basics of a format string attack and what a program that was vulnerable to a format string attack would look like. In this lesson, we're going to be talking about decompilers and decompilation. The idea behind decompilation is that you want to take something that looks like this, where it's just a whole lot of binary digits, or in this case, hexadecimal digits, but something that's just raw binary, and you want to get back to something like this. Now, there's a lot of problems with decompilers and decompilation. One of them is just inaccuracy. So the way that compilers work is you take a program and it runs through and translates the human-readable program into something that can be run by the computer. In other words, it's going to translate that to machine language. Now, the problem that we run into is different compilers will do things in different ways. So if you've got an optimizing compiler, for example, it may take a chunk of code and do something different with it to get it into machine language than another compiler would. There's not just a simple conversion, and that's particularly true when you get into really complex programs, particularly programs that have multiple modules to them, multiple dozens or multiple hundreds of modules to them. When you get to that point, decompilation just becomes really challenging, and beyond challenging, almost impossible. So you get conversion inaccuracies going from machine language to actual human readable code, where what comes out of the other end of a compiler probably won't look anything at all like what went into it when the program was first written. There's another problem with decompilers, and that's legality. The legality of decompilers was challenged almost 20 years ago, and so the courts have ruled that certain conditions have to be met before you can do a decompilation of a program, and that's partly because of the intellectual property that's involved. If I could decompile a program and get perfect, flawless code back, then I could take your code that was protected by copyright or patents or whatever, and I could start making minor alterations to it so it effectively worked the same way, but was just enough different to get around copyright laws or patent laws. Then I could start selling your program, basically. And that's not something that generally works very well in a capitalist economy, which is, of course, why software manufacturers started taking this whole decompilation thing to the courts. Now, because we can't decompile things like C programs doesn't mean decompilers are absolutely out of the question. So there is a program called Flasm, which is a flash assembler and disassembler. So when you write Flash programs, or you write programs in the Flash ActionScript language, and then you compile them, it compiles them to this intermediate language, and that can be disassembled back into something that resembles Flash. Same thing is true with Java, although it's becoming harder to find Java decompilers. For a while, there were Java decompilers that would take the Java intermediate code, the bytecode, and be able to come back with reasonable Java out of the other end of it. So you can certainly do decompilation if you've got the right kind of language or the right environment, but there are certainly a lot of challenges with decompilation as well, which is why decompilers are really, really hard to find these days, if not impossible. In this lesson, we're going to be talking about reverse engineering. Reverse engineering is the idea that you can take something and be able to observe it in particular ways and recreate what it does, or at least its functionality, so that you've got something that reasonably represents the original. So let's say I've got program A, and it does some series of functions. The idea of reverse engineering is I could take a look at program A and duplicate what it does in program B. So I'm not actually stealing program A, I'm just using it as a model for the program I am writing. Now, there are some different techniques for doing reverse engineering. Some of it is just simply observation. You can observe what a program does and be able to say, okay, so it does function X, Y, and Z, and these are things that have to go into my program. And so you could then go about writing these particular functions or features so that your program pretty well replicates what's going on inside of program A. Now, another thing that you could do would be to use something like a disassembler. So I've got a disassembler here, and I'm just going to disassemble a piece of code. And this is from the buffer overflow attack that we had used earlier. And I'm doing a disassembly on this binary program. And this is what the assembly language from this binary program looks like. So it's a file full of machine language. And what we've done is used a program to turn that machine language into human readable form, which is assembly language. Now, it's not hugely readable, but it's certainly better than what we had before. So here's the actual program in assembly language that was that buffer overflow attack program that had been demonstrated in a previous lesson. Now, you could use a disassembler to get an idea of how the program worked and take a look at the actual assembly language code and see what was going on. You could also use something like a debugger, and with a debugger, you could follow the flow of execution. This is along the lines of the immunity debugger and the Ollie debug that we had used previously. So here's a different debugger. This is GDB. And this is the GNU debugger, and it runs under Linux or Unix-like operating systems. So GDB is capable of doing debugging as well, and this is a command line program, although there are front ends that will work with GDB. But this debugger will allow you to step through the flow of execution of a particular piece of code and be able to understand how it works and what it's doing. And from that, you should be able to, or may be able to, determine how that particular section of your program should operate. So that's another way of doing reverse engineering. Now, you may find that reverse engineering is a bit of a questionable practice because there's the potential of violating patent laws and copyright laws, and you're really walking all over intellectual property, possibly. So you may find reverse engineering questionable when it comes to looking for vulnerabilities and exploits. However, reverse engineering is sort of a critical function. So you've got to be able to dig down into the program and look very closely at what it's doing in order to find where there are a possibility of vulnerabilities and where those vulnerabilities have the potential of being exploited. So reverse engineering isn't something that's done on a regular basis by most IT professionals. It's not even done on a regular basis by a lot of ethical hackers or penetration testers. But for some people, reverse engineering, and particularly the ability to use a debugger in a way that gives them some deep insight into the program, that's definitely a skill, and it's one that probably not a really large number of people possess. But that's reverse engineering. In this lesson, we're going to be talking about protecting against buffer overflow attacks. So we've talked about buffer overflows and how those actually work and what it looks like in memory to trigger a buffer overflow. Now we're going to talk about what do we do to protect against buffer overflow attacks. So the first thing I'm going to show you is how to do it from a programming perspective. So I can show you the buffer overflow program again, just to remind you. And you can see there under the definition of the character array or the string, we've got this str copy. The str copy will just take a chunk of data and try to stuff it into a variable regardless of the size of either one of those variables there. So what I can do is I can replace that str copy with something called strn copy. And one of the nice things about Unix systems is the manual pages or documentation are included, including for programmers. So here's a function, I don't really remember how to use it. I can do man strn copy, and here's the manual page. And it actually includes str copy as well. So you can see the definition there is for a function that returns a pointer to a character, and strn copy takes a destination, a source, and a size. And it's that size that's the really important bit. So what I can do, I can go in and edit here and change this to strn copy. And then I can insert a 10 at the end. And what that's going to do is it's going to say, once you have copied 10 characters or 10 bytes, you should stop. So it gives me some control over the amount of data that I have actually copied. And I can make sure as a programmer that I only copy enough data to fill the space that I have allocated. So I don't try to copy more data than I have actually allocated to a particular variable. So that's something I can do on the programming side. So we've got this memory layout, and I can't rely on all programmers to go do the right thing. And there's certainly a lot of programs that have been written over the years that are vulnerable to this that are not going to be rewritten for a variety of reasons. So there are probably some things that we should think about doing to protect the operating system. And those are things that we can do in the operating system kernel in order to protect the system and keep applications from doing bad things. So one thing that we can do to protect against buffer overflow attacks is the portion of the memory layout in low memory where all of the executable portions of the program are, that should be the only thing that actually can be executed. So when we get to the portion of the memory layout where the stack is, the operating system should say, hey, that's a stack and nothing out of there should be executed. So we should protect against buffer overflows by making sure that the stack is non-executable, meaning you can't inject code into the stack and then manipulate the return pointer so that it points into the stack and executes the program code that you have just uploaded in. So we should make the stack not executable. That's one way of doing it. Another thing that we can do is we can randomize the memory locations. So the way it used to be was every time you ran a program, you were pretty much guaranteed to get the same memory allocation. Since all memory allocations are virtual, you're not being given real memory addresses. You've just got a virtual address that the operating system manages and does the translation back to the real address. Since we've got virtual addresses, what we can do is randomize the starting point of the memory that you are given. So every time you run the program, your program is going to be given a different address space. In other words, when you run the program, you can't always guarantee what an address is going to be. And that's one way buffer overflows worked pretty well, was they could predict where the program was going to be at any given point and know the memory location that they needed their return pointer to point to. So if we've randomized particularly the stack for the memory layout, every time they run a program, it's going to have a different memory address. So it's going to make it a lot harder to figure out where they need to set that return pointer to execute the code that they have stuffed into the stack. So that's something else they can do. And you certainly see modern operating systems are doing stack randomization because it's something that they can do and that they have some control over. So they do stack randomization, where they randomize the layout of the stack and the addresses that you're provided. So there's something else that can be done, and it's kind of an interesting concept. It's something called a stack canary. And you may have heard stories about the canary in a coal mine, where coal miners would take a little caged canary down into the coal mine with them. And the reason for that was because the canary is a particularly sensitive bird. And if there were gases in the coal mine that were being released from their mining activities, the bird would die from these toxic gases. And when the miners noticed that the canary was dead, they knew it was a signal that they needed to get out of the coal mine because there were gases that they may not be able to smell. And so they could soon be dead as well if they didn't get out. So it was a signal to get out. So a stack canary is where we place a piece of data in front of the return pointer. So you can see there in the stack frame, function local vars base pointer return pointer. What we would do would be to place a piece of data in front of the return pointer that we knew about ahead of time. So when it comes to returning from the function, we would check the stack canary in memory against the stack canary that we knew that it should be. And if the values differed in any way, there was a pretty good chance that the return pointer had been corrupted in some way, and we should just dump out of the program. We should get out of the coal mine. So that's a stack canary. That's where you put a piece of data in front of the return pointer and then do value comparisons to determine whether you think the return pointer has been corrupted or not. So that's another way that we can protect the program and the operating system from these buffer overflow attacks. But that's a few different ways that you can manage protection against buffer overflows and buffer overflow attacks.